Welcome to Power System Analysis using ETAP. In this lecture, we are going to figure out why do we use Power System Analysis software. So the planning, design and operation of industrial and commercial power systems require engineering studies to evaluate existing and proposed system performance, reliability and economics. Studies properly conceived and conducted are cost-effective way to prevent surprises and to optimize equipment selection. So basically, power system studies is required for three kind of things. The number one is at the planning stage, number two is the design stage, and number three is the operation stage. At planning stage, we want to know that if we plan a system in a certain kind of way, how it is going to react, what will be the performance of the system. Will system be economically viable? Because we want to reduce the economics of the system, that what kind of equipment do we need to use. Secondly, when we come to the design stage, at design stage we want to know that a certain amount of equipment, will it be enough for this kind of system. For instance, if we are designing a transformer, we want to know that the load in the system is enough that it can be fed through this transformer. The transformer will not get overloaded if certain amount of load is available in the system. Similarly, a cable in a system or a cable in an industrial network will not get overloaded once the power flows through it. So these kind of decisions we have to take during the planning and the design stage. Similarly, during the design stage, the studies identify and avoid the potential deficiencies in the system before it goes into operation. Whereas in the existing system, when the system is already in the operating stage, that we have an existing system, it is working. If we want to perform, why do we want to perform the studies for an existing system? So that we can help locate the cause of equipment failure, the maloperation and determine corrective measures for improving system performance. For instance, if you have two transformers in a system and in one transformer gets tripped or it gets damaged and it is not available in the system. So will my existing equipment or the remaining transformer will be able to feed my system load? So if we want to answer these kind of questions, again we need power system analysis software. Although hand calculations are good, but they are only suitable for estimating and operating characteristic of a few individual circuits. For instance, if you have a very simple circuit which consists of one transformer, one transmission line or a one feeder and minimum amount of load, 3 or 4 loads, maybe that is good. But consider a system consisting of several transformers, several feeders, several kind of motors. And if you have a big system or a complex system, then hand calculation becomes very complex. So in this case, PSA software or power system analysis software comes into play. They make your calculations easy for you. So the complex power system analysis requires the use of computers and specialized program. Accurate calculation of voltages, power flow or short circuit currents throughout an industrial or commercial power system would be impractical without the use of power systems. It is going to take you so many days to perform a calculation if you want to do it hand calculation. The complexity of the modern power system makes studies difficult and tedious and time consuming to perform manually. The computational tasks associated with power system studies have been greatly simplified with the use of digital computer programs. So now, why we use software? Because it makes our life easy. What we have to do is we simply have to input different data into the power system software, and based on this, it calculates the voltages, the power flows, the losses, the short circuit currents for us. And with the help of this, the calculation, which would have taken you many weeks to perform by hand, only takes few minutes or hours. So with the help of this, you increase your productivity and eliminates or minimizes errors compared to the manual calculation. Because when you are doing manual calculation, you will be using the calculator or you will be using by the hand, and you may not be able to go up to several decimal places. But if you use a software, it can take care of such things. So now the next thing is, what are we looking for in a ETAP software or a power system analysis software in general? So what are the kind of things that should be available in a software, so that you should be able to use that kind of software? It should provide validation and be reliable. So what do we mean by validation? By validation, we mean if we input some data, so software should be able to tell us whether this data is okay or not. And secondly, the output should be reliable. We should be able to rely on the output, that the output we have gotten from this software is okay. There will be no error in this software. Similarly, it should be usable, user-friendly and capable. So if it is easy to use, more people will be able to use this software, so it becomes easy. So user-friendly is, being a user-friendly software is a very plus point. Set up system SLD which complete switchgear details, cables, transformer, other electrical component with their actual electrical parameters. So if you have a kind of a software which can do these things, whatever the data you have in actual form, if it can be directly input into the software, it will be very easy. You will not have to go through the calculations. These calculations will be taken care of by the software itself. So we need a kind of a software in which we can graphically define our system and input the values. Software provides results like load flow, alerts for overloaded equipment, voltage violation at plants, bus, etc. So the software you are using should be able to provide you with the results. So what kind of results we are interested in? For instance, if we have an industrial facility, we want to know what will be the voltages at each different nodes in this industrial system. Secondly, what will be the power flowing through each equipment in the system? Whether do I have overload in my system or not? So these kind of things should be able to tell by the software. Software also calculates short circuit ratings at all points of the electrical system and perform various studies such as selective protection coordination, arc flash, motor starting, transient stability. So as we will move on with the software, we will try to see things. Okay, fine. We have this load flow. So what about the short circuit? So a particular software which you are using should be capable of performing all these kind of studies. These are the most common type of studies which are used in power system analysis. So you need to select a software which has the capability to perform all these studies. Otherwise, what you'll have to do, for one type of study you will require one software, for the other type of study you will require other software. So it will become difficult for the power system analyst as well to use several softwares or several studies. So if we have a software which can perform all these studies by inputting only one kind of data, then it is good for us. So further moving on, advanced features to link together with a suite of multiple discipline suite of other software. So now, if you have performed study in one software, maybe some other utility or some other company may not be using some other kind of software. So you should be able to transform your data from one software to another software. So if your software has the capability of this, it means it is a good software. Secondly, you may have data from the SCADA system. The SCADA system is this supervisory control and data acquisition system where you have an industrial facility and some data is being logged on into your SCADA system. So what you want to do is you want to take the data from data points from your SCADA and input it into your software. So your software should have the capability to interact with your SCADA system or any other kind of system. Should take care of all calculation, track revisions and alert our users to changes in other designs that could affect our work, such as motor sizes. So for instance, you planned a network, then you designed a network, now you are operating the network. So you can see that now you will have three kind of revisions. At the planning stage, you planned your network with certain kind of equipment. But at the design stage, you came to know that the planned equipment is not enough. You need to make some changes. Similarly, at the operational stage, you came to know that, okay, fine, we were going for this kind of equipment, but that equipment got damaged and we had to replace it. So a software should keep track of such changes, that whether the system you are performing your studies on, is it in the planning stage, is it in the design stage, or is it in the your operating stage, or if there are some changes in your operational system. So what are these kind of changes? So some commonly used software for this power system analysis are ETAP, SIME, EDSA, SKM Power, PSSC or Dixieland. Welcome to Power System Analysis using ETAP course. In this lecture, we are going to provide you with the overview of the power system. So a typical power system starts from the generation plant, and then whatever the generation is generated at the generation voltage is stepped up with the help of a step-up transformer and transmitted through transmission lines. So after the transmission line, you will have a distribution side or the load side where you will have a distribution transformer, which is again going to step down these transmission voltages back into distribution voltages or consumer voltages, and then the load which is generated by the power plant is going to be consumed by different kind of loads. So at the when we talk about this industrial network can either be connected to directly to the high voltage transmission system or the distribution system, depending upon the type of industry we are talking about. If it is a big industry, then surely it may be connected directly to the EHV transmission system. But if it is a small industry, it can be connected to a distribution system as well. So in ETAP, what we are interested in is we are not interested in developing this whole power system, starting from generation to transmission all the way to distribution. We are only interested in the industrial network, which is either at the distribution side or either at the transmission side. So what we do is, if we go into the details of the industrial system, we'll see that we develop a grid here. This grid represents the entire transmission system of the network. So whatever is the short circuit level available here, the equivalent impedance of the whole system at this point or at this point, this is calculated and modeled here. And from this point onwards, this is our internal industrial network. So it will have some kind of a transformer which is going to reduce our voltages from distribution voltages to consumer voltages, or from transmission voltages to industrial network voltages. So with this transformer, the voltages are stepped down, and then we have this local bus, and this can be connected to, if you have some kind of a big industry, then surely it can have some kind of internal generation or cogeneration. So if some cogeneration is available, this is modeled here. If you do not have cogeneration, then you have some feeders or these cables which will be feeding your internal industrial load. Usually industrial load can be in the form of your static load, which is your lightning load or your power electronics load, or it can be in the form of large motors or pumps. So whatever the kind of motors or pumps you have in your system, you are going to model everything in detail, and then we are going to perform the load flow analysis, short circuit analysis and motor starting analysis in order to figure out what is going to happen in our internal industrial system when we have a change in voltages, or we try to start a motor, or for the different configuration. So how my industrial network is going to respond. For instance, one of the example here is, let's suppose this grid is tripped, or the incoming from the industrial side, from the utility side is tripped. So in this case, what will happen? We may have to switch on our internal generation. So in this case, we will have to see what is going to be the impact if my utility side is tripped. Will my generator will be able to feed this load, or do I need to switch off some load in order to maintain so that I can maintain the load of this industrial network with the help of this generation? So these are the kind of questions we need to ask, and this is a typical industrial network which we will be modeling in ETAP. Welcome to Power System Analysis using ETAP course. In this lecture, we are going to give an overview of ETAP. So what is ETAP? ETAP stands for Electrical Transient Analyzer Program. So ETAP is a most comprehensive and integrated suite of power system enterprise solution that spans from modeling to operation. So it has lots of things you can do with it. The most common, the system studies you can do protection coordination studies, you can even get the data or adjust the data with the real time. Similarly, you can perform control system studies in it, even grounding type of studies. So it has a huge variation. So you can do a lot of things. But the most common thing we usually do with the ETAP is the network analysis. And what do we mean by network analysis? By network analysis, we mean we can perform load flow analysis in this, we can perform short circuit analysis, we can figure out what will be the most optimum locations for the capacitors. Similarly, unbalanced load flow analysis we can perform with this, transient analysis, motor starting. So anything which is related to network analysis, different kind of studies which we have to perform, we can perform with the help of ETAP. So when you will see that when you open your ETAP for the first time and you try to open a case and you try to create a new case, ETAP asks for the user management. This user management is very important for ETAP. So usually what we will do, we will either use this project editor or base editor. So this project editor and base editor or the revision editor, what they can do is the project editor can create a new project. It can change the project. In short, it can perform anything that is available in ETAP. So it has the full capability. It can do anything. Whereas the base editor cannot create a new project, but it can play with the base data and revision and so on. So while performing with studying ETAP or making new project with ETAP, make sure that you select the right choice. And usually if you want full access, project editor is the best choice to be selected. This is the main window. This is how the main window of an ETAP looks like. So what it has this whole view. So this is the project view where you will have the different scenarios, different case studies which you are performing in your system. Everything related to the case study will be available here. Then you have this system toolbar where you can select different kind of studies. So what you want to do, it is available here, and this is the one-line diagram where you will create your network and get the results out of it. Here is the edit toolbar. This edit toolbar will work whenever you are in the editing mode. So in editing mode, it provides you with different components which are available in ETAP. So if you want to create a new generator, if you want to model a new transformer, you want to model a new transmission line or a cable, so you will select the values from here. Similarly, this is the mode, which type of study you want to perform. So if you see this pencil kind of a thing, this means that you are in basically editing mode. So you can create new things. You can edit the data of the different models, transmission lines, different equipment, circuit breaker and everything. And here, this is balanced load flow. So when you have to perform load flow analysis, we will be selecting this. This is balanced load flow. If you want to perform unbalanced load flow where all the three phases are not same, then you can use this option. Then this is short circuit analysis, then motor starting analysis, transient stability analysis. So in short, whatever kind of analysis you want to perform, you will select. Different kind of network analysis are available here. You will select the analysis you want to perform, and then you will perform in PSSC. And for each of them, you will have different kind of, for instance, when this edit mode is open, you will see that edit toolbar is available here. But when you select different modes, load flow, balanced load flow mode or unbalanced load flow mode or DC load flow or different things, then you will have different. So each of them will have its own toolbar, and each toolbar will have different kind of tools available on it, which can be used to perform a certain or review the results of a certain kind of analysis. For instance, if we look at the balanced load flow toolbar, what you are going to see, this is for the run calculation. This, if you select this option, you're going to perform load flow analysis. If you want to see the results of this, then you can use this option. Similarly, if there are any alerts in the system, so what are the alerts in the system? That whether your voltages are below some criteria, you must have provided some criteria. So if the voltages are below some limit, you can use from here. Similarly, if you want to generate reports, you can select this stop calculation or different values. You can, whatever you want to select from here, so you can select from this toolbar. And the one important thing about how the data is saved in ETAP. So basically ETAP has a three-dimensional database. What do we mean by a three-dimensional database? You know that when you are performing your studies, you will have with respect to display, you can have a different type of displays. You have this impedance display where you are this one line diagram is displaying all the impedance values in the system. Then you may have relays in your system, then you can have a certain display with this. So with the respect to presentation, what you are showing on your display. So one type of database will have all the data related to different displays. Then network configurations. So what kind of configurations you have? For instance, during the planning stage, you want all the equipment to be in service. But during the operational stage, some of this equipment may be out of service, because during peak condition or maximum load condition, you may have different configuration of load. But during off-peak condition or low load condition, maybe all the motors are not running. So different kind of conditions available. The status of each equipment can be stored. So one database is in the form of this. And the third is the revision. So in the planning stage, you may have some data, but as you move on, that okay, fine, at the planning stage, I just considered this MVA capacity, but in reality, when I was designing, I came to know that this planned capacity is not enough. I need to change this capacity. And at the operational stage, you came to know that when the equipment, certain equipment is procured, I assumed these values for the transformer or for the transmission line, but in reality, these values are different from the original values. So there you can select different. So this is how the data is maintained. So you can select any display, any status, any property, and you can perform the load or any analysis based on this. So this is how ETAP works with the database. Welcome to Power System Analysis using ETAP course. So in this lecture, we are going to demonstrate how ETAP is and what are the basic functions and the overview of the ETAP. So if you will open ETAP by double clicking on it, so you are going to open up with this window. So this is your working space where different kind of files are going to be open for you. This is your toolbars where it will show the system manager, the one-line diagrams, the different kind of features you have in PSSC. These are going to be shown here. The message window is going to show the different kind of messages that will be appearing with PSSC, and these are the toolbars which will be containing different data. So if you want to open a case, so opening a case is very simple. You can simply go to File and Open Project. If you have already some existing project open in your system, you can open from here, or simply you can go to this on the toolbar, Open, and when you will open, it is going to ask you where your file is available. So you can select different options from here, or you can browse to the location where the file is. So I have created one test case just for the sake of telling you what is happening when you open a case. So I'll just double click on my case. Basically the file to know is that ETAP file is saved in the form of static.oti. So OTI is the extension of the file. So you can just double click by opening it. And see, it is going to ask for authentication. Yes, I want ETAP authentication, and my username is there, and I already have the license from here. And when I press OK, so here the access level, I want to access my project as a project editor, so that I have the full control over the case. And I press OK. It will take some time. It is loading the database of the project. And there you go. So now you have different things open. So if you see this pencil, this is by this we mean that we are in an edit mode. So I can change different options here, and it's just a simple case. If you see here on the top, so just we can go here by scrolling. You can go up and down. So scrolling, I have this for grid. I have modeled two grids here. The one is the maximum short circuit level, and one is for the minimum short circuit level. And for one study, we are going to use maximum, and depends. And we will be discussing this more in the future. And similarly, it has two transformers here, and a certain load is connected to the feeder. One is connected to the feeder, and one is directly connected as a impedance. So in the form of RX and B, I have provided the value here. Here, it has been modeled as a cable. So some load is there, and you see, and there you have these different options. This is all your project manager, which has different kind of files which you have here. It will be coming here. Similarly, if you, this is our edit mode where you have different kind of equipments available. Whatever equipment you want to select in your case, it will be available here. And now if I want to perform some analysis, what I have to do is I have to switch from my edit mode to my study mode. So what kind of study I am doing, it will depend, the selection will be based on this. For instance, if I want to perform a load flow analysis. For the load flow analysis, I can select this peak, balanced load flow analysis. When I click on this, now if you see, this toolbar has changed. Now my toolbar is showing me in the form of this. So I can perform the load flow analysis from here. Similarly, auto run, if I want to do it automatically, I can do it from here. Similarly, if there are some alerts in my case, this will be shown here. From the alerts, I mean that if my voltages are within some limit or not, it is going to come here. And the messages had been updated. See here, the case has been opened, successful backup has been completed. So things like that, it will come here. So this is how you open the case, and you can perform if you want to check the data of something, or if you want to manipulate the data. What you simply have to do is you have to double click on the equipment, and the window for that particular will open. If you see here, the ID is transformer T1. If I go to the rating, the voltage rating is, this is 132 by 13.8 kV transformer, which has a capacity of it's a huge capacity here, 67 MVA capacity is there. So I am giving it in the form of MVA. So you can select from here, and then what is the derated capacity, different things you have here. Then the impedance values. If you do not know the impedance value, you can simply use these typical values. So typical values will provide you with, okay, whatever the impedance value is going to be there for a certain type of transformer. And if you want to consider some tolerance, so you can select the tolerance level from here. What will happen in the case of tolerance level, that it will consider this tolerance while performing the analysis. And this is important. Why? Because if you do not know the data, then you want to go with the worst case scenario. So the worst case scenario is, for the load flow analysis, worst case scenario is more impedance, because higher the impedance is, the more will be the voltage drop. And for the short circuit level, it will be reversed. So the lower the impedance is, the more will be the short circuit current. So this way you select this tolerance, and this ETAP take cares of this. And similarly, the other tabs are there. If you want to change the tap positions, the tap positions can be changed from here. Regarding grounding, what kind of grounding is there, you can mention the grounding here. The sizing of the transformer and everything is available here. So when you move forward with your case, you can select these values accordingly. And if you press OK, that's it. If I see my grid, so my grid is here, everything related to the grid is here, and this is how you perform. So this is the basics of ETAP. So this is how your ETAPs look like. Welcome to Power System Analysis using ETAP course. Now that we know the overview of our industrial network, so what are the different components which comprises or which creates an industrial network, now it is time to know the system modeling. So how do we need to model each of those equipment using ETAP? So before going into the some details of this, first of all, we need to understand what is system modeling and why is system modeling required. System modeling is required because each component or a group of component of an industrial or a commercial system be represented so that an analysis of the system performed can be made. Because the transformer in basic electrical engineering, you have to use these basic electrical engineering formulas. So in order to create this solve this network, what you need is some mathematical equations, so that which can be solved with the help of electrical engineering equations. For instance, if I can represent my transformer in the form of resistance and reactance or impedance, then what I can do, I can calculate the value of current simply by making using the Ohm's law equation, which is equal to V is equal to IR, or I is equal to V by R or V by Z. Similarly, power passing through any transmission line can be found with the help of P is equal to VI, because now I know the current flowing through the transmission line, I know the voltage of the transmission line, now I can calculate the power flowing through the transmission line. So for this reason, it is very important to represent each of these equipment in the form of some mathematical form. Secondly, which of the several possible representations or models of the system is well suited to meet the objectives of a given study. So now you need to make some choices that what kind of study you are performing, and for a particular kind of study, what kind of models are required. For instance, if you are performing simple load flow analysis, for the load flow analysis, you are not interested in the dynamics of the motor. So now what you can do is, instead of going into the detailed modeling of an induction motor or a synchronous motor, what you can do is simply model the megawatt and megavar value, active power and reactive power values of these motors. Because in load flow analysis, you only need to know, okay, what is the active and reactive power of a load. So by doing this, you will get your results for the load flow analysis. But if you are performing this motor starting analysis, now this model will not work for this, because there you need to know the dynamics of the motor. With the changing voltages or the changing current, how your motor is going to respond. So this way you need to know what kind of representation is okay for a certain kind of a study. Thirdly, what mathematical expressions will describe the characteristic of each element so that it can be quantified and programmed for computer input. So you need to know, okay, for each kind of study, what kind of mathematical expression is enough. So do I need to go for what kind of analysis? For this analysis, what equation can be used to convert my physical quantity into an electrical quantity or a mathematical quantity? So before going into the system modeling, we need to review the basics. So we have two type of components in our system. One is the passive elements, one is the active elements. So passive elements are those elements whose values or the quantity does not vary with respect to time or with respect to other things. It's not time varying. So some of the basic passive quantities in a power system are the transmission lines, transformers, reactors, capacitors. So these are kind of basically all those components which have R, L and C, the resistance, inductance or reactance or capacitance in your system. So an equipment which has, so these are the kind of equipment which have resistance, inductance and capacitance in your system. And in an AC system, with the changing sinusoidal wave, the equation of these becomes, for instance, if you want to know the current flowing through the resistance, you can simply use V is equal to IR or I is equal to V by R. Similarly, your inductance, it can be converted into reactance. So for converting your inductance into reactance, what you simply have to do, you have to calculate XL. And what is XL equal to? XL is equal to 2 pi FL. So what is the 2 pi FL? So F will be your system frequency, at whatever frequency you are trying to calculate this network. For instance, in India, the frequency is 50 Hertz. So here F we will be using as 50. But in another country, for USA, where the frequency is 60 Hertz, there the value of F will be 60 Hertz. Similarly, and then with the help of this, you can find your current and voltages. Also, you need to be able to convert your different values. For instance, resistance has a reciprocal known as conductance. And so what is conductance? Conductance is the reciprocal of resistance. Similarly, inductive susceptance or B is the reciprocal of inductive reactance. Similarly, capacitive susceptance will be the reciprocal of capacitive reactance. Similarly, impedance is given by R plus JX. Basically, it is the combination of resistance and reactance. Similarly, admittance. Admittance is basically reciprocal of impedance. So how do you represent admittance? Admittance is represented by Y, and Y is equal to 1 divided by Z. And what it is? It will be the combination of this conductance plus your susceptance. Then active elements. The active elements of a power system comprises of motors, generators, synchronous condensers or loads such as furnace, adjustable speed drives. So why are these active elements? Because one or more of the parameters of the active element will vary as a function of time, phase angle, frequency, speed. So if these quantities change in the system, your output or your response of these equipment, your active elements will change. Now the four expressions for power quantities given in the table below can be used to model nonlinear quantities. So now for these kind of quantities, what do we want to know? We want to know what is the active power, what is the reactive power, what is the complex power or the apparent power, and what is the power factor. So if we know these quantities, any two of these quantities, we can calculate the remaining quantities. So just to go through it, complex power or apparent power is given by VA or kVA or MVA depending upon the type you have and how much big or small this power is, and it is defined by S is equal to P plus JQ, where P is the active part or the real part and Q is the imaginary part. P part is related to the resistance and Q part is related to reactance in the system. Similarly, active power is given by P and its units in watt, kilowatt or megawatt, and this is equal to, by the simple Pythagoras theorem, P is equal to under root of S square minus Q square. Similarly, reactive power is given by vars. It can be kilowars or megawars depending upon the unit you are using, and similarly it can be defined by this expression, and at the end power flow is given by PF, and what it is basically the ratio between your active power and your apparent power. So now let's discuss transmission line modeling. So when you are trying to model a transmission line, 4 parameters are there which affect the performance of the transmission lines. These 4 parameters are the series resistance, series inductance, shunt capacitance and shunt conductance. So how does they come into play? Let us take the example. If you ever see a transmission line or a distribution feeder, what you see? You see 3 phases. And when you see 3 phases, so basically what is happening on a pole or on a tower, you will see 3 phases or the 3 conductors going on. So when we talk about a conductor or so what will this conductor have? So this conductor is basically a wire, or any conductor or the wire, what does it has? It has some kind of resistance in it. So this gives rise to series resistance. So all along the line some resistance is going to be there. Similarly, when the current is going to flow through this conductor, a magnetic field is going to be created around it. So because of this magnetic field, we are going to have some inductance in the transmission line. So these are basically the series component which are distributed all along the line. But on the other hand, you may have 2 different things as well. What are these things? The shunt capacitance. So how do we represent shunt capacitance, or what is this capacitance? So you see, you have one conductor, you have other conductor and air in between. So what does this make? One plate, second plate and an insulation in between, which is air in this case, and this gives rise to your capacitance or a capacitor. So basically a capacitive effect is going to be there in your system. So due to this capacitive effect, you are going to have this capacitance within your system. It can be within the 2 transmission lines or from the transmission line to the ground. So due to this, we have this shunt component which in the system, which will be known as capacitance. So these parameters affect both overhead lines and cables, and the same calculation procedures are used to determine the parameter values in each case. So because irrespective of if the conductor is on a tower or it is in the form of a cable, the calculation method is going to remain the same. The only difference will come, what will be the amount of values there. So for instance, if we talk about cable, what will happen in cable? So 2 cables or the 2 conductors of the cable or the 2 phases of the cable are in close proximity as compared to the overhead transmission line. So what will happen? So you have one conductor, you have another conductor, and instead of air, now you have a better insulation which is replaced by rubber or some other good insulator which is insulating the cable. So now the capacitance value in this cable will increase, and due to this increase in capacitance, you are going to have more shunt capacitance in cable as compared to transmission line. So for this reason, it is common to use the word line to represent both overhead lines and cable. So when we say commonly line, it can be either transmission line or it can be a cable, because both have the same kind of quantity. Please note that certain assumptions that are valid for widely spaced conductors used in overhead lines may not be valid for much closer conductor arrangement found in cables. And one of the best example of this is the capacitance, because for the overhead transmission line, capacitance may not be that much high. But in the case of a cable, this capacitance is going to play a very major role. So now, how do we mathematically model a transmission line from the physical structure? So we usually model the transmission line in the form of a pi model. So if you see a pi model, what we are doing is, on one side you have this generation, on the other side you have load, and the transmission line is connecting your generation with the load. And how we are modeling it? If you see, this is kind of a pi network. So what does this pi represent? This pi represent all the distributed R and X value in the conductor. This is represented by here, lumped R and X. Similarly, all this value of capacitance in the system, which is the shunt capacitance, it is represented on either side of the transmission line. So C by 2, half C by 2 is here, and half C by 2 is on this side. But if you see this difference between the cable and the transmission line for different two values, this is just for your comparison. If you see for 13.8 kV overhead transmission line and cable, the resistance may remain the same. Inductive value, yeah, it is going to vary a little bit, but the capacitance value is going to have a bigger change. So if you see here, so you will see that the capacitance value is for 13.8, and the cable and the overhead transmission line, you see that huge change in your capacitance value. Why? Because I already told you the reason. Because in a transmission line, your insulator is air, but in cable you have a good insulator, and the cables are in more close proximity as compared to the overhead transmission line. So you see the change there. This is a typical construction of an overhead transmission line. So as I said, with the help of this physical parameters, if you know the physical parameters of your transmission line, with the help of this you can calculate these passive elements of the transmission line, which are these R, X and B. So in ETAP you have this capability available. Either you can give the values, passive values directly, that is R, X and B values directly into the ETAP software, or what you can do is you give the physical parameters, of your tower, the physical parameters of your conductors, your ground wire, and once you give all this value, ETAP automatically is going to calculate R, X and B value out of this. So it totally depends on you, what do you want to do here. In this lecture, we are going to continue with the system modeling. Now the next big asset in the system is this transformers. So transformers you can have two types. One is the 2-winding transformer and one is the 3-winding transformer. First of all, let us discuss 2-winding transformer modeling. A typical transformer has 2 windings. One is the primary winding and the other one is the secondary winding. So if we want to model any transformer mathematically, what we first do is create the transformer from its physical structure into an equivalent circuit. So the equivalent circuit of a 2-winding transformer is like this. Here you have this primary winding, and then here G0 represents the iron losses of the transformer, whereas Bm represents the magnetization current at no load. Then there is this winding, which is a transformation ratio, and then this is the secondary resistance and impedance. EP is the primary voltages, whereas ES is the secondary voltages. Whether the transformer is going to be step up or step down will depend upon this value. So what we can do, we can represent this secondary side resistance on the primary side of the system simply by dividing it by its ratio, this transformation ratio. So now the same equivalent circuit is going to become like this. So here we have divided it by the transformation ratio, and here we have. Now if you see, it is a series parallel circuit. RP and RS are in series with each other. Similarly, XP and XS by N square are in series with each other. So we can represent this equivalent circuit as RT, which will be the total resistance, XT, which will be the total reactance, and this is where RT will be equal to RP plus RS. Similarly, XT will be equal to this. And in normal, what we do, we usually do not consider these because these values are very small, so we can neglect the value of conductance and the magnetization current, the no load magnetization current and these conduction losses. So if we neglect these iron losses and the magnetization current, then what we will get simply RT plus XT. So what do we need from a transformer? We only need the values of resistance and reactance. The R value will provide us with the transformer losses, where XT will provide us with the transformer reactive losses. So in usually when you will see that in a nameplate rating of the transformer, usually this only impedance is provided. So whenever the impedance is provided, you can estimate the value of R from this value with the help of this IEEE standard C37.10-192792, and the value for XT calculated from here is X is equal to Z square minus R square under the root. Similar Pythagoras theorem, because basically what is Z? Z is your total impedance, which is the combination of your R part and the X part. But in order to calculate this R part or X part, you will be needing X by R ratio or R by X ratio. So typically in a transformer, you will find these values given. So if these values are given, X by R values are given, with the help of these X by R values, you can calculate the, if you have Z value available and X by R available, then you can separately calculate R and X. So here theta will be equal to tangent inverse of X by R, and X will be equal to sine theta into Z, and where R will be equal to X divided by X by R. So using these formula, you can individually calculate the value of R and X if you have value of Z and X by R available with you. So when we look at a 3-winding transformer, what do we mean by a 3-winding transformer? Instead of 2 winding, this transformer is going to have 3 windings. And how we are going to name those 3 windings? If we look at this equivalent circuit here, you see this first winding can be known as winding 1 or high voltage, whereas the second winding can be known as winding 2 or LV voltage, whereas winding 3 can be known as tertiary voltage or winding 3. So, and similarly here R0 and X0 are the losses within the transformer. In 2-winding transformer, the MVA rating of the 2 windings is same. That is, whatever is the MVA rating on the primary side, the same will be on the secondary side. Whereas in the 3-winding transformer, all the 3 windings may have different MVA ratings. So usually what happens is that you will be given the value of this Z1, Z2 and Z3 in the form of per unit. So if you have this per unit and on their own MVA rating, the MVA rating of this winding, MVA rating of this winding and MVA rating of this winding. If such is the case, then how can you calculate? So you can calculate the impedances like this. So Z1 to 2 from HV side to LV side, it will be equal to Z1 plus Z2, which means the impedance of Z1 plus the impedance of Z2. If you will add them, you are going to get the impedance from Z1 to Z2. Similarly, from 1 to 3, you have to add this impedance, winding 1 impedance with the winding 3 impedance. For Z2, 3, you have to add these two. So this is how you get the values. And similarly, reverse. If you are provided with the values of Z12, Z13 and Z23. Here Z12 can also be known as ZHL or HV2LV. Z13 will be HV2TV or the tertiary voltage, and Z23 will be equal to LV2 tertiary voltage. So if you are given these values, you can convert them into Z1, Z2 and Z3 simply by using this formula. Z1 will be equal to Z12 plus Z13 minus Z23 divided by 2. So if you see what basically we are trying to do for Z1, we are trying to add both the impedances of Z1 and subtracting the impedance of Z23, which does not include the part of Z1, and simply dividing it by 2 because we are adding it together. So it will be 2 times because here Z1 is 1 time here, 1 time here, so it will be 2 times. So when you divide it by 2, you are going to have Z1. So this way you can calculate the transformer impedances. In this lecture, we are going to continue with system modeling, and now we will discuss generator modeling. So in order to model a generator, if you see, a generator can be simply represented by the resistance of the generator, the reactance of the generator, and that's it. So if you at least have these two values, you can model your generator. But for a generator, these reactance values, they vary with respect to time. So if you see, if whenever there is a short circuit fault on a generator side or in the system, your generator goes through some transformation. Usually for the first few cycles, your reactance is restricted by or limited by subtransient period. So this subtransient period is known as the reactance within this period will be known as subtransient reactance. Similarly, after few cycles, the fault current is reduced and then it enters into a transient period. And during this period, the short circuit is limited by transient reactance, and ultimately after many cycles or many seconds, the generator reaches its steady state period, and during this steady state period, the reactance is known as the steady state reactance or synchronous reactance. So whenever you have to model a generator, you need to know all these three reactances. For the steady state analysis or the load flow analysis, we only require synchronous reactance or the direct access reactance. But if you are performing short circuit analysis, we will be usually considering subtransient reactance, because during the subtransient reactance, the reactance is the lowest and the short circuit current during this period will be highest. So usually in simulation softwares like ETAP, data for the generator is input on its own base. Therefore, no conversion is required. So a good thing regarding the generator data in ETAP is whatever data you have from the nameplate rating, you can simply take this data and put it in your ETAP model, and that's it. Furthermore, once you have given these reactances, the additional data you will require in the ETAP or any other software for solving the case is the Pmax and the Pmin. So what is the range in which the generator can change its output? So you need to provide the two extremes of your generator. Similarly, we need the voltage source here. So for the voltage source, what we need to inform to the software is that what is my capability limit, generator reactive capability limit, because reactive power is directly proportional to the voltage. When we change the voltage, what we are basically trying to do is we are trying to change the reactive power of the generator. So we need to provide the generator with these values. What will be the value of Qmax and what will be the value of Qmin. So that our generator can change its voltage. When we ask generator to change its voltage, it will see that whether I am within this range. If it is within this range, and it is going to change the voltage within this range. And this is given by in the form of this generator capability curve. If you see here is a typical generator data model. If you see in this model, here you have this subtransient reactance, you have this transient reactance, you have this synchronous or direct access reactance. So for the load flow analysis, you can take this direct access reactance, whereas for the short circuit analysis or transient stability analysis, we will be requiring both the subtransient reactance and the transient reactance along with these time constants. And the additional data here available is what is the voltage of the transformer, what is the MVA or the kVA rating of the transformer. Similarly, here is a typical reactive capability curve. So what is this reactive capability curve telling us? That for what amount of active power, for a certain amount of active power, what is the reactive power that can be provided by this generator. So this point represents Qmax, and this point represents Qmin. So if we see here, if I operate my generator at somewhere here, then at this point my Qmax will be equal to this much and my Qmin will be equal to this much. And we have to make sure that when we are providing the active and reactive power to the generator, we are not exceeding its limits. Because what is happening in a generator? If you see a generator in a physical configuration, what are you going to have? You are going to have some stator, Within this stator, there is going to be a rotor, and on rotor, some field winding is going to be there. And this field winding is going to be energized with the help of some shunt generator, which is going to provide the DC current to this winding. And when this DC current is provided, a magnetic field is created. Then this rotor is rotated with the help of a prime mover, and the magnetic field generated by this rotor is induced into the armature or the stator, and then a stator current, you get some stator current from this, which is known as the output of the generator. So by controlling this field current, this DC field current, you can change the value of this reactive power, because what you are trying to do is you're trying to change the flux in the system, flux in the generator. So but how much maximum current you can provide? You can provide the current up to the value where you do not get rotor winding limit. So because when you increase current into your conductor, what will happen? A heat is going to be generated due to resistance within the conductor. So how much you can go? So this is providing the value. This is the maximum limit till where you can go in the overexcited range. The positive range of the reactive power is also known as the overexcited range, whereas the negative range of the reactive power provided by the generator is also known as the underexcited range. But what happens in the underexcited range? In the underexcited range, what you will be doing is you will be reducing your DC current. So when you are reducing your DC current, what you are trying to do is you are trying to reduce your flux. So you can reduce your flux, reduce. You can reduce it up to a certain value, because if you will make it 0, loss of excitation will happen. So you need to know what is but if you will, the flux will be weak. It means that the induction in the stator side of the generator will also be weak, and it may cause the heating of the stator. So that is why you have some limit here. So for the overexcited range, what is happening? You are providing in overexcited range, you will be providing the megawatt to the system, whereas in underexcited range, you will be absorbing reactive power from the system. Now, once we have discussed generator, the other side of the industrial system or power system is the load. So load, there are several ways to define your load or model your load. But some of the common ways to model the load are the constant power load, constant impedance load, or the constant current load. Or your load can be a combination of all these three. So what do we mean by a constant current load? Constant current load is going to be a load in which the current of the load will remain constant irrespective of the change in voltages. Similarly, in the constant power load, the power of your load is going to remain same with respect to the change in the current and the voltage. And whereas in constant impedance load, your impedance of the load is going to remain same with the changing current and load. So what are the examples of a constant power load? Your typical induction motor load is an example of a constant power load. What happens in an induction generator? When you have an induction generator, when the voltages will decrease, the motor will increase its current so that it can maintain the same MVA rating or the rating of the induction generator. So P is equal to VI. In order to maintain P, it will, if the V is reduced, the I has to increase. And the example of a constant impedance load is your lighting load. If you see your typical light bulb which has a tungsten filament in it, what happens when you have a reduction in voltages? Your light bulb becomes dim. So what is basically happening there is that when the voltages has reduced, the current is trying to reduce so that the value of Z is going to remain the same. And an example of a constant current load is a battery, your typical battery, because irrespective of the voltages what you are providing to the battery, irrespective of the power what you are providing to the battery, the current, the charging current of the battery should remain same. So when you are modeling the load, you need to know what kind of load you have. Do you have a lightning load? So if you have a lightning load, you can model it as a constant impedance load. If you have a typical induction motor load or a motor load, large motor load in your system, or all the type of load in your system is a motor load, then you can model it with the help of a constant power load. If you have a battery or a electronics kind of a circuitry in your system which takes constant current, so you can model it as a constant current load. So, or it can be a combination of all these three, because sometimes you are not able to figure out what is the composition of each kind of load. So in such cases, you provide a lump load, which is the combination of all these. Welcome to power system analysis using ETAP. In this lecture, we are going to discuss per unit system in power system analysis. So, why do we need a per unit system? So, per unit system provides you with an advantage that if you have different kind of values in your system, for instance, take a generator. Different generators in your system will have different MVA rating. For instance, one generator in your system will be a big generator. It may be 100 MVA generator or a 50 MVA generator, whereas other generator will be a small digiset, will be only 2.5 MVA or 3 MVA generator. So with these different type of values used in the generator, these per unit values typically lie in the same range. So what is the advantage of this? Although the ohmic value will be different, but when you convert these ohmic values into your per unit values, they usually lie in a narrow range. So what is the advantage of this? The advantage is that if you do not know the actual ohmic values or the impedance of the generator, what you can do is you can usually use this per unit impedance to a reasonably well value. How you can do this? For instance, if the per unit value of a 100 MVA generator is, let's say, 0.2 per unit, and that of a 90 MVA generator is 0.21 per unit. So you will know that, okay, fine, for this change, the value remains between 0.22. So for this generator around 100 MVA to 120 MVA or 150 MVA, the value is around 0.1, 0.2 to 0.21. So if you have a new generator for which you do not know the value, you can simply use either 0.2 or 0.21, which will be close to these values. So this is one of the reason. And the second reason is one of the biggest asset in your system is the transformers. You will find transformer everywhere. So you have distribution transformer, then you want to transform your voltages. Similarly, you will going to have a step-up transformer if you have a generation in your industrial network. So due to these transformers, now what the problem will happen? So this transformer has impedance. If you see the impedance of the transformer from the HV side, it is going to be something different. But if you will see the same impedance from the LV side, it is going to be different. So it will become very difficult if you are performing the calculation and if you have to see this calculation everywhere. So just to give you an example, if you see here, if we have a 2000 VA or 2 kVA transformer whose impedance is 4 ohms from the LV side. So if you see from here, I can see the transformer impedance of 4 ohms. But what about the transformer impedance from here? So just to give you the calculation, it is 16 ohms from here. So how you will perform the calculation? If you are performing the calculation with respect to LV side, you have to consider 4 ohm. But if you are performing the calculation with respect to HV side, you have to consider 16 ohm. So now these things become difficult. It becomes difficult for you to keep track of all these impedances with respect to LV side and with respect to HV side. So what is the solution? The solution is this per unit system. So with the help of this per unit system, for the impedance once expressed in proper base remains same, either reoffering from the HV side or the LV side. So now after converting, once you convert your transformer impedance into per unit, irrespective you are considering from LV side or HV side, it is going to remain the same. And at the end of the lecture, we are going to see practically that whether this happens or not. So now per unit system, a key problem in analyzing power system is a large number of transformers. It will be difficult to continually have impedance on different sides of the transformers. The problem is avoided by normalization of all variables. This normalization is known as per unit analysis. And how do you perform this per unit analysis? For the per unit analysis, you simply consider one benchmark value or base value and divide your actual value by this base value. And whatever you get, that is known as per unit quantity. So the four basic quantities in power system are the current, voltage, power and impedance. So this is basically the whole electrical engineering, the whole power system analysis, because somewhere you will be knowing P, you want to figure out V and I and Z. Similarly, if you have Z and V available, you will be trying to figure out I. So if you have at least two of these quantities available with you, you can find the remaining two quantities. So these are the basic quantities in the power system. So what we can do is we can consider some base quantities for these four basic quantities and then calculate the per unit system. So all other quantities can be derived from these quantities. Similarly, if the value of any of the above two quantities is known, we can derive the remaining two quantities. Base impedance and base current can be computed directly from the three-phase value of base kilovolt and base kilovolt ampere. Why? Because in your system, the most common thing you know in your system is the nameplate MVA rating of a certain equipment. For instance, if you have a transformer, for the transformer, you know this transformer is a 160 MVA transformer. This transformer is a 200 MVA transformer. This transformer is a 10 MVA transformer or 10 kVA transformer. So you know this value. And the other thing you know is what is your voltages in your system. For instance, you are talking industrial system. Maybe you have a 13.8 kV industrial system, or you have 4.16 kV industrial system, or 220 volt industrial system. So these two quantities are usually known. So if you know these two quantities, you can consider the base of these two quantities, and based on the base values of these two quantities, you can figure out the base values of current and impedance also. So how this is done? This is simply. So the base current will be simply equal to base kVA divided by under root 3 of base kV line to line. So whatever the voltages in your system is, you simply divided by under root 3, and what will be the base values you will consider for the system. Usually for system we consider 100 MVA as a base power or S base. So usually in power system analysis, the most common base used is 100 MVA. So your S base will be, if it is represented in kVA here, so kVA means 1000 kVA. So 100 MVA will be equal to 100 into 1000. That will become kVA. Similarly, base kV. So if you have a 13.8 kV industrial system, so here base kV will become 13.8. Similarly, Z base will be equal to base kVA divided by base MVA. So base kVA square divided by base MVA. So now once you have these base quantities, so you assume the base value of MVA, you assume the base value of kV. From this you calculated the base Z and you calculated base current. So now if you have these four values, now simply what you have to do is I per unit will be equal to the actual current divided by I base, Z per unit will be equal to Z actual divided by Z base, V per unit will be equal to V actual divided by V base, and S per unit will be equal to S actual by S base. Sometimes the per unit of the impedance of a current is expressed on a base other than the one selected. Therefore, to change from one per unit impedance on a given base to per unit impedance on a new base, following equation is used. Sometimes what will happen? This can happen that, for instance, you took the example of this transformer. In transformer, what was happening? So if you are seeing the transformer from LV side, so you want to know what is this same impedance from the HV side. So in such cases, what you want to do is you want to change the base. Basically, you want to change the base from LV side to HV side. So if you want to change the base, you can use this kind of formula. Or another example of this is usually in your system, your base MVA is 100 MVA. But your transformer impedance or your generator impedance may not be 100 MVA. It will be different than 100 MVA. So what you have to do is, in such cases, you have to convert your 110 MVA impedance into 100 MVA impedance. So how you can do this? You can do this with the help of this formula. Z per unit new is equal to Z per unit old into base kV old divided by base kV new square into base MVA new divided by base MVA old. And depending upon what are you trying to do, you will consider these things. For instance, if you are not changing your base MVA, then this side will cancel out. But if you are not changing your voltage, you are only changing your base MVA, then this will cancel out and you will consider this. So depending upon the situation, we are going to use this equation. For instance, in the transformer case, which we are going to discuss now, we have a 2 kVA transformer. So I just want to know what is going to be my impedance when I consider different voltages. So I am not changing my base impedance. So my base impedance is going to remain 2 kVA. So this side is going to cancel out, and I am going to left with only this equation. And if we see here, this is the same thing which I am doing. So ZHV here in this case will be Z per unit new or Z new. This will be equal to ZLV, Z old into V2 square. So your here V2 is your 0.4 square divided by V1 0.2 whole square, and when you solve this you get 16 ohms. So the same impedance which was 4 ohms based on 0.2 kV is equal to 16 ohms based on 0.4 kV. And now how per unit helps to make this common, this Z common? This is how we see. So simple comparison here. So here we have a transformer or 2 kV or 2000 VA. So let us consider the ZS base as 200 VA on the both sides, because for the primary side and the secondary side both the rating is 200 VA. So here we have 2000 VA or 2 kVA. Sorry, it's not 200, it's 2 kV or 2000 VA. So base value from LV side the base voltage is 0.2 kV, and from the HV side the base voltage is 0.4 kV. So considering whatever the voltages are on the either side, so we are considering them as the base voltage. Now the base current. So if we have this base voltage and if we have S base power, we can calculate I base and Z base. So I base will be equal to S base divided by V base. So in this case, because how we are getting this formula, you know that S is equal to VI or P is equal to VI and I will be equal to S by V. So simply using this formula, simply using P is equal to VI formula, I am calculating I base here. So if we see here S base is equal to 2000 and V base is 200. So 2000 divided by 200 is equal to 10 ampere. Similarly on this side, S base by V base. So here S base is same 2000, but V base is 400. So 2000 divided by 400 becomes 5 ampere. See how the base current is changing with respect to the different voltage level. Similarly, Z base is equal to V square divided by S base. So here 200 square divided by 2000 is equal to 20 ohm. Similarly on HV side, 2000 square, this 400 square, because here V base is 400. So 400 square divided by 2000. This is still the same, 80 ohms. Now Z per unit. What is Z per unit? Z per unit is your actual quantity. Here in this case, actual quantity is from LV side. It's 400. This 4 ohms. So 4 ohms divided by 20 is 0.2 per unit. Similarly, HV side it was 16. We calculated as 16 ohms. So 16 divided by 80, and this is going to become 0.2. So now, when you convert your transformer values into per unit, irrespective you see from the HV side or the LV side, the impedance is same. The per unit impedance is same. So this is exactly what we wanted. So this is why this per unit is important when it comes to transformers. Welcome to power system analysis using ETAP. So now in this lecture, we are going to do some hand calculation in order to figure out how this ETAP or any other software, this power system analysis software, calculates the load flow. So to demonstrate this calculation, let us assume a simple system where we have this 69 kV system which is connected to the 13.8 kV system through a transformer, and this transformer rating is 15,000 kVA or 15 kVA and has a vector group of dy. So dy means this side, HV side is delta and LV side is in Y form, and the impedance seen from the HV side is 1.49 plus J20, is it I think 1.49 plus 25.35 ohms. Similarly, then there is a cable available, and this cable is almost 1187 feet. So it's a 3-core cable with a diameter of 250 kc mil, and the values are 0.5. So the R value is 0.05 and the X value is 0.04 because it is written as J 0.04. And then you have this third bus, the C bus here, which has the base voltage of 13.8 kV. Let us assume the voltages at all the three buses are 69 kV. The voltage here is 69 kV. The voltage at VB at this bus is 13.6 with an angle of minus 1.6 degrees, whereas at VC at this bus the voltage is 13.57 kV with an angle of minus 1.82 degrees. Now for this transformer, so if you take ZAB, the impedance of this transformer, this is 1.49 plus J 25.35 at 69 kV, because this is on the HV side. But if you want to represent the same on the LV side, we already did the calculation in the previous lecture. You can see from there and calculate it. And so now this will become 0.06 plus J 1.01 ohms at 13.8 kV. Similarly, for the cable from point B to C, for the cable, the impedance is 0.05 plus J 0.04. So this is the known value. So now what we are interested in, we want to know what is the power flow from here. So what is the power flow? We want to calculate the power flow here. So how we can do this? Simple. So the current from bus A to bus B. So whatever. So now what we have done here is we have taken the same thing and represented in the form of impedance. So the transformer represented in the form of R and X. Similarly, cable represented in the form of R and X. So now what will happen from A to B? We want to find the current from point A to B. What we have to simply do, we have to VA minus VB, because the voltage difference between the two, divided by Z. So basic Ohm's law we are implementing here. So with the help of this Ohm's law, we can calculate IB. And once we calculate this IB, this becomes equal to 49.07 with the angle of minus 25.03 at 69 kV, because we are considering from this, and the impedance we have considered is the impedance of the HV side. So this is with respect to this value. So by definition, the power flow from A to B as measured at bus A. So now what will be the power flowing through this? We know I value, we know Z value, we know V value. So what we can do is we can simply calculate SAB, which will be equal to under root 3 into VA into IAB conjugate. So by calculating the value, we end up with this value 5864.4 into 25.03 kV. But this is in amplitude and angle. So let us transform this from polar coordinates into rectangular coordinates, and we end up with PAB plus QJB, which is equal to 5313.68 kilowatt plus J 2481.19 kilowatt. So this is the value we have with respect to this side. Now similarly, from the 13.8 kV side, so if we want to calculate the current from the 13.8 kV side, what we simply have to do, we can simply perform the transformation, because this transformer is a step down transformer of 69 to 13.8. So whatever the value we are seeing from the HV side, simply from the LV side, this for the same power, the value will be 245.37. So this is from the 13.8 kV side now. So by definition, so the power flow from B to A will become SBA, which will be equal to VB into IBA. So we have already calculated IBA here, and because we are reversing the direction, so instead of 245, it will be minus 245. So taking this and calculating, we end up with this. So what do you see here? From here the value is 5303, but if you see from here, the value is 5313. So what will be the losses in the system? The losses will be simply SAB plus SBA, or SAB minus SBA. So this becomes, you simply add the two, and we end up with 13.34 kilowatt losses and 182 kilowatt losses. So, and representing this whole thing in the form of impedance diagram, we end up with this, the final results. So we have this, this was 69 kV, 13.6 and 13.57, and the value calculated from A to B was equal to 5313, and from B to A it was 5303, and the losses will be value of this minus value of this, whatever was the losses in the transformer. So this is what basically ETAP is also doing, and it is doing for the whole system. We took the example of 2 buses or 3 buses, which was pretty simple, but in reality you may have several buses. So in those cases, instead of calculating like this, a impedance matrix is formed, and with the help of this impedance matrix, an iteration method is used, and with the help of the iteration method, the values are calculated for all the buses in the system, and the losses and the power flowing through each is calculated. Welcome to power system analysis using ETAP. In this demonstration lecture, we are going to show how to create a new project, a very simple project, so you can start working with ETAP. So for creating the project, you can simply go to File, New Project, and give the name of the project. So it's a demonstration project, so let us give it the name Demo. And from here, you can select the browse the path. So I'm gonna select a new path, and I have created a folder with the name of new demo project, and I'm going to give it the name demo project and save. So see, it's taken the name. So if you want to use metric system or English system, that is totally up to you. So I am here using metric system. You can select whatever you want, and when you press OK, so it is going to ask for ETAP authentication. Yes. And now I want to be the project master and the editor as well. So I'm going to press OK. And there you have it. Here we have an empty project created. So we have the project, but it does not have anything. So just let us enlarge this so that we can create a project in this. What are going to do? We are going to simply create a simple project. So let us assume that we have a 132 kV bus. So for the 132, developing a 132 kV bus, I am first of all make sure that you have edit mode selected, and from the edit mode go to this toolbar and select bus. This is for create bus, so I'm gonna click on this and come back here and click on this. So we are going to develop with the minimal because right now we haven't discussed different kinds of modeling techniques. So before this, just create a simple project. Let us create a simple project. So you can drag by simply selecting the bus and like this. So let us give double click on this to enter the values. So let the name be bus 1 for now, and it is in service. It's a 3-phase. So we are not changing anything from here right now. Then I'm gonna go to phase voltage is 100% and info load. If I go to rating, I have this. You have different tabs here, and nominal kV I'm going to select 132 because it was a 132 kV bus, and I'm gonna press OK. So see, one bus is created. Now what we can have is we can have a power grid, because as we said in ETAP, what we are going to do is we do not want to create the transmission network at the back end of the system. We are only interested in our industrial network or a commercial system which is under study. So what we are going to do is we are going to create a power grid which is going to correspond to the whole transmission system. So here click on it, and so we have here we haven't selected anything. So let us double click on this. It is 3-phase. It is going to work as a swing for us, and the short rating, we have this 132 kV rating. So the short circuit values, what do we want to give? You can select anything you want. So for now, let us select, for instance, you know that your circuit breakers ratings are usually in the form of kiloamperes. So because we do not know the short circuit level at this point, so we will be assuming the maximum short circuit of a breaker capacity. For instance, for a 132 kV system, usually 40 kiloampere or 25 kiloampere breakers are used. So let us assume a 25 kiloampere breaker with an X by R of 50. So these are my values. So for now, I'm going to keep the same and press OK. So I have my grid modeled with a 25 kiloampere short circuit current at an X by R of 15. So now let us create another bus which is going to reduce the voltages to say 69 kV. So again I go to select bus, click here, and now select this bus, and now you can drag. So here I am dragging this. Once again I will keep the name same bus, but this time voltages I'm going to select 69 and press OK. So now I have. So what do we want in between? We want a transformer in between. So you have different combinations of transformer here. For now I'm going to select a 2-winding transformer. So you simply click on it first on the one bus, and then just place your transformer anywhere. Now in order to connect it to the LV side, simply click on one and click on the bus. Here you have your transformer is modeled. So now if we want to change the values, because we do not know this is an actual transformer or not, so what we are going to do, we are going to use typical values. So let us double click on this. So let the name be transformer, standard be ANSI for now. So I'm gonna go to ratings, and what I'm going to select, let this transformer be a 20 MVA transformer. So when I select 20, you will see some of the data will be updated automatically. So the full load current with respect to 132 kV side and full load current with respect to secondary side has been calculated automatically by ETAP. And this is my Z base, and for the impedance what I'm going to do, I'm going to select typical Z and X by R. So there you go, I have this value. Do I want to consider tolerance? For now, because if you do not know the value, it is better to consider some tolerance, usually in the range of plus minus 5% or plus minus 7.5, because in industry usually plus minus 75% is used. For now I'm not using any tolerance, and this is the value, this is all the value I need for now, and I'm gonna press OK, and there you go, I have my transformer model. So now let us model some load at 69 kV. So we have different combinations of load which we can model. We can have a motor load, induction motor load, we have a synchronous motor load, we can have a lumped load, or we can have a static load. So let us go with lump load. So what is lump load? Lump load will be the combination of your steady state load plus motor load. So let us put here, simply click, and wherever you want to place it, there you go. So now let us put some data into it. So let it be lump 1. You can have whatever name you want. It's a 3-phase load, calculated values. So nameplate. So let us calculate what is going to be the number 1. So what is the combination? Constant Z means static load, constant kVA, constant power means motor load. So what kind of combination I want? So I'm going for 80-20. And what do I want? And my motor model type should be conventional. And let us assume that we have a load of 15 MVA here at a power factor of 0.9, so 90% power factor. And based on this, look, see, ETAP has automatically calculated megawatt, megavar, and ampere values for this. So if you want to have different values for your normal design, your operating, so you can select different values. For now, I'm using the same values, and you can have different values as per your requirement. So once I put this, I press OK, and that's it. Now I am all ready to solve this case. So for the solution, what we are going to do, we are going to select load flow. Without going into any detail, without going to anything, we are just simply going to prepare the load flow without anything else. So if you want to solve the load flow, what you can simply do is run load flow. When you click on run load flow, PSSC, this ETAP is going to ask you that what should be the file name. So here is my load flow. So let me call it load flow base, and I press OK. ETAP is going to solve, and there you go. So now you have these values, but let me check what these values are. So you have The voltages here are at 100% and the voltages calculated at the 69 kV bus are 96% because of this load. And when you will change the value of the load here, you are going to see your voltages are going to change. And similarly, this is the power which is injected from the grid, and this is what the power is receiving. And when you will subtract these two, you are going to get the losses which are happening in this transformer. So let me check the unit of this. So if I click on unit, see, so it's in kilowatt, kilowatt and kilowatt. If you want them in kilowatt and kilowatt, this is okay. We can even change this value, and let us select, this is watt, VA, ampere, was, watt. So you have different options available here which you can select. So this is an MVA, ampere, MVA and ampere, megawatt only, and megawatt only, megawatt and megawatt. So this way you can select different kind of options. So by toggling this value, similarly if you want to see how much voltage drop is there, so you have this option. When you click on this option, so regarding the voltage, it is telling you whether the voltage should be in percentage, kV, whatever you want. So if you want actual values, you can have actual values, but usually what we do is we use percentage values. So you can have percentage values here. So we have line and cable voltage drop, load terminal voltage drop. If I select this, because I do not have a line here, so I cannot see the voltage drop of the line. When we are going to go in detail, we are going to see this. If I want to see the alerts, I can select this alert view. If you see, no alert is there because all the voltages are within range, and we are going to discuss this later, how can we adjust this things. But this was to tell you how a basic load flow is performed. Once you are done with this, so this is how you perform your load flow. I'll close this, and in order to save this, what you have to simply do is Control S, and ETAP is going to ask you, can I save this project? Yes, I want to save this project, and you save this, and that the project is saved. Now you can close the project, and that is all. Welcome to Power System Analysis using ETAP. In this lecture, we are going to discuss load flow analysis. So what is load flow analysis and how this can be done using ETAP? So load flow analysis is used in power system operation planning and expansion studies. So what is the objective? The objective for the planning is to figure out what should be the size of each equipment. Similarly, at the design stage, we want to make sure, okay, so at the planning, we have some less details. So we are just coming up with the idea of how our industrial system should be. During the design stage, we plan those systems. Okay, fine, we need this, this and this kind of equipment, and this should be the rating of each equipment. And during system operation, we want to make sure that how my industrial facility should operate and under different conditions. And similarly, if we are planning to expand our system, we want to make sure that the existing rating of the system still holds true. So the power flow problem is the computation of voltage magnitude and phase angle at each bus in a power system under balanced three-phase condition. As a byproduct of this calculation, real and reactive power flows in equipment such as transmission lines, transformers, as well as equipment losses can be calculated. So if you remember in our previous demonstration video, when we created a simple system with a grid and a transformer in between. So what we were interested in, we wanted to know what will be the voltage drop when a certain amount of load is present in the system. So we saw that there was some voltage drop. So this was our first objective of the power flow. The second objective was, due to this much load or whatever the load is in my system, what will be the amount of losses in my transformer? So we saw that there were some losses in my transformer. So the starting point of a power flow is a single line diagram of the power system from which the input data for computer simulations can be obtained. And we saw in our demonstration video that we practically created a single line diagram of a system and used this diagram to perform the load flow analysis. Just to give you the basics once again. So for a 3-phase per unit system, this is how you provide the per unit. We have already discussed this, so I'm not going to go into details of this again. And now again, moving on, the load flow input data. What kind of data do we require? Number one, data we require is the bus data. For bus data, what is the minimum requirement? The minimum requirement is the nominal kV. What is the kV of this bus? Whether it is a 132 kV bus or a 69 kV bus, 13.8 kV bus, 11 kV bus, whatever the bus kV voltages are, the percentage voltage and angle when initial condition is set to use bus voltages. So what should be the percentage V and angle? These two values are usually calculated by ETAP, so we are not more concerned about this. So then the load diversity factor. This is required when the loading option is set to use diversity factor. For now, we are not using this option, so we did not consider this, but this is the minimum data you have to provide. For the branch data, we did not model the branch yet, but we did model the transformer. So for the branch editors like transformers, transmission line, cable, reactor, impedance editors, required data for load flow calculation, minimum data required is the Z, R and X or X by R. So we saw that when we were modeling this transformer, what did we do? We calculated, we asked ETAP to consider some typical Z value and some typical X by R value, and based on this Z value and X by R value, ETAP calculated R and X value. So for the, if you are considering and the tolerance and the temperature if applicable, so we were not considering the tolerance in that case, so we did not consider this. So cable and transmission line length and unit. So if you are considering modeling the cable and the transmission line, the important things will be the what is the length of the transmission line and the unit. So whether it is going to be in miles, whether it is going to be in kilometers. So depending, what do you require? The transformer rated kV, kVA, MVA, tap or low tap changer settings. So we were not interested in low tap changer, but we will see this in future. But the transformer rated kV, so we provided the rated kV, that was that on the HV side, the primary side, it was 132 and on the LV side it was 69. So this way you can have whatever voltages you have in the transformer, and we considered a 20 MVA transformer, so you can have different values. So then the impedance base kV and the base MVA, which was provided in our case. Then the power grid data, we use the power grid. For the power grid data, we have to define the operating mode. So we defined for this, because when we are considering a power grid, we usually consider it as a swing. So this is the type of a grid which is going to take the swing of the system. It is going to be the starting point of your system. So we consider it as a swing. So what is the nominal kV, the percentage voltage and angle for the swing mode, percentage voltage, megawatt loading if we are considering the voltage control mode, megawatt and megawatt loading if we are considering megawatt control mode, and megawatt loading and power factor if we are considering megawatt limits for power factor control. But usually when we have power grid, we consider swing, because we for load flow analysis we need to make at least one bus as a swing bus. So that swing bus is going to be our power grid data. Then if you have a synchronous generator in your database or in your case or in your system, so then you are going to define the operating mode for it, because if we have considered power grid as a swing mode, then other we are going to consider it as a voltage control or a megawatt control. Then the rated kV, similarly the voltages, the megawatt and the megawatt loading. We already discussed about the reactor capability curve, and based on this reactive capability curve, we are going to define the Qmax and Qmin values. So what is the load flow problem? The load flow problem tells us given the load and the power consumption at all bus, and for a given configuration or network topology, and the power generation for each generator, calculate the power flow through each branch. That branch can either be a transformer, or that branch can either be a transmission line or a cable. And what is going to be the magnitude at each node in the system or each voltage, each bus in the system. So why we are interested in load flow studies? We are interested because we want to determine the steady state operating conditions. We want to know what will be the voltage profile of our entire industrial facility, what are going to be the power flows in different branches of our facility, what is going to be the current flows, what is going to be the power factor, what type of load tap changer setting should I keep in order to maintain my system voltages, how much voltage drop can I expect at the end of each transmission line, because if you saw that we started from 100% at the power grid, and when at the load side we were only getting 96%, so we had almost a 4% drop in the voltages. Similarly, what is going to be the reactive power demand from the generator, because you saw that there is some megawatt or kVAr or reactive power which load is going to consume. So this is either going to come from the grid or it is going to come from the generator. So what kind of total generation and power demand is going to be there, what is going to be my steady state limits, what are going to be my megawatt and megawatt losses in the whole system or through a certain branch or a certain equipment. So it also helps, load flow also help us to evaluate the cable or the feeder capacity, the capacitor sizes, the transformer MVA rating or the turn ratios, transformer impedance and tap settings, current limiting reactor ratings, and the medium switch gear or the switch gear current rating, the generator operating modes, generator megawatt demand, the transmission, distribution and utilization kV. So we are interested in knowing, okay, if I create a certain kind of a system or a certain kind of a industrial facility, how much cable size I am going to need, how much transformer size I am going to need, what kind of generator operating mode do I need to use. For instance, if I am connected to the grid, then I am surely going to go for the droop mode. Droop mode means that I do not want my generator to continuously change its output with respect to frequency changes. But if I have a islanded system in which I am not connected to the grid, so my generator will be responsible for maintaining the load and generation balance. So this can only be done with the help of a isochronous. But if you have multiple generators, then again we are going to use droop instead of isochronous. So this way you can determine different kind of things with the help of load flow analysis. So what kind of conditions we are expecting, or what is my criteria? So my bus voltages should be within an acceptable range. Voltages should be within the rated insulation limit. Power and current flows do not exceed the maximum rating. System megawatt and megawatt losses are determined, and circulating megawatt flows are eliminated. So if you have some megawatt flows circulating in your system, you are going to check this, what are going to active losses, and with the help of this you are going to change your impedance in the system in order to make sure that you can reduce your system losses, because you want to reduce your system losses. Similarly, you want to make sure that the power flowing through the equipment is not exceeding its limit. So these kind of things you want to know with the help of load flow analysis. So how does practical load flow analysis happen? So this part is basically done by the ETAP, but we should at least know how this is done. So first of all, a matrix is going to be created. If you have a 10 bus system, then you are going to have a 10 cross 10 matrix created in your ETAP. So ETAP is going to create a Y bus matrix, and in this matrix it is going to evaluate, okay, from bus 1 to 2, what is the impedance of the network, or what is the admittance of the network. Similarly, between 1 and 3, 1 and 4, 2 and 4. So taking the whole topology of the system or your distribution system, it is going to create a Y bus matrix, and then make an initial estimate for voltages at each bus. So how it is going to do? It is going to start with your swing bus or your power grid, and starting from power grid it is going to estimate the voltages. And if you see that usually your voltages are at 100% at each bus when you start, so the initial estimate or the initial guess by your ETAP is going to be 100%. Now an iteration is going to be done. So how this iteration is iterate to find the condition that satisfies the system load flow equation. Update the voltage estimate of each bus based on estimate of voltage and power flow at every bus and values of admittance matrix. So now what is going to happen is that with the help of your V is equal to IR or all your equations or the hand calculations which we saw, this calculation is going to be performed for each and every bus by the ETAP. And once this is performed, you are going to get some new voltages, new power flows. Now what is going to ETAP do? it is going to see the difference between the calculated values and the original guess, initial guess. And it is going to check whether this is within a certain tolerance level. If it is within a certain tolerance level, it means that you have reached your calculation or your answer. But if it is more than your tolerance level, it is going to repeat the process, and it is going to continue to repeat the process until a certain set tolerance level is achieved. So this is how your load flow analysis basically performs. So the different solution engines available for the load flow analysis are Gauss-Seidel method, Newton-Raphson method, and fast decoupled Newton-Raphson method. So when selecting, before when we created the simple system, we did not consider, we used the system which was already selected by default by ETAP. But you have the choice to select what kind of system you want or what kind of solution method you want. So Gauss-Seidel method is one of the easiest type of method, or one of the basic type of method. It has low requirements on initial values but slow in speed. So if you do not even have good initial guess, it is going to solve your case, but it is going to take some time. So if you do not have, if you know that your system voltages are not going to change from your initial guess, it is going to be closer to your initial guess, or in other words, if you do not have a huge reactive power problem in your system, you can always go for, or you have a weak system where you can have huge difference in your reactive powers or voltages, or your initial guess is not going to be good, there you can use Gauss-Seidel method. So if you want to use Newton-Raphson, this is normally used in ETAP, either Newton-Raphson or fast equal Newton-Raphson method is usually used. For Newton-Raphson method, it is fast in speed but high requirement on initial values. So initial values or the initial guess should be good. If you do not have a good initial guess, it may not solve your case. So it depends. And the first order derivative is used to speed up the calculation. So it is using some different techniques in order to improve the speed. So as far as the speed is concerned, the load flow analysis result achieved through Newton-Raphson will be much faster as compared to Gauss-Seidel method. And the fast decoupled Newton, two set of iteration, equation, real power, voltage angle, and reactive power magnitude are taken, fast in speed but low in solution precision, better for radial system and system with long lines. So if you see that you have a kind of a distribution system where you have long transmission lines and it is just a radial system, so it is good to go with the fast coupled decoupled method. But if you have a normal industrial system where the lengths are not a problem and you know that more voltage change will not be there, so it is good to go with the Newton-Raphson method. So this way you can select the different type of methods. So the source operating voltages, we talked about this, that what kind of voltages we want to select. So here we have different kinds. So if when we select swing mode, so what we are saying that the governor is operating in isochronous mode. What do we mean by isochronous mode? Isochronous mode, by isochronous mode we mean that when we are going to have change in my load, my generator is going to respond to the change in the load and try to make the generation equal to the load. So this is known as isochronous mode, and it will be in automatic voltage regulator. Secondly, it is going to control the voltage of the whole industrial network. So if I have if I am in voltage control mode, in this mode governor is operating in droop mode and automatic voltage regulator. So voltage control mode, surely voltages are going to be controlled, but your generator, whatever the generation value you have given, the PGen value or the dispatch value of the generator you have given, it is going to be maintained there, and it is not going to be varied with respect to load. So now the generator is going to will be expecting that this should be done by some other generator which is in an isochronous mode. For instance, your power grid is going to be changing its value, its P value when you have change in load. So for the megawatt, you have governor operating in a droop mode, so it is not going to respond to the changes in the active power, and it is going to operate in a fixed field excitation, no FVRs. So it is going to just select a certain amount of megawatt, and it is not going to change its megawatt when the voltages in the system changes. And in the power factor control mode, again the P value will not change for the generator, and the AVR adjusts to power factor setting. So it is your generator is going to see what is the power factor at the bus, and based on the power factor, whatever the power factor it has to maintain, it will change its reactive power so that it can achieve that power factor. So this is how generator or your source can operate in different modes. Similarly, you are going to provide the generator capability curve, and we have already discussed generator capability curve. So whatever the curve you have available from your manufacturer, you are going to replicate it here. So, and if you do not know the values, you can simply go with the Q max and the Q min values. So you can provide these two values. Similarly, generation category you can define. You can have multiple generation categories. For instance, if you are operating with a grid, so your generation could be XYZ, but if you are operating in island mode, you can have a different category of your megawatt and megawatt. So similarly, depending upon your requirement, you can select different generation categories. Similarly, on the load side, you can have different load categories. For instance, at design stage, you may have 100% of your load, but in peak condition, your load may be only 80% of the peak load or 80% of the maximum load. And during minimum condition, your load may be only 30% or 50% of the peak load. So depending on this, you can select different kind of loading criteria in your system. And the conventions, as far as the conventions are concerned, this is just to tell you the convention. So for the leading and lagging, how the convention changes. So if you see, for the leading means that ETAP displays lagging power factors as positive and leading power factors as negative. The power factor is displayed in percentage. So this is how you're going to, for the capacitive load, see it is showing in minus, and here the kVAR is going. And but if you have the inductive load, the same thing, but this time here it was the kVA or the megawatt is provided to the system, but in this case it is absorbed by the system. So this way you can have these values. So you need to know these conventions. So for the load flow adjustment, we can have different kind of adjustment. For the transformer impedance, as we said that we can have some variation in the impedance. Why we use these variations or this load flow adjustment? Because if we are working with the design data or the planning data, we are not sure that what is going to be the exact data. So it is better to consider worst case scenario. So in order to consider worst case scenario, we consider some tolerance in our equipment. So we can have this tolerance for the transformer, we can have this tolerance for the reactor impedance, overload heater, the transmission line length. We can have some variation in this tolerance impedance for the transmission line and the cable. So when we take this, consider these variations or these tolerance, with this tolerance we are going to get some worse result, so that our actual condition will be much better as compared to a studied condition. Similarly, on the global level, you can select that what kind of load flow adjustment do you want. So for each impedance, do you want to consider on the individual level for each equipment whatever tolerance you have given on the equipment level, or do you want it in the form of global level? Global means it is going to consider the same tolerance level for all the same equipment. For instance, for transformer, if I select global, it means that whatever, if let's say the global value is plus minus 7%, so plus minus 7% is going to be considered for all the transformers in the system. So this is how. Similarly, for the cable, you want it on the individual level, this transmission line resistance, or on the global level, similarly for the cable. And at the end, this is where, so we saw that in the video that we were having how the value we are going to select. So how we are going to check the alert. So this is how we check the alert. We can give the alert values here, that for a certain loading, how for a bus, if the bus is loaded more than 95%, it is going to be shown in our alert. So similarly, you can select different alert values for your different equipment. Similarly, for bus voltages, if your bus voltage is, how much change should your bus have to be shown in the alert value. So you can select these values from here, and once you select this, these are going to be displayed in your alert level. Welcome to Power System Analysis using ETAP course. In this lecture, we are going to create a sample industrial system in ETAP. So let us go ahead. So this is an example system which we will be creating to study the load flow analysis. So let us discuss the system first. So here you can see we have two main sources coming from the grid and connecting at point of connection 1 and point of connection 2. So the MVA short circuit capacity is given. Similarly, it is connected via two transmission lines. The length of the transmission line is given. Then it is connected to the main bus, and from the main bus we have two transformers feeding the industrial system. So we have here 13.8 kV system, 4.16 kV system and 0.48 kV system, and each transformer is feeding some individual load, if you see here. So here we have a system, typical system, which we have to prepare, and the data for this system is given below. So for utility source data, we have this power grid. The rated kV is given. So we need, for load flow analysis, we need at least one swing bus. So here we are going to have two swing buses for each power grid, and then the MVA short circuit capacity X by R rating is given. In ETAP, when you put MVA short circuit and X by R, these values will be automatically calculated. So we will see that when we put these values, do we get the same values or not? Then for the transmission line, the data given is the length, the size of the conductor, and the ohmic values of the conductor. Similarly, the design configuration is also given. So we will be preparing this data as well. We'll be modeling at least one of this line. Then this is the cable data for each of the cable modeled in the line. Then this is the transformer data. For the transformer impedance and X by R values is given. Based on this X by R values and percentage impedance, the R and X value will be calculated. The vector group is also given, but this will be used when we will be performing short circuit analysis. Similarly, the HV side and primary and secondary side of the transformer, and the rating is also given. The induction motors which are being used in the system, the data regarding these induction motors is also given. So we'll be using the same and we'll be adjusting the values. We'll be showing you how to model these values for the load flow analysis. Then this is the load data, and this is the lump load. Somewhere the lump load is used, and where there is percentage constant impedance load, it means it is a static kind of a load. So we have the load we have here is the lump load as well and the static load as well. So we'll be modeling this load as well. Welcome to Power System Analysis using ETAP course. In this demonstration video, we are going to prepare the sample industrial case which we discussed in the previous lecture. So let us see the case again. This is the case we have. So what we will be doing is we will be modeling at least one of the each equipment in the case, so that later you can prepare the remaining case. Okay, so we have to start with the power grid. For the power grid, we need a bus with the name POC1 and a voltage of 132 kV. So let us go ahead and model this power grid in ETAP. So here we go. We open ETAP. So before modeling, we need to create a new project, because this is a new project. We do not have the existing project. So File, New Project, and now ETAP is going to ask, where do you want to create this project? So browse, same thing. I'll go to the folder location. Let me create a folder with the name of my case. You can have whatever name you want. I'll just go inside it and give it a name. So let me give it my and I'll press save. Now ETAP is going to ask me different thing. Yes, I want it in English, and then authentication. Okay, I want to be the project master and editor. So here we have this case. Now this is our window where we want to create the case. So I'll just maximize it. So starting from this bus POC1. So let us go here. So we'll select create bus. I'm gonna go here and click it. So we have this bus. So when I double click it, I can open its window. So what do we want from here? We want to change the name POC1 and the nominal KV. In our case, it is going to be 132. And keep everything as it is for now and press OK. And there you go. You have this bus created. Now we want to connect a power grid with it. So again, we will go here, and if you see here, we have power grid. So I'll just click here, come back here and click here. So now we have this. So if you go on to the tip, just click and click again. There you go. So we have this power grid created. So let us give it the name. If we double click, so we want this name to be power grid 1, and then we need to change its rating. So we will go to the rating tab. So we have already 132 kV adjusted here, so nothing to do. We'll go to short circuit. Here we have to provide the short circuit data. So what data do we have? Let us see from here. If I go down, so my utility source power grid 1 should be 1250 MVA short circuit with an X by R of 35. So I will come here and I'm going to put here 1250 and X by R of 35. So if you have single line to ground fault different, then you can use the value which is provided to you. But if the value is not provided, you can use the same. And let us see here the R and X values. So it is 0.228 and 7.99. So if we see here 0.228 and 7.99. So as I said before, PSSC, this ETAP is going to take care of this. So now we have this grid created. We'll press OK. Now that we have modeled the power grid, it's time to model the transmission line. So for modeling the transmission line, if we see here, the data available with us is the ID should be line 1. It is a 132 kV line. The length should be 7.89 miles. The conductor size should be 397.5 kc mil, and the impedance data for the transmission line should be this, and the tower configuration is also given. So we have to select a type of conductor with which we can get these values for this size. So let us see. For this particular case, I know that the conductor type here is, so let us first put the transmission line here. So just click and make a connection like this. If you see here, the conductor type is Kenna. So what we are going to do is, from the library, we are going to try to find this type of conductor. So I will double click. So first of all, I will go to parameters and conductor library. I know that this conductor should be available in south wire, all aluminum conductor. So if we see here, so I selected south wire from here, conductor type all aluminum conductor, and their different sizes are available. So let us find the size we want. So Kenna 397.5 kc mil. So this is exactly what I wanted. So I'm gonna press OK. So this is done. So now let's go to configuration. So configuration, I have to select that configuration which is the type we have here. So let us go ahead and select this. So from here we are going to select configuration type, and you can check different. So for this, I know parallel vertical is the kind of layout which I am expecting here. So the height was 40 kilometer. The distance between the conductors was 12, and the spacing between them is 5. So if I selected, yes, it has been selected for me. So now if I go to, and the conductor is here, if I go to impedance, you will see 0.117, 0.325, So we have ended up with almost the same values here. So this means that I have selected the proper conductor. So the next thing I have to do is to select the length, and the length from here we know should be 7.89 miles. So go here and select 7.89 and press OK, and there you go, we have this model. So if you want to see the values here, or you want to see additional information here, what you can do is you can go to on this toolbar at the end, there is display option. Just click on this display option, and for the line let us select ID. And what do we want to see? We want to see the length also, and that's it. So let us see these two things, and when I press OK, you will see the length. If you want to see the conductor type also, so you can select different items. So now we have this line modeled. So what is the next thing to do? If we come here, the next thing is to create a circuit breaker and a bus, and the bus name is main bus A. So I will come here, let us select one bus, create bus, put it here, and to drag this you can change the size of this bus when this icon comes. So when I double click, main bus A, and the nominal kV is again 132, and I press OK. So there you go, I have this bus prepared. So for the high voltage circuit breaker, so I select high voltage circuit breaker from here, click, and I click here. So the connection is made here, and similarly connection here. So what should be the name of the circuit breaker? The ID for circuit breaker should be CB line 1. So I will come here, double click on this, CB line 1. No need to change anything for now, because we are only working for load flow analysis. So for load flow analysis we do not need anything from the circuit breaker. So that's it. Now we have this model. So the next equipment to model in our system is this transformer. So let us go and prepare the transformer. For the transformer, what we require is, first of all, if you see here, the transformer is connected to the breaker on the HV side, similarly breaker on the LV side, and then we have a cable in between. So we have to model these two cables and then a transformer. So we are going to model this now. So first of all, create a high voltage circuit breaker. So we will select this circuit breaker from here, come here, click here. So let us connect it to the bus A, and the name of the circuit breaker was TF1 HVCB. So we will come here, TF1 HVCB, and press OK. So this is done. The next thing we have to model is the cable. So for cable, we are going to select cable from here, come back here, and click it here. So now we have a cable. So for modeling, first of all, let us make the connection. So now here is the connection of cable with my circuit breaker. So now the next thing we have to do is, just by double clicking, first of all, okay, what should be the name of the cable? The name of the cable should be C1, and its length is 2405 feet. So I will come here, the cable ID is C1, it's 2405 feet. So this is done. And now to select the library. So we have to select a library in such a way that for this cable data C1, we should, the rating of the cable should be 138. So the length is this, the size is 500 kcmil, and the insulation type is EPR. It is a copper type conductor, and the number of conductor per phase should be 2, and this is the R and X value. So we have to select a cable where we get a similar R and X value. So let us go ahead and try to find a cable with which we can have all these parameters fulfilled. So I will go here, double click library. So what you can do from here is, first of all, we are operating at 60 Hz frequency. So let us try to minimize the number of cables. Okay. Conductor type. Let us sort the conductor type. We are considering a copper conductor. So I will just select copper. Now the kV. If you see here, we are interested in 138 kV cable. So I'll press OK. Okay. So we have this one cable with EPR only, which fulfills this criteria. So are we interested in? Yes, EPR 500 copper and with RX and this. So 500. So everything seems okay. So when I press OK, I have this cable modeled, and when I go to impedance, you will see that 0.035 and 0.078. So if I come here, 0.035, 0.078. So all good. Then I come back to info, and number of conductors per phase should be 2. So I will select 2 here. And when I press OK, so now my cable is prepared. If you want to see the additional data for the cable, again you go to display mode. For the cable, what we can have the length here as well. So when I press OK, so you now are able to see the length as well. So the next thing to model, I go to my diagram, is the transformer. So now let us model the transformer. For modeling the transformer, here we go. We have a transformer. I will click on this 2-winding transformer and click here, and then make a connection with this. So now, because this has to be connected with the help of a node, so I have a node here. For this node, I'm just going to select N1. This is my first node in my system. So that's it. So I have this node. Now for this transformer, I have to select the data. So double click on the transformer. Everything is okay here. For the rating, I know that my transformer is a 30 MVA transformer. So let us select 30 MVA. It is done here. For the impedance, we have, what do we have with us for the impedance of the transformer? I go to transformer data. So ID T1, 30 MVA, 132 by 13.8, 9 and 23.7. So I will come here, 9, and R by X is 23 by 0.7. So once I do this, see, R and X has been automatically calculated. So I'm going to do the same for 0, 23.7, and if I see, yes. And if you go to grounding, you will see that the connection group is DY30. So DY and delta Y is already there. So everything is okay here. Let us come back to info. Info T1, ID is T1. Everything is okay. So press OK, and that's it. So we have this transformer model. So if I come back here, in this way, now the next thing we have to do is again model the conductor C3. So let us see what is C3 here. So if I go here on the conductor C3, it is a 15 kV cable with the length of 850. It should be EPR with 1000. So let us go ahead and find this kind of a cable. So I will come here. So let us select a cable first. So we will select a cable here, then here. So again, it is connected with a node. So for this, let us select, what do we have in our diagram? It says this node is N3. So I will just select N3 here and press OK. So everything is okay here. Now for this cable, what is the name of this cable? C3. So double click. ID should be C3. So we have this ID selected here. It is a 850 feet cable. And now from here again we are going to select our option. So we are working with 60 Hertz. So 60 Hertz selection, and should be a copper cable. So copper, and it is a 15 kV cable. So just select 15 kV from here, and then insulation type. So let us see what is the insulation type from here. The insulation type for C3 is EPR 1000 kcmil. So let us select from here only EPR. So you see, now we have several cables here. So we have to select the cable with which I should get number one. It should be 1000 kcmil, and I should get this R and X value. So let us see. So 1000 kcmil. So for this, no, we do not have. So let us select here and see. Yes, we have 1000 kcmil here. So let us go and select. Let me check if we are able to. So when I select this, I go to impedance. So 0.022, 0.089. No, see, the X value is not matching. So I need to select another cable. So again, I will go to info, library. I have to repeat this process. 60 here, copper here, 15 kV here, insulation is EPR. So let me see from here. Maybe this cable is going to have. So I press OK. We go to impedance 0.07. So this is exactly what I wanted. So this is the right cable for me. I will select this cable, and number of conductors should be 2. So 2 here, and we press OK, and there you go. We have this model. So now the next thing to do is to create another bus with the name of bus A and connect a transformer with it. So let us go here, again create a bus. I'm going to elongate this bus, adjust it. So the name of this is bus A, and it is a 13.8 kV bus. So that's it. I adjusted the bus name. Then I need an HV transformer, circuit breaker. So I'll connect it to the bus, and the name of the circuit breaker should be TF1 underscore incomer. So I adjust the name, and then I connect. So there we go. So we have this model. Now let us model load on the 13.8 kV bus. So just making it elongated. Okay, so for the 13.8 kV bus, I will model some of the load, and then you can prepare the remaining one. Okay, so first of all, here we have CB6, which is connected to a distillation unit. So let us create this load. Okay, so we will go here. So we want a HV side breaker. I will just put a breaker here. Press escape, double click. So it should be CB6. That's it. And now what I have to do is I have to put a lump load here with the name of distillation unit. So if I go here, you see this is lump load. I select this lump load. I come here, put here, and this is distillation unit, and the load here nameplate MVA. So if we go here, the load is 7000 kVA, so we have to select kVA. And if we see the load here, so here we are going to have a distillation unit at 13.8 kV, 7000 kVA at a rated power factor of 85 and constant 80-20%. So let us prepare this. So if I go here, so constant power kVA is 80, constant impedance is 20. So this is okay for me. Let us select kVA from here. So 7000 at a power factor of 85%. So 85% power factor is there. So we have this ready. We still have to give the value of the rated current. So just let us press OK. We connect our load to this. So now it is connected to 13.8 kV. If I see, the current should come here as well. See, so everything is all set here. So I press OK and that's it. So I have my load prepared. So now the next is to connect. Here if we see, so we have to connect. So I will select the CB4. With CB4 I need to connect a cable 2 and then a compressor of 4500 HP. So let us do this. Again, breaker, put a breaker here. Name of the breaker should be CB4. Starting CB4, pressing OK. Next I have to connect the cable. So I take a cable, put it here, connect it over here, and the next thing I have to put is a motor, induction motor. I will place it here and connect it to the. So again I need a node for this. So what is the node number here? Node number I have given N6. So we are going to provide here node number N6. Press OK. So let us go to the. So you will be modeling the data of the cable yourself. So I will just tell you how to model the motor. And once you have modeled one motor, you can model all the motors as well. So when I double click on this, here you go. So here it's a compressor A. So I have given this name here. Let us go to its nameplate. So nameplate HP horsepower is 4500 horsepower, and when I put 4500 horsepower, some of the data is already included here, but I do not require this data. I have some other. This will be depending upon the nameplate rating of the motor itself. So whatever the motor you have, you are going to put from there. Usually these data is provided in the motor, but for my case, so it is 92.83. So I will come here, instead of 9, I'm going to put 92.83 and at 75%, 92.46, 92.46, and at 50%, 89.72. So 89.72. Similarly, efficiency at 100% 97.99, 97.99, and at 75 98.58, and at 50% 99.03. So 99.03, and then at no load percentage, so no load power factor at no load is 0.17. So I'm gonna go here and select 0.17. So that is it. My data is ready, and no load ampere at 100% is around 18.24. So I'm going to go here at 18.24. So my data is ready. So I'm gonna press OK here. I have modeled this data as well. So let us continue further. Before continuing further, there is one easy way to do this also, because you have prepared. One way is to make all this thing as we have told you, or there is one more way to do it. And how you can do it, for instance, here we need main bus B also. So I'm just gonna create a bus. Come here, create a bus, Now get it. Let us give it the name main bus B. Again, this is a 132 kV bus. So 132 kV bus. I press OK. Now, if you want this data or this data copied here, so you simply have to do is select whatever you want, copy this, Control C, and right click and move from dumpster. Do not use normal paste. With the normal paste, you will have something remaining in the dumpster as well. So if you want to copy it for the multiple times, then paste is good. But if you want to copy it once, so always go for move from dumpster. So once you move from dumpster, see, the entire data is available here. You just go here and that's it, connect it to here and just change the name. So this should be, instead of this, transformer 2 HVCB. See, so the cable name here is C2. So let us check here. Let's make it C2. So all ID already exists. Let us see where the C2 is. So it has given this name C2. So let me change this first. So this one is C4. So I will go here and make it C4 first. C4 is also existing. Where is C4 existing? I need to check. Okay, so I need to go take a long route. So what I can do here is, let me give this name C5 because C5 is not existing, and then come here and make it C2, and then this C4. Okay, and I'm done. Now if you see, this whole thing is grouped together. So if you want to keep it grouped, okay, fine. But if you do not want to keep it grouped, just select this, right click, and you see this group option. So if you unselect this, now everything is ungrouped once again. So you can group or ungroup depending on your condition. So here I need another bus. So I'm going to select a bus, put a bus here, and like this, and the bus name should be bus B. So I will select bus B, and this is a 13.8 kV bus. So press OK, connect B. See how quickly we have prepared. And if you want to change the parameters, if the parameters are changed, just select whatever the parameters are there. Similarly, you can copy this and move it from the dumpster here, and you are going to have your case here as well. In the same way, continue creating the case. So now the next we have to do is create another bus. So I'll select a bus. This time the bus is 4.16 kV and bus 1A. So bus 1A 4.16 kV. So pressing OK. So now for this bus, we have a breaker, cable. So I'm going to select breaker and then cable, and then transformer, and then incoming breaker, then 2-winding transformer, which will come with a node. So you have to give the name to the node as well. Then this incomer breaker for this, and ultimately connecting it. Now you can add the data. You already know how to add the data. It will be added in the same way as you added for this transformer. So same way, we have the impedances from here. So the transfer impedance for T3 and T4 is given. So you can use the same impedance from here. The cable data is given. You can use the same cable data and get the values. And then induction motor data is also available. So use the same data to prepare the case. Then moving on, once you prepare all this data, then we have to go to again a transformer. Then again we have a bus. This time it's a bus 2A and 0.48 kV bus is there. For this also we have a breaker, so I'm going to select a breaker here, and then you have a transformer. So we model this transformer. You can add the data, you already know what data to add. And then on the LV side, this time you have to use LV circuit breaker. Now because we are talking about less voltages, less than 1 kV voltages, so LV breaker here use. So connect here, add the data, adjust the ID numbers, and you will be all set with this transformer. And then let us prepare the load. So this way, now for instance, if we want to prepare this load, so for this we have a breaker, then cable, and then load. So what we are going to do, LV breaker, then cable, and then load. So what kind of load is this? Server A. It seems it is a static load, so we are going to select from here. This is the static load. I'm going to select the static load from here, and like this. So now you will give the node number, you will give the cable ID, select the cable parameters and everything. Once you are done with this, so this, and the other load here in this case is light A, so which is directly connected. So simply click, add, change the name to light A, give the data, the ratings, which is the load rating from here. If we go to the load data from here, and then the receptible load, and the receptible load is lumped load. So here we will go here, we will select a lump load here, and for the receptible we will correct this load and give the data. So this way you will prepare your entire case, and once the case is prepared, we will perform load flow analysis on the case. Welcome to power system analysis using ETAP. Now that we have prepared the entire case, we can perform load flow analysis on this. So this is our whole case. So before performing load flow analysis, let us adjust some normal operating condition, because normal operating condition is the type of condition in which the industrial system or any power system is normally operated. So here we see that we have kept this breaker open. This should be closed. Why closed? Because let's say if this breaker trips, or this breaker trips, or this transformer gets tripped, what will happen? In this case, whole load feeding through this side of the bus will trip. This is what we do not want. So for this case, we are going to select this and close. Similarly, this breaker should be closed, and this breaker should be closed. So closing all the bus couplers. So in this way, we will have, in case of tripping of one side of the bus, the entire load will continue to feed. So now the next thing is, we need some kind of what load should be on, what should be off. So if we see here, we have crusher 1, crusher 2. So it seems similar. So let us assume that one of this and this compressor B and compressor A here. So let us assume that one of the crusher and one of the compressor remains in a standby position to be operated when there is some problem. So what we can select for this, let us select this crusher 1 to be in normally open state. So I'll just adjust this, and similarly compressor B to be in open state. So there you go, we have this adjusted. So this seems about. Similarly on this side, let us assume that we have pump A, B and C. Pump A and B seem similar, so we will assume that pump C usually remains in standby position. So I'm going to select this open. So here we go. And the load, let us assume that this local load remains connected all the time. So now that we have adjusted the configuration, you see it is written here normal status configuration. So this is my normal status configuration. I will just save this. That's it. I have my case saved. Now I can perform load flow analysis. So now performing load flow analysis, what I have to do, I will go to this load flow. From here, I will select run load flow. Let us run and see if you see here, we can select what kind of changes we want in our load flow. So if you see a brief case type of so I did case study, let us click on this. So my case ID is, I am calling this load flow. Okay. And my report should be in either in kV, percentage, whatever you want. So you can select from here. Yes, this is exactly what I want. What kind of method I want. So I'll be using adaptive Newton-Raphson because it is the fastest. What should be the, and how to adjust different conditions. So you can select different options from here. So the loading level, what kind of loading do you want? So I am selecting the existing loading which I have designed. Similarly, adjustment, we discussed this. So what do we want? For the impedance, for the adjustment of the transformer, do I want individual or global? So I want everything in the form of individual. Whatever I have given, please use the same values. Alert values, alert me when the over voltages are above this limit or below this limit, and the bus voltages, so critical or marginal. So whatever I want to select. Similarly, for the emergency condition, what I want to select. So if some in case of emergency, what do I want to do? So for now, I do not want to do anything, so I am keeping the same. You can try this new options as you want. So I'll press OK. Everything seems to be okay here. And now I want to be prompt for the output, so that whenever the report is created, I should be prompted, so that I will give the name of the report. So when I press run load flow, so now it is asking me, because I selected here prompt, so it is asking me what should be the name. I will give it the name load flow normal, because this is my normal operating condition. And when I press OK, ETAP will perform load flow analysis, and there you go. The load flow analysis has been performed and the results are there. So if we see the results, so if let me select the unit here, show unit, yeah, so that I know here almost 6,000 or 6 megawatt is coming from the system. So 6 megawatt plus 8, so almost 14 megawatt load is of this entire facility. So for this 6 megawatt is coming from here, 8 from here, and similarly here the buses. Here if you see the voltages, we have reduced voltages and the loading. So we have some problem here. So we can see that even in the normal operating condition, we may have some problem. So now we will try to resolve this problem. But first, we have seen that the voltages have reduced to 93. So it's well below the range. Usually the voltages, the criteria is to maintain the voltages within plus minus 5% range. So this is more than plus minus 5% range. Similarly this. So let's see what is the alert condition telling me. So if I go here, alert view, and I select here, so it is telling me some, yes. So it is telling me bus 2A under voltage condition. So EC3 cable, its rated limit is 114 and it is operating at 121. Similarly EC4, it should have a limit of 24, but it is operating at 35. So it's usually overloaded. And so this way, this is exactly what we mean when we say that we perform load flow analysis to find out that whether the loading of the equipment is okay and whatever the condition. So from here we have seen that yeah, condition seems to be okay, but there are certain problems in the system. So now what we have to do is we have to resolve this problem. We'll see that is it possible to resolve these problems or not, and how can you take the report. So for the reporting, we can come here to report manager, just click on this and it will ask us what kind of report do you want. So how about a PDF report and a complete report. So when I press OK, So a report should be created. It is still creating the report, and there you go. So we have a PDF report here, and the PDF report, so ETAP program we have used, and the loading category was design, generation category was design, load flow analysis, diversity factor, but we selected, so we had 2 swing buses here, total load we have 21, so number of buses. It has told us the transformers and the details of this, what kind of method we used, the type of adjustments we used, and then what kind of bus input data was there. So it is telling me about all the data I have entered in my system, and the details about my cables, what cables I have used, what is the tolerance factor, what is per phase, R and X values, so everything related, and the library model I have used, so everything is being told here to me. Then again, this is for the transformer, all the connections which I have in my system, and now the load flow report. So for bus 1A, the voltage is 4.16, the magnitude is this, the angle is this, there is no generation, there is no load on bus A, and then the ID is connected to it, and whatever the load on each branch is there, and how much power factor I have achieved for this. So it is giving me the detailed report. So you can go through this report, and this is the same way you will take the data from here and make your report. So loading summary is there. So how much each bus is loaded, how much is the percentage MVA, percentage loading for, similarly for branches, the loading for the branches will be given. So if you see here, yeah, the cable 1 has a capacity of 1253, it's 35% loaded, loading ampere is this, and it's this much loaded, and I have 3 cables which are overloaded, so here are the overloaded cables, and so this way you have all the data. You can go through this data, try to understand it, and so this is how you perform load flow analysis. Welcome back to load flow analysis using ETAP demonstration video. Now that we have performed load flow analysis, we came to know even under normal operating conditions, we have some issues. The issues are that we are having the overloading on cable EC3, EC4 and EC7. Similarly, we have voltages issues at bus at 4.16 level and 0.48 kV level. So what can we do? We can resolve these issues. There are several ways to do it. The first way is either to use a cable of higher capacity. So if we use a cable of higher capacity, then in this case surely we will not have the overloading. So this is one of the way to do it. Or another way is, so instead of one core, so if you see here, if I double click on this line, we have one conductor per phase. So instead of one conductor, what we do, we attach another conductor in parallel to this existing. We can reduce this. So it depends which is the easiest solution or which is the cheapest solution. Based on this, you will perform the analysis. So let us assume that we have the capability to increase the number of conductors per phase. So instead of one, if I use 2 here, and let us solve the case again. Now if you see, now we have resolved the overloading problem here, but if we go down, we still have the problem here. So how about we do the same thing here and here? So let us use 2 instead of 1 here, and 2 instead of 1 here, and let us solve it again. So now we have improved the situation. Now we do not have any overloading in our case. This can be seen from here as well. If I go here into the alert mode and I increase this, so now I am only having under voltage problem. So I have half marginal problem and some critical. So what to do for this? Now there are 2 ways to resolve this problem. One of the way is to play with the tap, transformer tap. So we can play with the tap. If we adjust the tap of these transformers, we can improve the voltage. So let us see what happens if we change the tap. First of all, let us change the tap of this T3 transformer. So I am going to double click on this. I will go on to the tap, and here is my fixed tap. So let us reduce the tap. So now what I'm trying to do is I'm trying to reduce the voltages from 13.8 kV side so that I can improve some voltages on 4.16 kV side. So when I do this and I solve it again, yes, now you see the voltages have improved. Although the voltages have improved, but see, if I change the tap of only one transformer, if you see here, now this transformer is exporting 1235 kilowatt, but this transformer is only exporting 1024. So it means there is some kind of a circulating current flowing in between the two transformers, so which is not a good condition. This can cause the heating of transformers. So what do we have to do when we have transformers in parallel? We have to change the tap of both transformers. So let us change the tap of the other transformer as well. Okay, let us solve again, and now see, now it is same, no circulating current is there, and I have improved the voltages as well. But I still have the problem here. So I know that by changing the tap position here, I can change the voltage, or I can change the tap position here. So let us change the tap position here this time. So tap, let us reduce here, and I will do the same for here. And when I press OK and solve, there you go, I have improved the situation here. So one way is to improve the voltage in this condition is to use the tap. So by changing the tap, we will be able to improve the voltage. So this is our solution. This will be our operational solution or design solution, that okay, fine, if you have this problem, you can go with this, but you can give other solutions as well. So for instance, if you do not want to change the tap, there is another condition. How about capacitor? So by putting the capacitor bank in your system, you can improve the situation as well. So let us see how we will in later stages see if capacitors will be enough for this or no, but for now we will go with this solution. So this is now the solution. Now you can again create the report or whatever you want to do. So from here again, so this is how you perform load flow analysis and do the changes in this. Welcome back to power system analysis using ETAP load flow analysis demonstration video. So now we calculated the load flow analysis, we adjusted the tap of the transformers, and we improved the voltages. So everything seems to be okay at this point. But what if? So now we can have different what if conditions. So one of the what if condition is, what if we have the maximum load operating on this? So what do I mean by maximum operating load? If you see here, we opened some of the load which was in standby. So there can exist a condition where the load should be maximum, where all the load in the system is operating. What will happen in this case? So if we want to simulate this condition, let us create an additional case. So we can go to configuration manager to create this case. So for this purpose, I will go to edit. I'm in the editing mode. Now here I want to change the status of circuit breaker 2, circuit breaker 5 and circuit breaker 13. So how we can do this? If you come here, you see this configuration manager. You click on this configuration manager. Now we need to create a new configuration manager. So I will create new from here. And let us give the name. The name for this, let us give maximum or peak. So let us press OK. Now we have another configuration. So now from here we can change the configuration or the status of what we want. So what do we want here? We wanted to change the status of circuit breaker 2 and 5. So if I go down, where is my circuit breaker 2? This is my circuit breaker. So circuit breaker 2, it was in open position. So now for this maximum, let us select as close. So it has already selected as close. So similarly for 5, it is also closed. So this is good for me. And the final one is CB13. So let us see CB13. It is also closed. So now for this, I am considering all the breakers closed, but you can change the configuration from here. So you see from here, open, close, you can select whatever condition you want, but the condition I want has already been selected and it is okay for me. So I will press OK. So once I press OK, now I have another condition. Now what I have to do simply, if I want to select another configuration, I will just drop down from the list and select maximum. See, if I select maximum, now it has saved the same configuration for me. So let us first save so that I have both configurations saved with me. Everything seems to be okay. So now let us calculate the load flow for this condition. Now if you see, I was only calculating the load flow for load flow normal. So instead, let us select prompt again, so that now whatever I am doing, it will be selected. It will ask for the new name. So run load flow. Here I will give maximum underscore load flow because this is my new condition. I will press OK and it will start performing the simulation. Okay, so everything seems okay with the additional load. No overloading is there, but yeah, now the voltages has reduced a little bit. So marginal reduction is there, but still in the normal operating range. This can be adjusted by the transformer. So see, my taps which I adjusted, they are already in it. So even with this condition, my system seems to be okay. So this is how you create configuration manager. Now what you can do is you can try different configuration. How about you switch off this breaker and this breaker, or one grid and keep one grid, and play with this so that you can study different kind of combinations. So this way the combinations are prepared. So that is all from load flow analysis. Welcome to power system analysis using ETAP. In this lecture, we are going to provide you with basic introduction of short circuit. So why short circuit studies are required, or what is the extent of the short circuit studies? Short circuit studies are equally important at the planning stage, design stage, or at the operational stage. At the planning stage, the basic objective of short circuit analysis is to identify the rating of the circuit breakers required. So the short circuit study can be performed in order to help finalize the system layout, determine voltage level and size cables, transformer and conductors, especially the circuit breaker and these equipment, that what should be the capability of each and every equipment. That because we want to know that when a short circuit is going to occur in the system, there is going to be a huge inrush of current or a huge current flow through each of these equipment. So we want to make sure that each equipment has the capability to withstand such short circuit levels. Similarly, at the existing system, fault studies are necessary in case of added generation, installation of extra rotating loads, system layout modification, rearrangement of protection equipment, verification of the adequacy of existing breakers, relocation of already acquired switchgear in order to avoid unnecessary capital expenditure. So you have a running system, you decided to add a new load in the system, or a new motor in the system, or new generation in the system. So now that we are changing our configuration of our system, so we want to make sure that, okay, with this changing configuration, will our short circuit studies or the short circuit levels which we identified before at the design stage, are they still applicable, or do we need to change these? So that is why this short circuit studies is equally important at the planning or design stage as well as the operational stage. So what is the purpose of the short circuit study? Short circuit study can be used to determine the following condition. The first and the most important condition is evaluate the electrical equipment short circuit withstand capacity. So this is important so that we can verify the protective device making capacity, verify protecting device breaking capacity, verify protecting device thermal withstand capacity, so that when a certain amount of huge current is flowing through a protective equipment. In our case, this protective equipment is going to be the circuit breaker or the switch gear. So we want to make sure that our circuit breaker or the switch gear has the capability to, number one, withstand the huge stresses provided by this short circuit current. Secondly, that it will be able to make or break this amount of short circuit current. And the second most important thing is to select the settings for the relay coordination. Especially in the industrial system, the most important type of coordination we require is with the overcurrent. So we want to make sure that, because if we do not know the exact fault currents, we cannot properly coordinate our relays, and condition may occur when a fault at a certain level can cause another relay to operate, thereby making the outage of a large element as compared to the feeder itself. So the type of short circuits, basically you have two major type of short circuits. Number one is the balanced short circuit, and the other one is the unbalanced short circuit. A balanced short circuit is a type of a short circuit in which all the three phases in the system gets shorted out at the same time. So why it is balanced? Because the fault current will affect all the three phases and all the three currents. So that is why it is known as a three-phase short circuit or a balanced short circuit. Whereas unbalanced short circuit will be the one in which not all the three phases and not all the three currents are affected. Only one or two phases are affected. So such type of fault can be line to line, in which only two lines are shorted out, or we can have line to ground, whereas two conductors are shorted out along with the ground, or we can have a line to ground fault. And so this is how the short circuit can be. And the type of faults, as we discussed, will be three-phase ungrounded fault. In case of ungrounded fault, all the three the phases are shorted out each other, and we also call this as a metallic fault, that there is no resistance or impedance which is restricting this fault. So in this case, huge amount of current is going to flow through the system. Then the other is the three-phase grounded fault. This is same as the three-phase fault, but in this case there will be some grounding or impedance in between the fault. So this type of fault is going to be less severe as compared to three-phase bolted fault. Then the remaining type of faults are phase to phase, and phase to ground. So same case for the phase to phase, it can be ungrounded or grounded. By what do we mean by ungrounded? That only the two phases are shorted out. And what do we mean by phase to phase grounded? That two phases are shorted out and they are shorted to the ground. Most of the time in a power system, the faults are usually single line to ground fault, because this is the most common type of fault occurring in the system. So 85% of the time, the fault occurring in the system is going to be a single line to ground fault. So single line to ground fault current can range in the utility system from a few percent to possibly 115%. So if X0 is less than X1. So now these short circuits, they are basically dependent upon the impedance of your system. So depending upon the impedance, you will have different kind of short circuit. But in usually as a benchmark, what you can say is that usually the short circuit current in a power system is almost 115% times the three phase. So what do we mean? Let's suppose if we have 100 kiloampere or 10 kiloampere of a three-phase fault, then the single line to ground fault will be usually 115 times of this. But in industrial system, having a single line to ground fault greater than the three-phase fault is rare. So typically for a typical industrial system, we will usually see that our single line to ground fault is almost 87% of the three-phase fault. So in an industrial system, the three-phase fault condition is frequent, the only one considered, since the type of the fault generally results in the maximum fault current, because this is going to affect our system the most. Because in our industrial system, we see that usually we have seen that statistically three-phase fault is most common, and it is going to have most were fault current, so we are going to consider this when performing the short circuit analysis. Welcome to power system analysis using ETAP. In this lecture, we are going to discuss basic short circuit calculation. So when we talk about a short circuit or a balanced short circuit, in case of balanced short circuit, all the three quantities behave same. So when we are talking about balanced short circuit, it means that all the three phases are going to be shorted out at the same time. It means that the voltage, the current and the impedance of all the three phases is going to be impacted at the same time. It means that the normal calculation for the single line diagram or the single line method of calculation can still be implemented here. So how do we implement a short circuit calculation for a three-phase balanced short system? It is simple. Consider this example here. Consider a generator connected to a step-up transformer, then to a transmission line, then there is the load transformer and then the load. Everything in this system has been converted into its respective R and X value. So when we calculate short circuit, what do? We simply calculate the Thevenin impedance behind the short circuit. So in this case, what is going to happen? We have three impedances in series. This generator impedance, the transformer, step-up transformer impedance and the transmission line impedance. So simply we are going to add them up and get the Thevenin equivalent impedance in the form of RTH plus XTH, because R is going to be added with R value, X is going to be added with X value. So once we do this, what we simply have to do, we simply need to know what was the pre-fault source voltage, and using the ohmic formula V is equal to IR or V is equal to IZ, we can calculate I as I is equal to V by Z. So simply by converting this into an equivalent form and calculating the current flowing through this simple circuit will give us the short circuit current through this circuit. So this is how we calculate short circuit current. Now to further explain this concept, let us take a hand calculation, a hand example, a simple example. Here this is an ETAP circuit which we'll be creating in our next demonstration video. Here you see we have a power grid. This is the same circuit which we have used for the load flow analysis as well, for understanding the basics of load flow analysis. So we have a basic power grid which has a MVA short circuit capacity of 5715 MVA and has an impedances of 0.116 and 1.74%. And we have a transformer, a 20 MVA transformer with an impedance of 9% at 20 MVA connected to a load of 15 MVA. So now if we want to calculate the short circuit, what we have to do at this 69 kV bus, so what we have to do, we have to calculate the total impedance of the power grid as well as the total impedance of the transformer. So we are going to add them up and then calculate by simply using V is equal to IR or I is equal to V by R. We are going to calculate the current at this point. So in order to do this, because we have a transformer involved, so the easiest way to do such a calculation is to use per unit calculation. So here these values are already in per unit at 100 MVA base. So my Z grid will be equal to R grid plus JX grid, which is on per unit at 100 MVA base. So what we simply have to do, because these values are in percentage, we are going to divide the values, both values by 100 in order to convert them into per unit. So 0.116 divided by 100 will become 0.001116 and here J will be equal to 0.0174, so 0.0174. Now we know that R is equal to R square plus X square under the root. So by simply using this formula, Z grid will be equal to 0.00116 square plus 0.0174 square under the root, and with this formula we are going to get Z grid is equal to 0.017495 per unit at 100 MVA base. Now for the transformer, we already know that transformer has 9% impedance, Z value is 9% at 20 MVA base, or 9 divided by 100 is equal to 0.09. So 0.09 per unit at 20 MVA base. Now we can convert this 20 MVA impedance to a 100 MV impedance by using the simple formula Z per unit new is equal to Z per unit old into S base new divided by S base old. So here Z per unit new is equal to 0.09 into S base new, which is 100, S base old, which is 20. So simply using the calculation, we get ZXFMR or Z transformer is equal to 0.4499 or simply around 0.5 per unit at 100 MVA base. Now what will be the total impedance? Total impedance here will become the impedance of Z grid plus impedance of Z transformer. So Z total is equal to Z grid plus Z transformer, or adding up the both values, we are going to end up with Z total is equal to 0.467494 per unit at 100 MVA base. Now to calculate balance short circuit calculation, what we have to do, V is equal to IZ, or I short circuit will be equal to V by Z in per unit. So here I short circuit will be equal to 1. We are assuming the voltages here to be 1 per unit. So 69 kV is equal to 1 per unit divided by 0.467. So this we are going to end up with 2.13 per unit. Now, in order to convert this value back into its actual value, we need to calculate I base. So what will be I base equal to? I base is equal to S base divided by under root 3 into V base. So here S base is equal to 100 MVA, V base is equal to 69 kV, and simply calculating this, we are going to end up with I base is equal to 0.836. So now actual short circuit current will be equal to I base into I per unit, because I per unit is equal to I actual divided by I base. So after multiplying this per unit value with I base value, we get actual current of 1.789 kiloampere, or almost equal to 1.79 kiloampere. Welcome to basic short circuit calculation demonstration video. So now before we discussed how we can use hand calculations in order to calculate simple short circuit for simple networks. So now here we are taking the same network and we are going to calculate short circuit through ETAP and compare our results with the actual results. So if we see here, what do we have? We have a power grid. So for this power grid, what do we have? If we go into the short circuit, so we have a power grid of 25 kilo short circuit current with a X by R of 15. So we modeled this, and now the percentage values of R and X at 100 MVA base are 0.116 and 1.74%. So this is exactly what is shown here. You can get this value simply by going to display option, and for the power grid check Z. So this way you will be able to get the Z value. Similarly, for the transformer, we have a transformer 20 MVA transformer, and if we see the impedance of this transformer, we have an impedance of 9% with an X by R of 18.6. So R and X value. So because we have to calculate the percentage Z, so we are not taking care of R and X at this moment. So we are mostly considered with percentage Z, which is 9% here. 9% or 9 divided by 100 will be equal to 0.09. And we have a static load. So static load means it is not going to have any contribution because no motor is there or no rotating load is there, because usually the short circuit current is contributed by the rotating load. So rotating load can either be a generator in the system or some induction motor or induction generator. So since we do not have any induction motor here, so no contribution should come from this. And for loading, we simply used a 15 MVA load with a power factor of 9%, which is not going to impact our short circuit at all. So this is the almost same network which we used for the load flow analysis. So this is the same network. If you created this network before, you can simply use the same network. However, I have done only one change. Instead of the lump load, I have used static load, because for now, in order to understand the basic calculation, we are not interested in the motor load. So how do we calculate short circuit? For calculating short circuit, simply you have to go to, from here this was power flow, now this time you have to go to short circuit. Without going into the detail of which type of method we are using, we are simply going to calculate short circuit. So without changing anything in my system, I simply go here and we can select where we want to select short circuit. So if I see here, let this bus. I do not want the short circuit here, so I'm going to click here. You can simply right click and make sure that this fault is checked. So check of this fault means that the short circuit will be calculated for this. So if I calculate for, if I see this is unchecked here, so if I will check, this becomes maroon also, it means it is also going to be considered. But for now I only want to calculate for my 69 kV bus, so I'm only selecting 69 kV bus. So now for simply calculating three-phase fault, what you have to do, calculate three-phase duty. So simply run this. When I click on run, ETAP is going to take time and going to give me the value which is equal to 1.79. If you remember from our hand calculation, we calculated the value as 1.789. So rounding off to 1.789 to 2 digits, we almost end up with 1.79 kiloampere. So this way our hand calculation is matching with the ETAP calculation. So this gives us the confidence that whenever we are going to calculate the fault current, we are going to end up with the same values. Welcome to Power System Analysis using ETAP. In this lecture, we are going to introduce the concepts of IC 60909 short circuit standard. This is the most commonly used standard in the industry. So let us discuss some common terms, important terms for the IC 60909 standard. The four common terms which will be commonly used are initial symmetrical short circuit current. This is the maximum current which you can have, the maximum RMS value of the short circuit current at the zero value instant. Which means that as soon as the fault is started on the system, the short circuit current gotten at that point is known as initial symmetrical short circuit current, whereas peak short circuit current IP is the maximum possible instantaneous value. Symmetrical short circuit breaking current is the instant of the separation of first pole of the switching device. So the short circuit current at the point where breaker or the switching device will open its or part its contact. So the current at that moment will be known as symmetrical short circuit breaking current. Whereas steady state short circuit current is the RMS value of the short circuit current which remains after the decay of transient phenomena. So when everything has settled down, the value of short circuit current will be known as steady state short circuit current. So the calculation method. So initial symmetrical short circuit current can be calculated as I double dash K is equal to C of UN divided by under root 3 Z of K, where Z of K is the total Thevenin impedance or the total impedance behind the fault. It is the same thing or the equivalent impedance at the fault location. So this is the same thing as which we did for the hand calculation. So similarly, this ZK is calculated, whereas C is the factor. This factor will be discussed in detail in next lectures, but IC 60909 tells you that you have to use a certain amount of certain value of this factor in order to get the most conservative current. For instance, we know that V is equal to IR or I is equal to V by R. So where V is the base voltage at the point where short circuit has to be calculated. But for now, if we increase the value of V, we will get the maximum current because we have V divided by Z. So this is the same thing. So by increasing the C factor to a certain maximum value, we can increase the value of short circuit current. Peak short circuit current calculation. The peak short circuit current is calculated by IP is equal to under root 2 K I double dash of K. So whatever is the short circuit current value, we multiply it by under root 2 and then multiply it by K, and where K is the function of system Rx ratio at the fault location. So now talking about X by R for peak current can be calculated with three different methods. For the method A, what do we do in method A? The uniform ratio of X by R in calculating the short circuit current. So we use uniform ratio of X by R, whereas in method B, we use X by R ratio at the short circuit location and calculating the short circuit current. So whatever is the X by R at the point of fault, this is the X by R we take. Whereas method C using equivalent frequency in calculating the peak current. So this is how you can use different methods for calculating short circuit current, but usually method B is used. Method B is the most common type of method which is used. Similarly, if you want to get more conservative result, it is good to include no motor decay. So without no motor decay, what will happen is that when the DC component of the short circuit current usually is decayed with the help of in the form of an exponential form. This we will see in the later stage that how this decay is there. But if you do not include this decay, you are going to get more conservative value. But if you include the decay due to motor, then surely you are going to get less conservative value when calculating breaking short circuit. So we were discussing the methods. So the K factor method. So method A is the uniform R by X. The value of the K factor is determined from taking the smallest ratio of R by X of all the branches of the network. Only the branches that contain a total of 80% of the current at the nominal voltage corresponding to the short circuit location are included. Branches may be series combination of several elements. So method B, R by X ratio at the short circuit location. The value of the K factor is determined by multiplying the K factor by a safety factor of 1.15, which covers the inaccuracies used after obtaining the R by X from a network prediction with complex impedances. So in order to make it more conservative and taking care of error, we include an additional factor of 1.15. Method C, equivalent frequency. The value of the K factor is calculated using a frequency altered R by X. R by X is calculated at a lower frequency and then multiplied by a frequency dependent multiplying factor. So you can use any method, but as I told you before, method B is the most commonly used method. So the symmetrical short circuit current breaking calculation. So now when we talk about breaking, this is the point where the contact of the circuit breaker or your switching device is going to part or going to open. So why we are interested in this current? Because we are interested, this will be the point where where your switch gear or your circuit breaker will open the contact. So we need to know what will be the exact current at that point when the circuit breaker will be opening itself. So for a far from generator fault, the symmetrical short circuit breaking is equal to the initial short circuit current. So if you have a far from fault, so what do we mean by far from fault? So if we are talking about our distribution location, or we are talking about a industrial location where there is no generator close to it, you are far away from the power plant or far away from all the generation which is available in the system. So in this case, your IB will be equal to I double dash of K. But for a near to generator fault, when this will come into play? When you have generation within your plant. So if you are talking about an industrial network which has some kind of local generation or co-generation, or there is a power plant very close to this industrial network, then in this case, this will be an example of a near to generator fault. So for a near to generator fault, IB is obtained by combining contributions from each individual machine. IB for different type of machine is calculated using the following formula, where IB will be equal to either micro I double dash of K for synchronous machines and micro Q I double dash of K for asynchronous machine, where mu and Q are the factors that account for decay. So what are they? They are the functions of the ratio of minimum time delay and the ratio of machine's initial short circuit current to its rated value, as well as real power per pair of poles of asynchronous machines. So IEC standard allows you to include or exclude AC decay effect from asynchronous machines in the calculation. So usually we do not have asynchronous machines in our system, so we can exclude it. So it totally depends on you if you want to calculate this decay for the asynchronous machines or not. So this is totally dependent upon the study engineer. Secondly, there is going to be a certain DC component into this. So why this DC component is coming into the system? There is very simple reason for this DC component. As you will see that your entire system is a combination of R and X, and most of the system component is X. X is usually in a larger value as compared to X. So what happens when a current flows through a inductor? So this change, when this huge current flows through a conductor, usually this change does not come quickly in the inductor. This change of the magnetic field does not come very quickly. So due to this change, slow change in DC change, what we happen to get is a DC component in the system. So the DC component of the short circuit current for the minimum delay time of a protective device is calculated based on initial short circuit current and X by R ratio. And what will this depend on? This will depend upon the X by R ratio. So if you have lower X by R, the decay will be less. So if you have higher X by R, the decay will be more. And how it is calculated? It is calculated as calculated by multiplying your I double dash K initial short circuit current by the exponential of X by R. So X by R will play a very important role when identifying DC component of the short circuit calculation. And here F is the system frequency. So if you are talking about a 60 Hz system, then F is going to be 60. If you are talking about a 50 Hz system, F is going to be 50, where T minimum is the minimum delay time of the protective device under concern. So what do we mean the minimum delay time? This is the time which is the minimum possible time in which the circuit breaker can open its poles or it can break its contacts. And X by R is the value at the faulted bus. So now the AC component of fault current close to generator. As we said that when we are going to have fault close to generator, so what happens when a fault comes close to generator? So here, if you see, for a fault close to generator, AC component will decay as shown in the figure. So from the IC standard and from the actual system also, what we see is that when we have a fault close to the generator bus, there is a change of impedance in the system. So how this impedance change? This impedance change in 3 stages. So first, initial is known as the X double dash T or subtransient reactance. So due to this, when this transient phenomena happens, when the short circuit comes is initiated close to the generator bus, a transient phenomena happens, and in this transient phenomena, the impedance of the generator changes with respect to time. And for the first few cycles, the impedance is known as the subtransient reactance, and the current calculated at this moment will be the highest because the impedance is the lowest at this point. So here, this is shown as I double dash T. So this the subtransient current, it will be equal to your voltage at that point divided by the subtransient reactance. Similarly, after few cycles, the generator is going to enter into a transient phase. In this transient phase, the current will be limited by XT dash, and ultimately after many cycles the current is going to be limited by transient synchronous reactance or steady state reactance, which is given by XT. So whenever you are modeling, so from here what we came to know is that whenever we will be modeling our generator in the system for the short circuit calculation, we need to provide 3 kind of impedances: the subtransient reactance, the transient reactance, and the synchronous reactance. And here, from here are both the things. So if you see here, what we have is this is your AC current which is flowing through the system, and this is the DC component which depends upon X by R value. And wherever you are going to part the contact, so this value is decaying. So the longer the time the breaker will take to part the contact, the lower will be the DC component, or in other words, the lower will be the breaking current of the breaker. And this is shown for a single breaker. See how the current is changing. For the first cycle, its value is very high because it is restricted only by the subtransient reactance. But as on after few cycles, you see that the current has reduced, and it has been reduced because now it is being limited by the subtransient reactance, transient reactance only. And here, after many cycles, the current has come to the steady state value because it is being limited by the synchronous reactance only. However, if you go far away from the generator, so in this case, your subtransient reactance will not be will become negligible because you are far away from the system. So hence, any change in x double dash t to xt will not have a big impact in a net total x, since AC component of the fault at a bus does not decay. So if your total reactance of the system at the point of fault is much greater than xt dash, then in this case you are not going to see this decay, and you are going to end up with a short circuit current which is continued or of the same value. So this is exactly what is going to happen in our industrial network, because in industrial network, the generator or the power plants are usually far away from the industrial location, because when we talk about any industrial location, we are talking about something which is towards the distribution side or the transmission side of the system. So in this case, this component will not have a major impact. But if you have a generator within your facility, within your industrial network, then surely you will have this impact of x double d dash, conversion of current from x d double dash to xt dash, or from subtransient reactance to transient reactance. So we also talked about the DC component, and as we said that the decay of the DC component will depend upon R by X value. So how do you get this X by R value or R by X value? This is simple. So when you calculate this Z at the point of fault, so what is Z? Z is a combination of R and X. So you simply divide X value by R value and you get this ratio known as X by R. And what do we call it in short circuit phenomena? We display it by value tau, and tau is equal to L by R or X by R, and tau is equal to X by R divided by omega, and the DC decay component is given by IDC, or the DC current at time t is equal to IDC, t is equal to IDC at t is equal to 0, that is the initial short circuit, multiplied by e raised to power minus t by tau. So by changing the value of tau, by changing the value of X by R, my DC component is going to change. And for the generator, DC decay is based on TA of the generator, where TA is the armature DC current, a short circuit time given in seconds, and if TA is given by the vendor as 0.3 second, then for 50 Hz generator, omega TA or omega tau will be equal to X double D dash by R is equal to 0.3 into 3.1 is equal to 94. And please note that an ETAP, X double D dash by R value needs to be entered, not tau. So whenever we give this X double D dash value by R for a generator, tau will be calculated automatically by the ETAP. So this is how we calculate the. So now at the end, what we'll be needing now, my short circuit current is a combination of a symmetrical AC component and the decaying DC component. So with these two values, I am going to introduce, or IC 60909 introduces a concept of asymmetrical breaking fault current. And what does asymmetrical fault current means? Asymmetrical fault current is the combination of both symmetrical current plus DC current, and this value is going to change with respect to the time where breaker is parting its contact. Welcome to power system analysis using ETAP. In this lecture, we are going to describe the data which is required for ETAP short circuit analysis. So before discussing the data, let us summarize what we have learned so far. So we have basically two types of fault, the balanced faults and the unbalanced fault. Balanced faults are also known as symmetrical faults. Why they are called symmetrical? Because in this the symmetry of the system remains. So such type of fault can be a three-phase grounded fault or three-phase ungrounded fault, in which all the three phases are shorted out together so that the current, the voltage and the impedance of the network remain same even under the fault condition. And the data required for short circuit analysis, for a balanced short circuit analysis, is normally positive sequence data. This is exactly the same data which we normally model for load flow analysis. Unbalanced faults are also known as unsymmetrical faults. In this case, the symmetry of the system does not remain. The example of such faults is single line to ground fault, or line to line fault, or line to ground fault. These are the kind of faults in which only one phase or two of the phases of the network gets affected. Due to this reason, the voltages in all the three phases during the faulty condition does not remain same. So there is no symmetry between all the three phases. So in order to solve such a network, we require three kinds of sequence data: the positive sequence data, the negative sequence data, and the zero sequence data. So whenever, if you want to model a single line to ground fault, or you want to calculate single line to ground fault or unbalanced fault, any kind of unbalanced fault, you will need to model all these three components in ETAP. Similarly, there is another term known as asymmetrical fault. So never confuse asymmetrical fault with symmetrical or unsymmetrical fault. Asymmetrical fault can exist both for three-phase and single line to ground. So in other words, it can exist both for balanced fault and unbalanced fault. But what is asymmetrical fault? It consists of both AC component and DC component in the system. So now let us discuss some data which is required for ETAP analysis, for short circuit analysis in ETAP. So bus data. Some of the data which will be required for short circuit analysis is, you will be requiring nominal kV. When the pre-fault voltage option is set to use nominal kV. So when this option will come into play, that if you select that you want to select the voltages as pre-fault voltages or 1 per unit voltages. So the example was like in hand calculation, when we perform the analysis, we consider the voltages to be nominal or 1 per unit or 100%. So we calculated a short circuit on 1%. But IEC 60909 says in order to get conservative results, it is better to get the results on 110% of the nominal kV voltages. So depending upon the short circuit requirement, you have to input this value. And the percentage voltage, when the pre-fault option is set to use bus voltage. So you can either use percentage voltage, and the type of the bus bar. So this type of the bus bar will be good when you calculate the short circuit. So you can compare the ratings of the bus bar with the short circuit level, whether this bus bar is going to withstand these short circuit currents or not. So that is why this type is required. Even if you do not provide the type in ETAP, it won't matter. So the branch data. Branch data, we have different kind of branches in ETAP. So what are these kind of branches? We have a 3-winding transformer, we have a 2-winding transformer, we have a transmission line, we have a cable, we have a reactor, or we have a impedance. So all these type of equipment are known as branch. So each one of them will have some individual branch data where we provide the values of R, X and B. And these values are either provided in the form of physical parameters. For instance, in the form of cable or transmission line, we select some model from the library and we create a physical cable or a physical transmission line, and based on these library values, R, X and B are calculated. Whereas in the case of reactor and simple impedance, we input R, X and B value. So for this reason, when we are trying to perform short circuit analysis, if you want to perform balanced three-phase short circuit analysis only, we will be only requiring R, X and Y, or R, X and B, and similarly Z. Z can be calculated from these three. Similarly, X by R values will be required in case of transformers. cable and transmission line length and unit will also be important, because ETAP considers the values of R, X and Y or Z in the form of per kilometer or per unit form. So per unit length form. So what do we need to give? That this is okay, this is the value for per unit length, but what if we have this much amount of length, or this much kilometer of length, or this much mile of length? So in this case, this becomes important. For the transformer, rated kV and MVA is important, because when internally it is going to perform short circuit analysis by using per unit method. So for conversion, these MVA and kV will play a very vital role. Base kV and MVA for impedance branches. So if you want to model unbalanced fault or calculate unbalanced faults, then we are going to require zero sequence impedances also for the branches, and transformer winding connections will play a very important role. So we need to provide what kind of transformers we have. Do we have delta Y transformers or YY transformer or star grounded on both sides of transformer? So whatever is the vector group of the transformer, this becomes really important when we are trying to calculate unbalanced short circuit analysis. So for power grid, same. If we want to perform only balanced short circuit analysis, then we need to provide the nominal kV, percentage kV, and the three-phase MVA short circuit and X by R value. And based on MVA short circuit and X by R, ETAP is going to calculate R and X. But if we want to perform the unbalanced short circuit analysis, then we also need to perform single phase MVA short circuit and X by R. If you remember, in load flow analysis as well as our hand calculation, we considered single phase MVA short circuit value same as three phase short circuit value. So in this case, when we are calculating, we may end up with the same, because now this power grid will be providing the same data for both three phase and single phase. But in reality, usually these values are different. So when you are performing this analysis on a real system, make sure that you have these individual values available. So now synchronous data. In case of synchronous data, we require the rated megawatt, kVA and power factor of the generator. Then the impedances are very important, and we talked about these impedances that for generator, the impedances vary over time when a short circuit is initiated on a system and close to generator. So we will be requiring subtransient reactance, which is known as X double dash D or XD double dash, the transient reactance XD dash. Similarly, we will be requiring the X by R ratio with respect to subtransient reactance, then negative sequence X by R, zero sequence X by R, and RA, R2. R2 means zero sequence resistance, and R0 means R2 means negative sequence resistance, and R0 means zero sequence resistance. Then we will be requiring the generator type, the IC exciter type, the if applicable GOST exciter type, RDC for GOST short circuit calculation if we are using GOST type calculation, but usually we use IC type calculation or ANSI type calculation. Then the grounding type and the parameters of the generator itself, then the zero sequence and the negative sequence impedance of the generator. For induction motor data, now we will require some additional data for the induction motor. For the load flow analysis, what did we perform? We gave only the values of the efficiency at different power factor, the poles, values for the induction motor. But now one of the most important thing, apart from this rated kV, rated kilowatt or HP and kV of the motor, what we will be requiring? We will be requiring the X by R plus one of the following for ANSI short circuit calculation. So if you are calculating based on ANSI, you will be requiring X by R. So this X by R can also be calculated based on the locked rotor current. So if we provide the locked rotor current, then ETAP can automatically calculate, convert this locked rotor current into the reactance of the system. And similarly, if we want to perform unbalanced short circuit analysis, then some additional data will be required. What is this additional data? The grounding type of the motor, the zero sequence value and the negative sequence value. Please note that whenever you have a rotating machine or a rotating device, for instance generator or a motor, In such cases, you will always have a negative sequence component in the system. And when you have negative sequence component in the system, you have to provide negative sequence impedance. Whereas, in case of static equipment like transformer, impedance, transmission line, cable, since there is no rotating part, therefore there will be no negative sequence component. Such system only contain positive sequence component and zero sequence component. And zero sequence component will only come when there is grounding involved in the system. And for the lump load data, if you remember, for the lump load data, we model our system as a combination of motor load and static load. So if we have motor load in our system, it means that motor load is due to the motor available. Although we are not modeling the motor, but we are telling ETAP that we have certain amount of or certain percentage of motor load available in the system. So if we have motor load in the system, at least we need to provide the percentage locked rotary current so that it can be converted into its respective impedance and the X by R values. So for lump data, we need to provide the percentage of the motor load, and for that percentage of motor load, what is my percentage locked rotor current? In the end, this is the basic data which was required, which we discussed. Now, apart from that, we have some circuit breakers or switchgear in our system. So what we want to do is we want to model these circuit breakers, these high voltage circuit breakers or low voltage circuit breakers in the system as well. Why do we want to model them? For the sake of short circuit calculation, they will not be required. But when you provide these kind of data, it becomes easier for you to compare. For instance, you have some particular kind of a circuit breaker available in your system, or you are planning to procure a certain or this circuit breaker from a certain manufacturer. So you want to make sure that when I have short circuit in my system, the data provided by this manufacturer for a certain circuit breaker, is it compatible with the short circuit levels I have in my system? So for this reason, you can provide this value. But if you are only interested in the short circuit current levels, in the levels you're not interested in getting the requirement of the circuit breaker, then there is no need to model this data. So, but let us see, for your information, what kind of data we require. So we require the maximum kV of the circuit breaker, the rated interruption capacity, the maximum interruption capacity, C and L RMS, and the crest values. Similarly, the standard and the cycle. So these are the different kind of data we require. Similarly, if we have IEC standard type circuit breaker, in this case we have to provide the rated voltage, the minimum delay, so delay time in second, the peak current, AC breaking current. This is the same current where contacts are going to part when some DC current is going to be there. So I threshold or short circuit withstand current, TK user defined duration of short circuit withstand current, the rated duration of short circuit withstand current. So we have to provide this withstand capability for the generator, and this will be then this breaking current and this rated, and the maximum will be for this circuit breaker will be compared against the short circuit value which we have calculated, and from there we can compare. Okay, fine, my does my A circuit asymmetrical rating gets violated? So if it is getting violated, it means that I have a problem, I cannot use this breaker. Or my symmetrical rating is getting violated. If symmetrical is getting violated, fine, it again means that I need to change the type of the breaker, or I need to get a higher capacity breaker. Same is for the low voltage circuit breaker. So in this case, again, what do we have to provide? We have to provide the type. What kind of the type is breaker? It is a molded case. Is it an insulated case? What type is it? Then the rated kV of the breaker, the interrupting capability of the breaker, and the test power factor, the power factor at which this breaker has been tested. And in case we want to use IC standard of circuit breaker, then we have to provide the type, the rated kV, again the minimum delay, the peak current. This is the same, these are the same terminologies which we discussed in IC 609, the breaking current, the threshold, and the withstand capabilities. Welcome to power system analysis using ETAP. In this lecture, we are going to see how we can perform IC 60909 type of short circuit calculation using ETAP. So now that we have input all the data, like load flow analysis, our next step will be to perform short circuit analysis. So for this, the type of selections we need are this. So we can select the standard type of standard we want to use for calculation. So we are considering IC 60909. We'll be selecting IC from here. For the short circuit current, we can either select maximum user defined C factor or minimum C factor. So usually maximum C factor is used. What does maximum C factor says? The maximum C factor says that if you want to perform short circuit analysis, you can use the value as 1.1 per unit. So because I is equal to V by R, and higher the value of V, the more conservative or higher will be the value of short circuit current. Different type of calculation methods we can use. The method A, method B, or method C. We have already discussed these methods in details. Similarly, breaking kiloampere. So do we want to consider the DC component, DC decay, or we do not? Based on this, you can select this value. Similarly, zero sequence model. So for the zero sequence, do we want to consider the branch impedance and static load? Usually we do not consider this. Based on your requirement, you can select whatever you want from here. So two types of short circuits are very important for us, because we want to see the short circuit levels of either extreme, the maximum short circuit level in a network and the minimum short circuit level in a network. So what is maximum short circuit and how it is calculated using ETAP, or what should be the different type of assumptions or considerations which needs to be considered. So for maximum short circuit currents, voltage factor Cmax according to table 1 of IC 60909 shall be applied for the calculation of maximum short circuit current. And we have to choose such a configuration which will give us the maximum short circuit current. Now, what is short circuit? Short circuit is calculated by lumping or calculating the equivalent impedance, right? So how can we get maximum current? Maximum current will happen when we will have minimum impedance. And how can we get minimum impedance? When we have multiple equipments in parallel. So if you want to get maximum current, you need to configure your network in such a way that the impedance of the network is reduced. For instance, if you have two transformers, operate both of them in parallel. This will reduce the equivalent impedance of both the transformers. Similarly, if you have any generation in your system, you have 2 or 3 generating units in your system, run them all so that maximum contribution can come from them. Similarly, include the motor contribution to the fault so that fault current is also increased. And the resistance of the overhead lines and cables are to be introduced at a temperature of 20 degrees. So lower will be the temperature, lower will be the impedance. So based on this, using these different types of assumptions, you can increase the fault current in your system. And then what you can use during the selection, use maximum so that 1.1 per unit is considered. For the minimum short circuit current, the Cmain value according to IC 60909 shall be applied. So this is one of the thing you have to do. The second thing to do is, or the second assumption you can do is, choose the system configuration in which the contribution of the fault is reduced. How you can do this? As we talked, if we have two transformers parallel, this time use only one transformer so that your equivalent impedance increases. Similarly, if you have 2 or 3 power grids in your system, choose the one with the highest amount of R and X value so that you can get you will have maximum resistance or limitation to the short circuit. So by selecting such a network, and if you have the cogeneration in your system, just reduce the cogeneration to 0 or switch it off. Also, make the motor contribution 0. So without taking the motor contribution, the fault current will eventually reduce. And similarly, at the end, the resistance RL of overhead lines and cables are to be introduced at a higher temperature. So by using at a higher temperature, when the temperature is increased, resistance will increase. When the resistance will increase, the short circuit current passing through the equipment will decrease. And for this purpose, what you can do is you can use minimum, in which exclude duty cycle. The duty cycle will be excluded and you will get the minimum currents available. And this is the typical table which is used. So if you want to calculate maximum short circuit current as per IC 60909 standards, for 100 volt to 1000 volt of system, you can use 1.05. However, if you have medium voltage or high voltage, you have to use 1.1 per unit of the voltages. For the minimum short circuit level for lower voltages, you have to use 0.95. And for medium and high voltages, you have to use 1 per unit. And one thing you need to make sure is that first you have selected this value, the maximum or minimum value. Configuration, system configuration will play a very vital role. So make sure that you select that type of system configuration which can either give you maximum or minimum short circuit. Welcome to the demonstration video of short circuit analysis using IC 60909 standard in ETAP. So we are going to perform the short circuit analysis on the same network which we used for load flow analysis. So if you see, when we performed load flow analysis, we configured two systems. One was the normal operating condition, in which we had some of the equipment in normal standby mode. Whereas we also performed load flow analysis on the maximum operating condition, in which every equipment within the industrial network was in on position or closed position. So everything was connected to the system. For short circuit analysis, we need to perform two kinds of analysis. One is for the maximum fault current and one is for the minimum fault current. When we talk about maximum fault current, we say that in maximum fault current, we have to select the configuration of the network with the help of which we can get the maximum current. And how can you get the maximum current? Maximum current will only come when you have a system configuration in which the impedance of the network is reduced. And one of the easiest way to reduce the system impedance is to have multiple parallel paths. So for instance, if we see here, we have two power grids. So if these two are connected, the equivalent impedance will be much less. Similarly, these two transformers in parallel will have much less impedance. For instance, if the impedance is 9% here and 9% here, it means that the equivalent impedance will only be 4.5%. 9% divided by 2. Same goes for these transformers and same goes for these transformers. So if we use this maximum configuration, it means that we are going to get the maximum fault current in this case. And other important thing here is that if we see our power grid and we go to short circuit, here we have modeled the same short circuit for the 3-phase as well as single phase. So it means that if we will be using this system to calculate single line to ground fault or unbalanced fault, we may not be able to get this. The reason is simple, because we do not have modeled the power grid for the single line to ground fault or unbalanced fault. But if we see other equipment, for instance transmission line, and if we go to the impedance of this transmission line, here we have positive sequence and negative sequence separately. So this means that although we do not have modeled a power grid for the single line to ground fault, but we can get single line to ground fault with respect to transmission line data. And same goes for the cable data. So if I go to cable data and impedance, we see here we have a zero sequence different than positive sequence. So it means that we will be able to get different short circuit level for unbalanced fault because we have modeled it properly. So even if we use this same model for a single line to ground fault or unbalanced fault, we will get some results. But for now, as we discussed, that in an industrial network, 3-phase short circuit is far more worse as compared to single line to ground fault. So we will be emphasizing more on 3-phase short circuit. So We have this configuration available for the maximum. This is exactly what we want. So we are going to first perform the short circuit analysis on this maximum configuration so that we can get maximum fault current. So in order to perform short circuit, what do we have to do? We have to go to this tab now. Before, for load flow analysis, we were using this PQ load flow tab. Now for short circuit analysis, we have to use this short circuit analysis tab. When I click on this tab, now my network configuration has been selected for this. So this is my network configuration. Now let us see what kind of configuration I have. So if I go to edit case study, you see here short circuit. So my case name is short circuit. So I selected this. If I go to case study, I can give another name if I want. I can add new names into this, but for now I want to keep the same name. Now I need to select on which buses I need the short circuit. So I need the short circuit at main bus A and B. So let me select main bus A, and what is the name of the other? Main bus 2. Okay, so we can select main bus A and main bus 2, and then we need on bus A and B. So bus A and bus B, then bus 1A, 1B, bus 2A, 2B. And because these were my main buses, so I'm trying to see the short circuit on my main buses. You can select whatever you want. Similarly, the standard. So for here, if you see in my ETAP 19.1, I have three type of standards. This IC standard, ANSI standard, and GOST standard. Because we discussed IEC standard, so I will be performing using IC 60909 standard. So what I am interested in, I'm in maximum short circuit, so I'm going to select maximum short circuit. What will happen in maximum? The C factor is going to be considered as 1.1 for the medium and HV buses. So Cmax for Z adjustment. Do I have adjustment? I am not taking any adjustment. And the calculation method for X by R for peak kiloampere, I am using method C. And these are the other configurations which I will remain, which I am going to keep them as it is. So for the adjustment, do I want change in the transformer impedance? You can use this. If you have used this tolerance in level in your different equipment, then you will be able to use this. But since I do not have used any tolerance, so I cannot, I can just uncheck it. Or if you want to make sure that you want to calculate the exact impedance, whatever you have given in your equipment, so you can simply uncheck these values. Similarly for alert is going to tell me my alert based on the equipment capability. But if I press OK here, if you see, if I double click on my bus and if I go on my rating, I haven't provided any kind of rating for here. I haven't provided any bracing rating for here. See, so asymmetrical 0 kiloampere. So I haven't provided what kind of kiloampere I can have on my bus bar. So this is exactly what I want from the planning stage. What I want to make sure is that what should be the capability of number one, my buses, and secondly, my switchgear or circuit breaker. So if you see the circuit breaker here you see 0 kiloampere, 5 cycles 0 kiloampere. So what I have done is I haven't included any kind of requirement for the circuit breakers as well. So I do not know, because this is the planning stage and I do not know what will be the exact short circuit current in my system. So I do not know what kind of capability, device capability I should select. So that is the exactly reason why I'm performing short circuit analysis. So once I am done with this and I know, you see the colors has changed for the buses where I want to perform short circuit analysis. Now what I simply have to do, I simply have to perform this duty. So if I run 3-phase device duty, when I click on this, because this was on prompt, so it is asking what should be the name of my file. So I am performing maximum short circuit. So let us select the name of the file as maximum short circuit and press OK. Now ETAP is going to do its work, solve the network, and there you go. So here we have the result, and if we see the result here, so what do we have? At the main bus, at the 132 kV bus, my short circuit level is 11.218 kiloampere. Similarly, at my 13.8 kV bus, my short circuit level is 29.146 kiloampere. At my 4.16 kV bus, my short circuit level is 11.787 kiloampere, and at my LV bus, which is my 0.48 kV bus, my short circuit level is 34.532 kiloampere. So this means that if I want to select the bus bar, so at least my bus bar should be able to withstand this much amount of short circuit current. And you can also see that I am getting the contributions. So ETAP tells you these contributions also. So the contribution coming from the grid, power grid, it is being shown here. Similarly, the contribution coming from each motor or my lump load. Because why would I get the contribution from lump load? Because my lump load is a combination of motor load and static load. So the motor load, for the motor load, we provided some kind of locked rotor current. So if I go to my short circuit, see, I have provided some kind of locked rotor current. Although this value is as per the actual value, or what do we call the default value of the ETAP. So this fault current is based on the default value. But if you have the original value of the locked rotor current, you can use the similar value. Similarly, for each type of motor, if I double click on this motor and if I go on to the impedance, here you see the locked rotor current is there. So this is taken up as a default. So when I selected my nameplate of my motor, I got this value. So if you know the exact value, you can use the exact value. But however, based on this, I am getting some fault current contribution from each motor, and see, wherever I have static load, I do not get any contribution. If you see from here also, this server rack A or server rack B, because it was connected to a static load, so no contribution is there. But receptacles A and B, which are connected to a lump load, I'm getting some contribution. Similarly, light A and B, no contribution is there. So this way, now we know from here that this is the kind of short circuit contribution we have from each of the bus. So if I want to use a switch gear or procure a switch gear, what kind of switch gear I need? For 132 kV, my switch gear should be at least more than 12 kiloampere or even more than this. So what do we usually do? We usually tend to keep some kind of percentage. So at least 10% should be kept. So what do we mean by 10%? So 11.21 multiplied by 1.1. So whatever the value you get from this is at least should be your device capability. So similarly, for 13.8 kV bus, I should get a switch gear of at least 29.146 into 1.1 is equal to 32. So my switch gear should at least be able to withstand 32 kiloampere. So I should get at least 40 kiloampere breaker, because 25 kiloampere breaker won't work here. But here 25 kiloampere breaker will be enough. Here also on 4.16 kV bus, my 25 kiloampere will be okay. But here I should at least have 40 kiloampere on the LV bus. So this way you can select the rating or the protective capability or the short circuit withstand capability of your switch gear. Welcome back to the demonstration video of short circuit analysis using IC 60909 standard in ETAP. Now that we have calculated the short circuit level, the three-phase duty cycle for the network, now what we can do is we can adjust the ratings of our circuit breakers. So how we can do that? Let us see. So let me go to this first breaker, which is CB line 1. So when I go to the rating, I have this library available. So I'm using ANSI standard. I can use IC standard as well. So let us select IC standard here, and let us go to the library and select a breaker from this. So we have different type of breakers: ABB, Alstom, GE, Hyundai, Merlin, Siemens. So whatever breaker you want to use. So what kind of breaker I'm looking for? I'm looking for a 132 kV breaker, right? Because at least it should be 132 kV. So I do not have the breaker available rated kV for this. So let me check Alstom. Yeah, at Alstom I have this breaker. So here are the different capabilities. So the making capability and the AC braking is 31.5 kiloampere. So just to give you, and I have only one 145 kV breaker. There is no 132 kV breaker. So let us see in GE. What do we have in GE? We do not have any high voltage breaker in GE. Let us see Hyundai. All the rated kV are up to 12 and 17. So 24. So nothing here. So let us check Merlin. Nothing. So let us check Siemens. So 145. Yeah, we have. So making capability is. So what we can do is let us select this breaker because it has a AC braking capability of 40 kiloampere. So this seems good to me. So I select this Siemens 145.3 AP1, and when I press OK, see the data has been updated for this as per the actual Siemens circuit breaker. So I select this. This has been tested for 45-second time constant. So braking will be done at 45. So I select this and press OK. And this is done. Similarly, I go to this. I will go to rating. I select IC. I go to library. I go to Siemens. And once again, I'm going to select this 145 kiloampere breaker, and when I press OK, again the same is selected. When I press OK, so I have selected this breaker. Same will go for these two breakers. So I go to this breaker, rating, IC, library, Siemens. So 145 AC, press OK. OK. Same goes for this. For my 13.8 kV, my short circuit level was 29.146. So I need a kind of a breaker which should have a capability more than at least 29 kiloampere, or 29 multiplied by 1.1 is around 132. So at least 32 kiloampere. So for this, what I'm going to select, I'm going to click on this. Then I'm going on the rating, IC standard. I go to library. Let us select some ABB breaker with the I can use. So I have a 13.8. So what I can do is I can use my switch gear. I can select 15 kiloampere rated kV. So 15 kiloampere will work for me. 13 won't work because it is less. I can work with 17.5. So let us, what do we have here in Alstom? So in Alstom we have big breakers, and here 15 kV breaker is there with a capability of 25 kiloampere and 50 kiloampere. So 25 kiloampere won't work for me, so I will have to use 50 kiloampere breaker. So when I press OK and OK, I have selected this breaker. So what is the name of this breaker? If I see again rating, so I have Alstom HWX model. So I can use the same for here. Reliability, rating, go to standard, Alstom, like this. In the same way, Now you know how to select the breaker rating. So you can go ahead and select different kind of breaker ratings for each of the breaker as per your need. And then we will continue with the analysis. So now that we have added the different breaker duty cycle for each one, for instance for LV, we have used this G electric FCH 0.5 kiloampere maximum with 36 kiloampere 3-phase. So in this way you can select different values. So once we are done with this, let us perform this duty cycle or the IC609 again. And when I perform this, perform the analysis. Let's see. So we have the same short circuit levels available. So let us go to this alert view and see. Now this time we are getting the alert because we added some values. So here, so incomer rating is 75.6 kiloampere and it is operating at 76.19. So it is a little bit loaded. So I need to change this circuit breaker. Other than that, if I go to my report manager and I go to the summary and I select summary and press OK. So here we have a summary generated. So now you see, for each bus bar, whatever is the circuit breaker connected to it, it is telling. So the making capacity here is 65 and IB symmetrical is 25 kiloampere, asymmetrical is 26 and IDC is 9.32. And from the short circuit value, what I'm getting 11.87. So everything seems within the limit, and where there is a change, where there is more, so it is being told by the ETAP. So this way you can calculate short circuit analysis. Welcome back to demonstration video of short circuit analysis using IEC 60909 standard in ETAP. Now that we are done with the maximum short circuit level, we can now calculate minimum short circuit level. For calculating minimum short circuit level, we have to create a new operating condition or the new configuration of the system. So for creating a new configuration, what do? We go to this edit mode. And now what we have to create is, we have to create a new configuration. So I will go to the configuration manager, click on configuration manager. My configuration manager has opened and I am going to create a new configuration manager. And what is the name? This time this is going to be minimum. And when I press OK, so now I have a new configuration available. So what about this configuration? If you see here, we have two power grids. One is with a short circuit capacity of 1250 MVA short circuit and the other one is with a short circuit capacity of 1600 MVA short circuit. So surely the power grid with a capacity of 1250 MVA short circuit is the weaker one. So when we are performing minimum, we need the higher impedances. If you see, the impedance here is 0.22484 and here this is. So what I'm going to do is, I'm going to select my minimum short circuit level here, which has the least short circuit level. So what I can do now is, I will simply go to the CB line 2 and let us make this one open. So where is my CB line 2? Here for the minimum, this should be open. So I'm going to make this open. So moving on, what do I have here? So here if you see, I have two transformers. So what I can do is, in order to calculate the maximum short circuit, I can minimum short circuit, what I can do is, I can shut down one transformer. So in order to shut down this transformer, I have to make this TF2 HVCB and TF2 incomer as open. So I will go here, I will search for my circuit breaker which I am looking for. So TF2 HVCB, this should be open. and TF2 incomer, this should also be open. So in the same way, moving on, let me press OK. So in the same way, moving on, what I can do is I can switch this transformer and this transformer off as well, so that I have the maximum possible impedance available in the system. So I'm gonna go ahead and do it. You can do the same, and then we will perform minimum short circuit. So now I have adjusted the configuration. To give you another tip on ETAP and making your life easy, if you go to configuration manager, you have this selection. So if you select all AC element, you see all the AC elements in your system are coming here. And if you want to select only circuit breakers, what you can do, you can select circuit breakers. So this way, all the other equipment is going to be filtered out and your life is going to become easy. So what we have done for HVCB, we have opened some of the breakers. Like we have opened transformer T2, we have opened transformer T3, and we have opened transformer T6. And because T6 has LV side breaker also, so when I go to see, you see T6 incomer is open. So this way you can select the configuration. So we are done with the configuration. This is my maximum configuration in which nothing is open. So if I select from here maximum, this configuration, and I select minimum, see, I have this new configuration where this power grid 2 is open, my transformer T2 is open, my transformer T3 is open, and my transformer T6 is open. So with this configuration, what I can do next is perform my minimum short circuit. So how can I calculate minimum short circuit current? So once again, I'm going to go to short circuit, and again I'm going to select this edit case study. This time in standard, IC standard, but this time I am interested in minimum. So I'm excluding duty cycle and I want the minimum, and the design category I am using. So same method C, everything else same for me. And when I press OK, so I have this new configuration selected. Now because I want another report for this, so I am going to go to this list output report. From here I am going to select prompt again, so that when this simulation is performed, I get the minimum short circuit. So for this I am going to perform this IC 60909, because now I am not calculating the duty, so I am not getting this value. So IC 60909, so this is going to be minimum underscore short circuit. And when I press OK, so here I have. And how do I want to see the results? You can simply go to this display option, and I am looking for 3-phase results. Yeah, so I have selected 3-phase for AC, so different options are there. So for the results, I am more interested in 3-phase, so let me select 3-phase here and press OK. Why it is showing 0 kV? Because it is now. What has happened? If you see here, this is my magnitude and this is my angle. I am more interested in the magnitude, and if you see here, before the maximum short circuit current was 11.218, but in this case I am only getting 4.608. Similarly, at my 13.8 kV level, my short circuit level was around 29 kiloampere. So now it is 10.166 kiloampere. For bus A or 4.16 level, my short circuit level was around 11 kiloampere. Now it is 4.1. And for 0.48 or LV bus, now this is 12.28. So this way you can get. And now ETAP has calculated, because I use 60909, so it has calculated other short circuit levels for me as well. If I want to see them, I can go to this display option. Let us select line to ground fault. And what do I want to see in? So I want to see the phase values, or I want to see the total fault current. So I am more interested in the total fault current. I can also get the sequence currents, but let's see what is the total fault current. And when I press OK, so there you go. So this is my single line to ground fault. And I can select line to line fault in the same way, line to line to ground in the same way, or I can select three phase. So if I select three phase, I press OK. So this is my three phase. So this is how you can perform short circuit analysis for different configurations and for the different types of fault. Welcome to power system analysis using ETAP. In this lecture, we are going to introduce power system stability. Traditionally, power system stability was exclusive to utilities only. The cogenerations or small power producers were considered as a load of utility only. So the impact of these was not a bigger problem for the utility itself. Now with this increasing number of industrial and commercial facilities, the installed local generation is also increasing because there are several cogeneration plants like oil and gas power plants or these oil and gas utilities where you have certain amount of gas available with which you can produce some generation. Similarly, you have these sugar industry or some other kind of industry which have these some kind of exothermic reaction, and they use the heat from these exothermic reactions to create some local generation. So with this increased local generation, the role of cogeneration companies and other power plants with on-site generation maintaining system stability is becoming the new area of interest for power system studies. So when a cogeneration plant is connected to the transmission grid, it changes the system configuration as well as the power flow pattern. This may result in stability problems both in the plant and the supply of the utility. So this is the reason why transient stability is now becoming more and more predominant, and even for an industrial or a commercial facility with some local generation available, it is important to perform these transient stability analysis. By definition, power system stability is the ability of an electric system to remain in synchronism or in equilibrium when subjected to a certain disturbance. So what are these disturbances? These disturbances can be of different kind. This disturbance can be in the form of a three-phase fault, or this disturbance can be in the form of loss of generation or loss of load, or this can be in the form of starting of a very large motor. So these type of problem can lead to power system stability. So when we classify this power system stability, we have usually three kind of stability problems: the rotor angle stability, the frequency stability, and the voltage stability. Rotor angle stability can be further divided into two types: the transient stability and the small disturbance angle stability. And both of these are short-term problems. Whereas frequency stability can either be a short-term problem or a long-term problem. So what can be a type of a long-term stability problem? That a load is getting increased slowly into the network. So you started one motor in your system, then after few seconds you started second motor, and step by step you are increasing the load on the system. So this will start to cause some load and generation imbalance, and due to this imbalance you may feel the change in frequency. And what is the short term? Loss of a generation, loss of a load instantly in the system. That will result in the short term frequency stability. So voltage stability can also be divided into large disturbance voltage stability or small disturbance voltage stability, and that can be in the form of a long term or short term. So typically, what are we looking in a stability? So here is an example. So here you can see system is operating normally, then it is subjected to some disturbance. Then following the disturbance, the system tries to find a stable point. Here you can see that there are some oscillation in the system, and ultimately the system is stabilizing itself on a certain point. In this blue curve you can see the system is getting stabilized, whereas in this red dotted curve you can see the oscillations are still there in the system. So these oscillations mean that the system has less dynamic stability as compared to the one in the blue curve. So for a typical power system stability phenomena, the time of the simulation, or the time frame in which we are working is usually in milliseconds. So from millisecond to second phenomena is usually where we will be working on when we work with the transient stability problem. For this modeling or studying the transient stability, now the dynamics of the motor will become important. And as we said that we are looking for the cogeneration. When a certain system has cogeneration in its facility, then we will be seeing this stability problem. So for studying the stability problem, we have to model the generator in detail, in the dynamic detail. So there are 4 kind of models which are responsible for dynamically modeling the system. So let us see in the form of these 2 things first. So what is basically a generator in reality? So you have some stator, which is the stationary part of the system, and it has 3 sets of winding: the phase A winding, the phase B winding, and the phase C winding, which are 20 degree at a displacement of 120 degree from each other. Then you have a rotor. This rotor is connected to the prime mover with the help of some shaft, and there is some winding on this rotor which is known as the field winding or the rotor winding, and the rotor windings are supplied with the help of some DC supply. So what happens? We provide this DC supply to the rotor, and then we rotate this rotor with the help of some prime mover, and this creates magnetic field. So current passing through the conductor of this winding will create a magnetic field, and when this magnetic field will cut the 3 phases of the 3 set of windings, rotating EMF will be induced, which will be 120 degree out of phase from each other, and we are going to get the AC supply out of it. So in other words, how can we represent this? This is represented with the help of one generator, the machine model, where we are going to provide the reactances of the stator. The reactances of the stator is represented by this synchronous generator here, which is now connected to the external electrical system, and from there we are going to take a feedback to this automatic voltage regulator, and we are going to provide, if you remember that for the load flow analysis, what we were doing, we were modeling our power system or the power grid in the form of swing bus, but we also had this voltage control possibility available. So this voltage control possibility is exactly the same. What we are trying to tell the generator that please maintain the voltage at this level. So it is going to see what is the actual voltage at the terminal and what are the reference voltage, and based on these 2 it is going to adjust its DC current so that it can increase or decrease the EMF induced, thereby adjusting the voltages of this output. And this exciter is then this exciter and this synchronous generator, then they are connected to the prime mover with the help of this shaft, and the prime mover is again connected to the governor. And what will this governor do? This governor will actually work on this how much active power you want out of this generator. So if you want to reduce the power output, what you are going to do, you are going to reduce the fuel input. By reducing the fuel input, the speed of the turbine is going to reduce, and then the power output is going to reduce. So this way, so now if we want to model an electrical generator in our transient stability analysis, what do we have to do? We have to provide at least 3 kind of models. Number 1 is the generator model or the machine model, which will be in the form of equivalent model, transient model, and subtransient model. So we have to provide all the 3 impedances into this, and then we have to provide the inertia of this coupling also. Then we have to provide this exciter model, so that in when this dynamics is performed, we can tell the generator, okay fine, your voltages are changing at the terminal voltage, please maintain this kind of voltages. Then we will be modeling the prime mover and the speed governor, and then there is a secondary control to this exciter, which is known as power system stabilizer, which is used in this long-term stability or small signal stability problems, which we will not be discussing in detail right now. But this is what you require. So whenever you are trying to study transient stability, you need at least 3 kind of models: the generator model or the machine model, the exciter model, and the governor model. So if you have these three models, you can study any kind of transient stability problem. Welcome to power system analysis using ETAP. In this lecture, we are going to review basics of power system stability. What is transient stability? As we discussed before, transient stability is the ability of the system to maintain synchronism on equilibrium when subjected to a severe disturbance. And what can be these type of disturbances? This disturbance can be in the form of a three-phase fault on a transmission line or a transformer on a bus, loss of generation, loss of load. Once the system is subjected to this disturbance, the response of the system resolves around the large excursion of generator rotor angles influenced by the non-linear power angle relationship. So the stability depends on both the initial operating state of the system and the severity of the disturbance. Post-disturbance steady state condition usually differ from the pre-disturbance condition. Why is that? For instance, you had two transmission lines in your system. So following the disturbance, one of the transmission line tripped. So now pre-fault condition, you had two transmission lines. In post-fault condition, you have only one transmission line. So in this way, your post-disturbance steady state operating condition will differ from your pre-disturbance operating condition. Now to get the basic concept or the basic review of this transient stability, let us take a very simple example. What do we have here? We have a generator which is connected to the system with the help of a step-up transformer, generator step-up transformer, and then it is connected to the infinite grid or the system or the power grid with the help of two transmission lines having impedance of X1 and X2. Here we are considering the classical model of the generator. By the classical model we mean we are not interested with the impedance or the reactances of the generator. We are only interested with the inertia of the generator, and that's it. Nothing else. Only inertia of the generator, nothing else. So with this, how this transient stability or how this generator transient stability is impacted by the disturbance. To understand the concept, first of all, we need to review the basic power flow equation. So what does the basic power flow equation says? The basic power flow equation says that the power flow from the generator to the infinite grid through the network is dependent upon V1 into V2 divided by X into sine of delta, where V1 is the sending end voltage, V2 is the receiving end voltage, and X is the impedance of the network between sending end and receiving end, whereas sine delta is the angle between these two voltage sources or between these two buses. So with the stator resistance neglected, PE represents the air gap power as well as the terminal power. So now what we are doing here, to find the equivalent, this is same as finding the equivalent impedance for the short circuit analysis. Here these two are in parallel, so we are going to calculate the equivalent of these two parallel. Then it is going to be added with the this XTR and XT dash, which is the impedance of the transient impedance of the generator, and this whole becomes XT. So now my formula will become E dash EB E dash V1 V2. So E dash EB divided by X of T, the total equivalent impedance, and the sine of delta, the angle between the two. To further take this concept, let us discuss power angle relationship. Now what do we have? We have this formula V1 V2 divided by X of T into sine of delta. Let us plot this sine delta for different values. So starting from 0 to 180 degree, we plot different values, assuming V1 and V2 as constant and X certain value of X. With this value we can plot this, and this is our impedance. So here this curve number 1 is with the PE with both circuit in service, and this curve number 2 is P electrical or the power flow with circuit number 2 out of service. So why there is the difference between the electrical power flow? The difference is there because in this curve we have two transmission lines in parallel. So impedance is going to be something different. But when you switch off one transmission line, the impedance of the system is going to increase. So with the increase in the system impedance, the power flowing through this system will decrease because V1, V2 divided by X. We have this X quantity in the denominator. That is why. So this is both the curves shows. So now what happens to the angle? So if we assume that this curve shows P electrical and here this shows P mechanical, and if we are operating at point A where P electrical is equal to P mechanical, we will have point A. But what happens when one of the line is tripped or switched off? Now due to change in impedance, my power curve will change, and with this power curve, in order to maintain the same P mechanical equal to P electrical, I need to change my power angle. So this is how my angle is changing with the changing power or the changing impedance of the network. So what do we understand from here? That higher the reactance, higher delta is required to transmit the same amount of power. Now this gives rise to the swing equation because transient stability is governed by this swing equation. So thus, what is this swing equation telling me? This swing equation is telling me that in order to maintain stability of the system, we need to know the four quantities. Number one, the stability will be there when P mechanical minus P electrical is equal to 0. And what does this difference between P electrical and P mechanical will be dependent upon? This will be dependent upon the system inertia, H, and delta, the angle between the two. So when we say angular stability, we are actually talking about this delta. So this delta will be dependent upon the difference between the P electrical and P mechanical in the system and inertia of the system. So higher the inertia, the more it will be difficult to, or the more the system will have stability, this angular stability, and less the inertia, so less will be this angular stability in the system. Now to understand this concept of angular stability, let us take an example. This is the same example. My generator is connected to the system with the help of these two transmission lines. So now what is happening? Now here we are drawing three curves, same three electrical curve. This curve number 1 is the pre-fault condition in which both these two circuits are connected. And then this curve is known as this during fault curve. And what is happening when fault comes on the system? What will actually happen? The voltages are going to get depressed. Due to this drop in voltages, what I am going to have, my P electrical is going to decrease. And when the fault is cleared, the voltages will return back to their pre-fault condition, but this fault will cause this line to trip. And due to the tripping of this line, my impedance is going to change. So now the post-fault condition, I will have power flow or P electrical with this curve. So now what happens in the system? Let us go step by step. So in the pre-fault condition, what is happening? So let us discuss the stable condition first. So what is happening here? So both circuits in service, P electrical is equal to P mechanical and the angle is equal to delta naught, my actual angle. So I am operating at point A. At this point, my P electrical is equal to P mechanical and I am operating at delta naught. So this is the point in the network where delta naught is there. So during fault, what will happen? The operating point moves from A to B. So why this moves from A to B? Because due to this fault, instantly this P electrical becomes very less or even can reach 0 in case of a three-phase fault. So what is happening here? Now my P electrical just shifted from point A to point B. Here it has shifted to point B. But inertia prevents delta from changing power instantly. But still my P mechanical will take some time because I have this shaft connecting my P electrical or the generator with the turbine. So the shaft speed will take some time to get reduced. So what is happening? Now I have a difference between P electrical and P mechanical. As a result of this, my P mechanical becomes greater than P electrical because I am still operating at this point and I am trying to reduce this value. But at the same time, my P electrical has instantly dropped to this point B. So this P mechanical becomes greater than P electrical. As a result, rotor accelerates to the operating point C. So what is happening here? My rotor accelerates to this point C. So now rotor is trying to here reduce its value, but during reduction it is trying to find an operating point where it can make P electrical equal to P mechanical. So my delta has increased to delta C1 and I have reached this point. So now during post fault, what will happen? The faulted circuit is stripped, operating point shifts to D. So I have reached this point where I am trying to find my P electrical equal to P mechanical. I am still trying to figure out what should be my point when the fault is cleared. And after the clearance of the fault, what will happen? My system will try to increase from this point. Instantly my P electrical will increase to point D. So it has reached this point D. So after reaching this point D, what is going to happen? My P electrical becomes greater than P mechanical because P electrical was reducing and it was trying to find some point close to C. But now as my P electrical increases, now this P electrical becomes greater than P mechanical. So now what is going to happen? The rotor will try to decelerate itself. It is going to reduce. So it will see, okay, fine. Now P electrical is more, P mechanical is less. So I need to reduce. Okay, reduce. So the opposite is happening now. The rotor speed is greater than omega naught and the delta increases. So now due to this change, this inertia in the system, the rotor speed is still greater because it is still operating at this point. So it becomes greater than the omega naught or my original speed and the delta increases. So it goes on increasing and reaches to this point delta M. So the operating point moves from D to E such that A1 is equal to A2. And in order to find an equilibrium between P electrical and P mechanical, so I reach this point. Now at E, speed becomes equal to omega naught and delta is equal to delta M. So I am operating at this point and I am trying to find equilibrium here, and P electrical is still greater than P mechanical. So the rotor decelerates and speed goes below omega naught. Now when it comes this point, I have the difference in speed. So my rotor is still decelerating and it decelerates to a point that it becomes even lesser than my omega naught or normal speed or nominal speed. So delta decreases and the operating point retracts from E to D. So in order to find, so it reduces back to, so it says, okay, fine, I am trying to reduce. So now I need to find a point here. So it retreats its back and it goes to point D. So with no damping, rotor continues to oscillate and the P mechanical and P electrical will try to find an equilibrium position and will try to move back and forth between point D and E until some point is reached. And if this no point is reached, then we are going to have this oscillatory behavior in my system. Although it is unstable condition, but I am seeing oscillations in my system. So I have some kind of instability in my system, but it is not causing the system to go out of step, but it is maintaining the system with some oscillations. In case of unstable position, when the operating point E reaches the kinetic energy gained during the accelerating period has not yet been completely expended. As a result, the speed is still greater than omega naught and delta continues to increase. So if I have less inertia in my system will increase to a very higher value. And it will go to such a value that it will not be possible for the generator to retract back from E to D. So as a result, what will happen? The generator rotor will continue to speed up. As a result, beyond point E, P electrical is less than P mechanical. Rotor begins to accelerate again. The rotor speed and the angle continue to increase, leading to loss of synchronism. At the end, what are the factors which will affect this transient stability? Number one, it will depend upon how loaded the generator is. We have seen that from here, from my curve, where is my initial operating point? For instance, if I increase my operating point from here to here, my initial angle will be high, and due to this initial angle, my stability limit will be much less. So it is very important to know where I am operating my generator. The generator output during the fault, this depends upon the fault type and location. So if you have a three-phase bolted fault, the P electrical will become 0. So you will have greater difference between this P electrical and your steady pre-fault condition. But if you have single line to ground fault or a fault where the voltages does not exactly become 0, so you will have still the chance to improve this stability. The fault clearing time. The longer the fault duration is, the more difficult it will be for system to maintain synchronism. The post-fault transmission system reactance. So the closer the system reactance goes to the pre-fault condition, the more chances you have of system stability. But if you have a huge difference between your pre-fault condition and post-fault condition, then surely you may end up with transient stability problem. The generator reactance. A lower reactance increases peak power and reduces initial rotor angle. The generator inertia. The higher the inertia, the slower the rate of change of angle. This reduces the kinetic energy gained during fault, and the area 1 is reduced. And due to this reduction in area 1, you have more chances of getting this stability in your system. The generator internal voltages. This depend upon the field excitation and the infinite bus voltages, because this power transfer equation depends upon V1, V2 and X. So the stability will be impacted by V1, V2 and X at the same time. Welcome to transient stability analysis demonstration video. So now that we have discussed the basic concepts of transient stability, let us put this to test with the help of the same example which we studied in the lecture. Here what we have, I have created one infinite bus in the form of a power utility grid, and what I have modeled here. So I have a system with a 10,000 MVA short circuit with an X by R of 50. So this turns out to be a kiloampere of 43.73. So this is my power grid, 10,000, very strong source. So I have created one strong source here. Then there are circuit breakers which are connecting this transmission line. Now in order to model this transmission line, this time I have used impedance. So for this impedance, if I double click on this, let us see the data for this. Here we have the impedance in the form of, I have a 132 kV system, and the impedance is in percentage of 132 kV at 100 MVA base, and this is 50%. So 50% turns out to be 0.5 per unit. So this is my system for both the transmission lines, and then I have a generator, and the generator is a 20 megawatt generator. If I go to the rating, 20 megawatt generator with a MVA rating of 23.529 or 28.53, and it has a operating value of 15 megawatt. So its initial operating value is 15 megawatt, and based on this, ETAP has already calculated the megawatt values. And if I go to the capability, here is my capability curve for this. So this is the capability curve for my generator, and it can go up to this 18.88 and 12.39. So let me change this value here and make it, let us make this user defined and make it 12.39. So this is my reactive power. Okay, now going to the impedance model, we are using a 19% impedance, and for the dynamics I am using typical data. So my subtransient reactance this XD is 155%, XQ is 155%, and these are the different values, x double dash q, xt dash, so all the values, and xt double dash is this 19%, the negative sequence is 18%, and zero sequence is 7%, so all the values are there. So these are the values I have entered, and for the grounding it's a simple delta, and for the inertia let us assume that this generator part only, I'm not considering the coupling gear and this inertia of the prime mover, only the generator has an inertia of 4%. So with these values, let us press OK. So this is the only data, minimum data, because we said that this is the minimum data with which we can perform angular stability. So after this data, we have inputted the buses are 132 kV. So let us perform the load flow analysis to see what are the power flows through this system. So for the power flow analysis, I am going to go to this power flow, and I have given it the name of test, and let us solve this. So when the power flow is solved, I have this 15, let us make it, let us change the unit to I want to change the unit to megawatt. Let us change this unit to megawatt, so that in the display, and let us select MVA. Okay, so I have the result in megawatt and megawatt. So 15 megawatt is coming from here, from the generator, and 7.5 going through this line, 7.5 going through this line, and to the grid 15 megawatt is going towards the system. So this is my power flow. My power flow is all set. Now I am ready to perform. Let us perform simple transient stability analysis. Now performing for transient stability analysis, what do we have to select? We have to go to this transient stability option. This is number 1, 2, 3, 4, 5, 6 and 7th. From the left, I click on this. Now for this, let us first prepare the transient stability case. So what do I need in this case? I need to generate an event. So what kind of event I am looking for? So if I go into my transient stability, let me have this information as it is. I am not changing anything from here. Let us go to the events. In the events, we will create an event. So what we are going to do? We are going to introduce a 3-phase fault at bus number 2 at time number 1. Then we are going to clear this fault after 100 millisecond, and then trip this line by tripping circuit breaker number 1 and circuit breaker number 2, and my total simulation time will be 10 seconds. For the plots, I want to plot my generator, all the plots for my generator. Then I have bus, I want to plot both the buses, and similarly I want to plot my branches so that I can see the overall impact on the system. So this is the minimum data we require, and when we press OK, we are all set for this. Now let us perform transient simulation and see what happens. Let us go to run transient stability. We click on this, and the transient stability is performed, and here we are. So we have two events here. At time number 1 or 1 second, what I'm having a 3-phase fault on the system, and 3-phase fault on the system means that my voltage at this bus should become 0. So let us see if my voltages become 0 or not. So increasing the and going to second number 1. Let us see what happens at. So just reducing a little bit below. So here, so at 1 second and going a little bit. So here, the voltages have become 0, and due to this 0 voltage, my reactive power has also active power, and the reactive power at this point has become 0. So now what here it is happening? My grid is trying to increase the power reactive power into the system in order to improve the situation or improve the voltages, because here it is saying 0 voltages. So voltages are directly proportional to your reactive power. So the grid is now trying to provide some reactive power so that the voltages can be improved here. My system frequency has also increased a little bit. Now what happens after 1 second? Now after 1 second my fault should clear, and if we go after 1 second, see here my fault is cleared, my voltages has reduced, my line has tripped, and all the load has shifted to this. And now you see, instead of 15 megawatt, my generator is providing me with 20 megawatt. And if we go further, you will see continuously change. So why this change is coming? This is basically the stability which we are seeing, the stability problem, that now my generator is swinging with respect to my infinite bus, and this is the stability problem we discussed. Now let us see what will happen in the form of plots. Let us try to study the plots. So for studying the plots, let us go to transient stability plots. I will click on this. My plot window will open. So this is my plot window. I want new plots, and number 1 I am going to select for this generator 1 the relative. So power angle with respect to my swing bus. So what happens to my power? Let us plot this power. See, my initial angle was around 46-47 degrees, and as soon as the fault came on the system, the power angle increased, and this is the transient we were talking about. So we have this transient, and slowly it is reducing, and ultimately it is trying to reach the some stable value. So this is the angular stability we were talking about. So here we have a little bit of problem with this angular stability. So what happened to the bus voltages at this time? So let us generate the bus voltages also here. So let me, for bus 2, I want to plot voltage. So let us plot voltage, and let me plot, and there you go. So now you see, my for first second my system was operating at normal operating condition, and as soon, or at 132 kV, and as soon as the fault came onto the system, my voltages became 0, and it remained 0 for 100 milliseconds, and as soon as the fault was cleared, the voltages started to improve, and they have reached this value. So this is how you can see the stability problem in the system. So what happened to the transmission line? Let us see what happened to the transmission line as well. Let us select both 1 and 2, and let us plot megawatt values first. Plot. There you go. So what happened here? So this is from the from end, that is why it is negative here, because it is receiving. We could have plot from the 2 end. Let us plot from the 2 ends so that it will become easier for you to understand. So let's plot. My initial power transfer through both the transmission line was 7.5 megawatt. So this is 7.5 megawatt here. At 1 second the fault came, and with this fault V became 0. So V became 0, we know that P is equal to VI. When my V became 0, my power became 0. So here, this is my 0 power, and as soon as the fault cleared, my line tripped. So Z1 is the first line which we tripped. So now the power on this line will continue to remain 0, whereas the other line will take the power of the whole generator. So it is taking, and then this is some stability problem. It is trying to improve its stability, and ultimately it reaches some stable point. Welcome to power system analysis using ETAP. In this lecture, we are going to discuss some typical transient stability studies and what are required from them. In a typical power system, in order to maintain load generation balance, the system frequency should remain 60, or in other words, the system frequency is balanced or 60 Hz or 50 Hz when the generation is equal to demand. So what constitutes demand? Demand can be in the form of the total load in the system, the total losses in the system, plus anything coming from the utility. So this will be known as the demand, whereas generation will be the power generated within the facility and anything exported to the system. So as long as these two are balanced, the system frequency will be 50 Hz. However, if we see a change in this, our frequency may not remain 60 Hz. For instance, what happens if the load is lost or certain motor in the industrial facility is lost? So now generation will not be equal to load. As a result, frequency will start to go towards lower side. Whereas on the other hand, if the power generation is increased or the load is tripped from the system, now the generation will become more than load, so the system frequency will start to increase. So let us take a typical example of load addition. Here in the pre-transient case, let us assume that my P electrical is equal to P mechanical. So the difference between the two is 0. What happens if a load is added into the system? So with the addition of the load, my P electrical will increase to its new value. For instance, from P electrical is equal to 0 to P electrical is equal to 100. But at the same time, the prime mover, due to inertia of the system, will take some time to react to this change. So as a result, the P mechanical here will take some time. Ultimately, it becomes equal to P mechanical. And due to inertia in the system, this P mechanical will increase beyond this P electrical and then will try to adjust itself till it reaches P electrical equal to P mechanical. So the time required for the frequency fall event is directly proportional to the inertia and inversely proportional to delta P. So this change in frequency will directly be dependent upon the inertia of the system. So higher you have inertia in the generator or the total equivalent inertia in your industrial facility, the more less will be the change in the frequency. So this is how the system responds or the generator responds to the change in the load or the generation imbalance. So now this control of generation is in the form of two modes. So first of all, what is the objective of this generator? The goal is to maintain the constant frequency with the changing load. So what do we want? That our generator in the system should maintain the load so that my frequency remains 60 Hz. So if we talk about this isochronous mode, what is this kind of mode? If there is just a single generator, such with an emergency generator or isolated system, then an isochronous governor is used. What happens in this isochronous governor? Integrates frequency error to ensure that frequency goes back to the desired value. Cannot be used with interconnected system because of haunting. So here is the image source. Let us see this source. So here is my isochronous system. So what will isochronous system do? Irrespective of the change in load, it will try to maintain the same system frequency. So it will changes the output of the generator continuously in order to maintain the stable or the nominal frequency of the generator. So what is the problem with this mode? This mode is very good if you want to implement, if you have only one generator in your system, or in your facility if you have only one generator, then you can go with isochronous mode. However, if you have two or more generators, what will happen? Now in case you have change in frequency or you have an imbalance between load and generation, both generator will try to control this frequency, and due to controlling of these two generators, they will try to fight each other in order to maintain the system frequency. As a result, when one generator will try to increase the frequency, maybe the other generator will try to reduce the frequency. So in order to maintain this balance, because as a result of this, we may have this hunting in the system. What do we mean by hunting? A continuous oscillation may occur in the system. So what is the solution to this problem? The solution to this problem is the droop mode. So to allow power sharing between generators, the solution is to use what is known as droop control, in which the desired set point frequency is dependent upon the generator's output. So if we select droop mode, what will happen? Irrespective of the output frequency, the droop will try to change its frequency accordingly, and it will not try to maintain the frequency at 50 Hz, but it will increase its power a little bit. It will share its power a little bit so that the frequency is maintained at a certain lower value. So here the important concept is this R, or the droop. R is known as the regulation constant or droop. A typical value in the system is around 4 or 5%. So what does this 5% or 4% droop means? It means that at a 50 Hz system and a 5% droop, each 0.1 Hz change will change the output by 0. So what does this mean? That if you have this output by 0.1, so I have a change in frequency of 0.1 divided by 60 into 0.05 is equal to 3.33%. So in other words, whenever there is going to be a change of 1 Hz in my system, my frequency or my load is going to be changed by 3.33%. So for every 1 Hz change, my output from the generator will be. So now each generator, depending upon its MVA capacity and depending upon how much value it has available, it will try to provide this output. So this way the generators will not fight, but will try to reinforce each other in order to maintain the system frequency. Some typical kind of transient stability studies for industrial facilities are load addition, load rejection, the application of a three-phase fault, application and clearance of a three-phase fault with equal load sharing, with unequal load sharing, loss of generator, and frequency-based load shedding. We already saw this problem that if we have one generator connected to my infinite system and I implement a three-phase fault, what happens to my system? So these are the kind of studies I try to do in order to find out that how my generator, my cogeneration is going to respond in an industrial system. Welcome to transient stability analysis using ETAP demonstration video. Now that we have studied about the transient stability, let us put it to the test here and simulate some conditions to see how this transient stability works with the ETAP. Now in order to perform transient stability, what we have done is we have used the same case which we have used for our load flow analysis, short circuit analysis and motor starting analysis, and we have added an additional part to this network. So what do we have created? We have created here a HV breaker and we have given it an ID GCB or the generator circuit breaker, which is connected to 13.8 kV generator bus with the help of a 25 MVA 9% impedance transformer. So if we double click on the transformer, we go to the rating is 25 MVA and the impedance of the transformer is 9% with an X by R value of 23.7. On the generator side, we have a generator. We have modeled a generator with the ID of cogen with the rating of 20 megawatt at a power factor of 85%. This turns out to be an MVA capacity of 23.59. So we have a generator of 23.59 MVA capacity. It's a 4-pole generator operating at 1800 RPM, and the design or its normal operating megawatt value or the PGen value is 15 megawatt. So we have selected here 15 megawatt and we are using capability curve, and for the capability curve, peak megawatt is going to be 12.39 based on 85% power factor. So for the capability curve, if I go to the capability curve, point A and B, the maximum reactive power is 12.39. Similarly, minimum reactive power is minus 12.39. So I am using the same values for the positive side and the negative side. For the impedance model, we have used subtransient model with the typical data. And here the type of the generator is, I am assuming that my generator is a gas turbine. So I am using here generator type gas turbo and the rotor type round rotor. If you have a hydro generation, then this round rotor will be salient pole rotor. But see, salient pole. But since we are modeling a thermal generator, so we are going to use this round rotor. If you have a hydro generator, you can go ahead and use salient pole generator. We haven't changed anything in the grounding. So let us go to inertia now. For inertia, we are assuming that the total inertia is available at the generator side and the value of this is 4 megawatt second per MVA. And for this value of 4 inertia, ETAP has done the back calculation and calculated WR square, which is equal to 125752. Now for the exciter, we are assuming that the exciter of this generator is AC1 type and we have used sample data for this. But in reality, this data will be provided by the manufacturer. So you need to take this data from the manufacturer data sheet and enter this impedance model data and the exciter data. Similarly, governor data will also be provided by the manufacturer. So please use the same actual data in your calculation. But here we are just providing the demonstration. For the demonstration purpose, we are using the governor GT type in the droop mode with the sample data. So this is the data we have, and let us adjust this P max to 20 megawatt. So we do not want our generator to go more than 20 megawatt. And we are assuming the droop to be 5%. So this is the data we are assuming for the generator. Similarly, we assume that we have an auxiliary load of 0.5 MVA or 500 kVA. So we have given it an ID of auxiliary nameplate, and what we have here, we have this load of 500 kVA or 0.5 MVA at a power factor of 85% or 0.85 with 70% load as constant kVA or constant power load or motor load and remaining 30% as static load. So with this, we have also created some configurations, and the configurations we have created are, one is maximum, system and maximum cogen. For maximum system, we assume that we have no cogeneration connected to the system. So let us see what this impact it has on the power flow for the benchmarking purpose. Let me go to my power flow and let me select from here maximum system. And when I run the power flow, here you see I am getting 9.01 megawatt from my source 1 and 11.8 megawatt from my source 2, and it is being distributed to the whole system. And other important thing you will see here, because I just selected from the configuration manager outage of this HV breaker or the GCB breaker. I did not select the outage of generator or auxiliary load. That is why now think of this generator operating in an house load mode or island mode, supplying only this auxiliary load. So what will happen if we select the other mode? So let us go to this here and let us select maximum cogen. And when I come back to power flow, let us select the power flow from here for the maximum power gen. Let us solve. So the first thing that has happened is we have improved voltages. We have a little bit improvement in voltages, number one. And the second thing we will see is that the import from the grid or from the utility side has reduced. Here it was 9 and here it was 11. Now it has reduced to 2.72 and 3.58 because we are getting some generation from the cogeneration plant which is feeding the internal load. So this was about the configuration, and now for this maximum cogen configuration, we want to test the angular stability of this generator. We want to test what happens if we have a three-phase fault in the system and my strong source gets tripped, or my CB line 2 gets tripped. So how my system is going to impact to this disturbance. So for this purpose, we have to create a transient stability case. For preparing the transient stability case, I will go to my transient stability and let us prepare the case. For preparing the case, I will go to edit case study mode. So this is my transient stability, and let us create an event. No change here. I am using the same default values from here. I will go to the event now and let us create the event. So what is going to be my first event? My first event is going to be E1, and I am going to introduce a fault at 1 second. And where this fault is going to be introduced? This fault is going to be introduced at bus main A, 3-phase fault, and press OK. So I have a 3-phase fault at bus main A at 1 second. Now when the fault is seen by the system, this will be cleared within some operating time, the relay operating time. So let us assume that it takes almost 100 millisecond to clear this fault. So let us create another event by the name of E2, and which will happen at 1.1, which means that 100 millisecond from or 0.1 second from the first event. So I just add 0.1 to my original event to get the second event. And what will happen in this event? Number 1, my main bus A will have clear fault. So fault is cleared, number 1. And the second item will be, from here, my circuit breaker for CB line 2 will be opened. So these are the two events I have created, and my total simulation time is 100 seconds. Now to adjust the plots, what type of plots I want? From here, number 1, for my generator, I want all the plots. Similarly, for my buses, I am more interested in my main buses. So let me select bus 1A, bus 1B, bus 2A, bus 2B, bus A, bus B. Let us select the generator bus as well, and the main bus, so these buses. From the branches, let us see how my line flows are impacted by this fault. So let us select only this. So these are the selections, and then I go to dynamic model. Now since we are performing the load flow analysis, transient stability analysis, we are not interested in the load dynamics. For this reason, I am going to make this do not model dynamically. Similarly, my induction motors and my lump load will be, so everything is not, so I am using only for, in simple words, constant power load I am using. So I do not want my LTC action, I do not want any starting device action, and rest is okay here. Then everything seems okay. For the adjustment, I do not want any tolerance for my transformer, for my reactor, for my cable, or for my transmission line. So I have everything ready now. When I press OK here, so I have this case ready. Let us solve this case with the help of ETAP. So I will run transient stability. Let us select the option. I have already one option selected. So the name I have given is cogen angular stability, because I am trying to check cogen angular stability. And let us solve. It is going to take some time. Resolve it, and there you go. Our first event was at 1 second, which was a 3-phase fault. Let us see what happens with a 3-phase fault. So when I go to my 1 second here, a little bit above 1 second, due to this 3-phase fault, the voltages have reduced to 0. On all the buses, only generator bus, a little bit higher voltages are there. At 0.1 second, the fault should clear. So if I go here, see, the fault has cleared after 1 second, and this generator, my CB line 2 has opened. The voltages are trying to restore, and see, the interesting thing is the power. here. So you see the power. Now the power of the generator has increased to 27 megawatt. And if I increase a little bit further, so here I am seeing the variation in the voltages. So what does this variation in the voltages tell me? It means that I have a certain instability going on in my system. So this system is taking, or the generator is taking some time to settle to its post-fault condition. So if I go to almost 8 or 9 seconds, and so now the system is almost restored. So a little bit variation is there. So system is almost restored to this point. Now let us see the same thing in the form of plots, because it is easier to understand with the help of plots. So let us go here, transient plots. No. First of all, let's see what happens on the voltage. So I am going to select main bus A, because this was exactly the bus where the problem happened. And I am going to select voltage. And when I plot this, so everything was okay here. And then we had a three-phase fault which caused the voltages to drop to 0. And the voltages remained for 100 millisecond to 0. And then the fault was cleared, line was stripped, and the voltages recovered. And here is the recovery. Everything seems to be okay after this. What about the generator bus? And let us select the same thing for the generator bus. And if we plot, here you see. So we have both plots here. So this is at 132 kV, 13.8. The voltages drop. Here the voltage has not dropped to almost 0, but it is a little bit higher than 0, because the fault is a little bit far away from the generator bus, because it was on the higher side of the bus. So here we have this, and then voltages recover. Let us see what happened to the angle, because angle is important for me. So for this, let us go to synchronous generator, my cogen, and let us see the relative angle with respect to my grid. What happened to this? So let us plot. There you go. So initially I was operating somewhere near 47 or 48 degrees, and then as soon as the fault occurred on the system, I had some unbalance in my system, and then system started to oscillate with respect to the grid and ultimately reaching some steady state value. So this is how you can perform transient stability. From here, what we come to know, that my system is stable, because my system synchronizes back to some pre-fault condition. It does not go out of step. If my system or the generator has gone out of step from here, it would have told me that now my system or the generator has lost synchronism. But in this case, no synchronism is lost. What you can do is you can perform this simulation again and again, but with different time of clearing time. Instead of 100 millisecond, use 200 millisecond or 300 millisecond and rerun this simulation to see what happens. Welcome to transient stability analysis using ETAP. In this demonstration video, we are going to perform frequency stability analysis. Now for the frequency stability analysis, we have configured a new configuration known as normal cogen, in which under normal operating conditions, we have only two motors out of service. This crusher 1, 3500 horsepower is open, and pump C with 500 horsepower is open. And the cogeneration is connected to the industrial facility itself. In the simulation, what we are going to do is, we are going to trip the utility sources, both the utility sources, so that our local generation continue to feed the industrial facility itself. So first of all, let us perform the load flow analysis to see how much import we have from the grid in this case. So for this purpose, we will go to load flow. We will create a new prompt, output report known as normal cogen, and let us solve this report. So if we see here, we have almost 1.39 and 1.83, around 4 megawatt of power which is flowing from the grid itself. So it means that in case we trip these two incomers or we trip this utility source, we have only 15 megawatt of generation, and this we will have a deficiency of almost 4 megawatt, which is going to cause drop in system frequency within the industrial facility. So let us perform this simulation to see what happens. For this purpose, we will go to transient stability. We have created a new case with the name TS_frequency, and the event in this case is event 1 at 1 second. And what will happen? Both the circuit breakers of the incomer of the utility will trip at 1 second, and the total simulation time is 15 seconds. For the plots, the same plots are there. We have selected the plot for the cogen, we have selected the plot for the bus, and we have selected the plot for the branches, and we press OK. Let us perform this simulation. The name of the output file is frequency_stability. Let us perform transient simulation here. So we have 15 megawatt input from the system and 1.3 and 1.8 megawatt input from the utility. So at 1 second, both the utility breakers are going to get tripped. So if we go to a little bit more than 1 second, here both the utility breakers have tripped. Now the entire load has to be fed from the local generation or the cogeneration. So if we move further, you see that now the system frequency has started to drop, and this drop in frequency is telling us that we have a little bit deficiency in the load. And if you see here, my load has increased from 15 megawatt to 18 megawatt in order to, as per its droop value, in order to feed the load of the entire facility. So let us see in the form of plots. So we will select transient stability plots. No, so that we have fresh plots. So for this transient stability plots, first of all, let us go to the bus and see the frequency. Let us see what is happening to the frequency, and for the frequency, let us monitor the frequency of the main bus A, or my main 132 kV bus. So if we see here, at this time my source got tripped, and due to this tripping of source, here my system frequency in the form of percentage is reducing. It reduced to this value, and then it is settling to some value. So this is how my plot is responding. So let us see how my generator electrical output or the mechanical output of the generator changed. So I will go to system frequency. Let us number one select the speed of the generator and megawatt mechanical of the generator, and let us plot both these plot. So there you go. So here you see the RPM of the machine. When the RPM of the machine are dropping, at the same time the load or the prime mover is trying to increase the output of the generator, so that this drop in speed is compensated by the increase in the megawatt power output, and here it settles at 1785, and here it goes to its high value. So this is how you can create different simulations and see how the system is responding. Welcome to transient stability analysis using ETAP demonstration video. In this video, we are going to perform load rejection simulation. For the purpose of load rejection simulation, we have created a new configuration in the system known as island, and in this case we do not have any power grid connected. So the entire load is being fed with the help of the local generation, the cogeneration available in the network. So we have these, some of these motors are in standby mode, whereas other are running. So what will we see is what happens, what will be the impact if some load is rejected from the system. Say this distillation unit of 7 MVA is tripped. So what will happen to the system in this case? So for this purpose, let us first perform the load flow analysis to see what is the system condition. So I go to load flow analysis and I have created a new output report with the name of island. When we solve this, everything seems to be okay. For this cogen, I have increased the voltages to 103%. How you can do that? You can simply go to cogen, your rating, and simply at the design, I have changed rating from 100 to 103. So this means that my voltages are okay everywhere. So let's see what happens if this 7 MVA load is tripped from this industrial facility when it is being fed through the cogeneration. For this purpose, again, we will go to transient stability. Let us create another case with the name of LR or load rejection. And in the event, what I'm going to do is at 1 second, now instead of tripping this at 1 second, I'm going to trip my breaker. This is C6. So I'm going to, let us press cancel here and check this breaker. This is CB6. So I will go here, create a new case with the name of transient stability underscore LR, because this is the new simulation I'm trying to perform. And in the event, I'm going to delete these two events, create a new event. And in this case, my new event is my circuit breaker CB6 gets open at 1 second. And I'm going to run the simulation for 15 seconds. Everything is already the same because we have copied this from the existing. So what we can do is simply press OK to get the results. So now let us select prompt, because now we want to create a new report. And when we perform run transient stability, this time we are performing load rejection for 7 MVA load, and we press OK. The simulation is performed at 1 second. We are going to have tripping of this distillation unit. So if we move forward to 1 second, here you see the distillation unit has tripped. As a result of this, the voltages are increased because the load has tripped from the system and the frequency is starting to increase, and the load on the generator has decreased. So if we move forward, we see that frequency has now settled to 60.9 Hertz. Now to see this thing through the plots, let us select transient stability. No. So we have this load rejection. For this load rejection, first of all, let us select bus A, and let us select the frequency of this bus. And when we press plot, there you go. So the frequency was at 60 Hertz, and then it increased to 100 and almost 206, 101.6 or 100.7 Hertz, and then it settled back to almost 101.5. So what does this 101.5 means? You simply can do is 101.5. Okay, so this means, so you have a 60 Hertz system, and this is the percentage of the frequency. So 100 means 1 per unit, and this means 1.015 into 60. So the frequency is 16.9 Hertz. Now let us see the generator condition. For the generator, let us select the mechanical power output, and when we plot this, so when the frequency is increasing, my output of the generator has started to decrease, and from 15 megawatt it has dropped all the way to 8 megawatt and then settled at around 8.5 or up to 9 megawatt. So increase in frequency is followed by drop in load. Whereas in the previous simulation, the drop in frequency was followed by the increase in generation from the cogeneration power plant. Welcome to Power System Analysis using ETAP course. In this lecture, we are going to introduce the basic concepts of motor starting analysis. So what is motor starting analysis? A motor starting study is performed to determine the voltages, current and the starting times involved when starting large motors or a group of motors either sequentially or simultaneously. Motor starting studies are carried out to help ensure that the motors will start with appropriate acceptable voltage drop. Voltage drop at time of start will not disrupt other loads. Motor feeders are sized adequately. Motors will accelerate within acceptable startup times. An accurate evaluation of motor load speed torque curve and accelerating time is made. Accurate evaluation of thermal damage characteristic of motor is made. The motor will not experience nuisance tripping on the start. In the event of direct online start is not possible, that the type, size of starter drive required to start the motor is known. Motor protective devices are sized and set properly. So what are the different criteria? Before understanding the criteria, we need to know that the starting large motor can cause disturbances to the motor and the other loads on the other buses. In the worst case, the starting motor may stall and be unable to start the driven load. So therefore, it is important for us to know that at which time or when this motor starting analysis should be performed. So some of the criteria where it is important to perform motor starting analysis are: a motor starting study should be made if the motor horsepower rating exceeds approximately 30% of the base kVA rating of the supply transformer. So if you have a motor which is at least 30% of your transformer rating, you should perform motor starting analysis. Similarly, if a motor is to be started from an isolated generator, or a motor starting study should be performed if the motor horsepower rating exceeds 10% to 15% of the generator kVA rating, depending on the actual generator characteristic. So what happens if you are not connected to your grid? So you are isolated and you want to start your motor, so you have to make sure that your generator will not cause any problem, your motor starting will not cause any problem to the generator. The study should also recognize contingent condition, that is the loss of a source. So what does this mean? If you remember, when we were performing short circuit analysis or load flow analysis, we were considering different kind of configurations, system configurations. And in our case, what happened? We had two grid sources. So what happens if one of the grid source is not available or the strong source is not available? We are only connected to the weak source. So what will happen in this case? Surely in this case, motor starting will be more depressing. It will be more worse case. So we need to consider these cases when performing load flow analysis. The types of motor starting studies range from simple voltage drop calculation to a detailed waveform representation of a motor bus voltage, motor speed and motor torque, acceleration torque, load torque, power factor, rotor and stator currents, motor slip, real, reaction and reactive and total power study that approaches a dynamic analysis and complexity. So when we talk about this simple motor starting analysis or static motor starting analysis, in which we are not considered about the dynamics of the motor, in this case we are only interested in the motor bus voltages, what kind of voltages drop we can expect. But in case of dynamics, we go into further detail and we want to know the motor torque, the acceleration torque, the load torque, the power factor, the rotor and the stator currents, the motor slips, so things like this. So depending upon the requirement, you have to perform such studies. Now, one of the most important criteria as discussed is that we want to know that what will be the voltage dip. When a motor is starting, what will happen? Motor is basically a constant power load. So what happens to a constant power load? When voltages drop in a constant power load, the current is supposed to increase in order to maintain the voltages. So in other words, when during the starting of the motor the current is high, so voltages will be low, so that the total power, the constant power remains the same. So now we need to make sure that when this huge inrush of current is coming into the motor, the voltages does not drop below a certain level. Number one, at the bus where the motor is connected, and all the neighboring bus where other motors are connected. So we need to make sure that this will not lead to further stalling. So probably the widely recognized and studied effect of motor starting is the voltage dip. Available accelerating torque drops appreciably at the motor bus as the voltage dips to a lower voltage, extending the starting interval and affecting sometimes adversely overall motor starting performance. Acceptable voltage for motor starting depends upon motor and load torque characteristic. During motor starting, voltage level at the motor terminal should be maintained as specified by the motor manufacturer. So how can we make sure of all these things? Here is a table giving an example, so that the voltage drop location or problem, that whenever there is a motor start, the system voltage should not drop below 95%. They should remain within this range, 95% to 105%. At the terminal of the motor starting, the voltage should not drop below 80%. Similarly, at terminal of other motors that must decelerate, the voltages must not drop below 70%. And similarly, the values are given for other requirements. So when we talk about this motor starting, we have two types of motor starting analysis, which we will discuss further in detail, and the applications and advantages and disadvantages of each one. But to give you an overview, we have two type of motor starting analysis. We have a static motor starting analysis, and we have a dynamic motor starting analysis. When do we use static analysis? When we are concerned with the effect of motor starting on other load. So what is going to happen when I'm going to start my motor, and how it is going to affect the other motors, and if you do not have available dynamic motor information. Usually some utilities say, or some these oil and gas facilities, they have their certain criteria, and from their criteria you will come to know that in which cases you have to perform static motor starting analysis, and when you have to perform dynamic motor starting analysis. But usually when we have motor load below 1000 horsepower, we tend to perform static motor starting analysis, and if we have motors ranging from more than 10,000 horsepower, then we tend to go for dynamic motor starting analysis. But this is not a hard and fast rule. It will depend from industry to industry or utility to utility. And for the dynamic models, we are concerned with the actual acceleration time and concerned if motor will actually start. And so this is a typical curve which we can expect in case of static motor starting and a dynamic motor starting. Here you see, there you have a typical. Here just a voltage drop is there, and then once the motor starts to accelerate, you go to the final load. Welcome to power system analysis using ETAP. In this lecture, we are going to provide an overview of induction motor. So what is a motor? A motor is an electromechanical device that converts electrical energy into mechanical energy. Electrical motor operates through the interaction of magnetic fields and current carrying conductors to generate force. So what do? We provide electrical power at the input of the motor, and at the output we get mechanical power, with the help of which we drive the load. So power input into the motor is in the form of active power plus reactive power, or the apparent power. So usually you have seen that motor rating is given in the form of MVA rating. So MVA rating means that it has some active power plus reactive power. And this is the torque, omega m, which is generated. This is the speed of the motor, omega m, and the torque generated by the motor will be Tm, and the torque by the load will be TL, and they will be working in opposite directions. So PM will be equal to Tm omega m, where efficiency of the motor will be equal to Pm divided by P, where Pm is the mechanical power and P is the electrical power. And T acceleration will be equal to T mechanical minus T load. So before going into further details or discussing the torque curve, it is important to know about some important terms. So the important terms related to induction motors are accelerating torque. So what is an accelerating torque? The amount of torque available to accelerate the motor and load at any instant in time. Accelerating torque is the difference between the torque available from the motor at the motor output shaft and the required load torque of the load system as seen at the connection to the motor shaft. Accelerating torque varies with the instantaneous speed of the system. So as the speed varies by varying speed of the system, what do we mean? We mean 2 pi f or omega of the system. And so when the frequency of the system changes, the accelerating torque will also change accordingly. The breakdown torque or the maximum torque. The maximum shaft output torque that an induction motor or a synchronous motor operating as an induction motor develops when the primary winding is connected for running operation at normal operating temperature with rated voltage applied at the rated frequency. This is also the peak of the torque slip curve at rated voltage. So the maximum available torque in the system, which can be withstood by the motor, is known as the breakdown torque. Motor starting torque or locked rotor torque. The torque output capability of a motor at zero speed and rated voltage and frequency. It may also be defined as the minimum torque of a motor developed for all angular positions of the rotor when at rest and with rated voltage and frequency. So, during the starting of the motor, when you are trying to start the motor, what will happen? The motor will be stationary. So, at that time, when you provided the rated voltage and the rated frequency to the motor and the input current, the current injected by the motor and the torque generated due to this is known as motor starting torque or locked rotor torque. Pull-up torque. The minimum torque developed by the motor during the period of acceleration from rest to the speed at which breakdown torque occurs with rated voltage applied at rated frequency. So if you want to see these items, let us discuss this motor torque speed curve. This is the commonly provided, this is the common way of seeing any induction motor, how the induction motor responds, and this torque speed curve is going to vary for different kind of motors. So what does this tell you? This tells you, so what is the torque here? Here it is the torque and here is the speed of the motor. And this portion is the operating region where your motor is going to operate normally. And this is the pull-up torque we talked about, and this is the starting torque. So see, when the motor is trying to start at the rated voltage, the speed is 0. And at that moment, when the speed is 0, the torque is really high. And the injection from the system, the current injection will be really high. So that is why when the current is high, you want to reduce this current. So there are several ways to reduce this current. So what we will do, we will be using some kind of motor starting techniques or the motor starting devices, startup devices, which we use at the start of the system in order to reduce this value. And then this is the pull-up torque, and this is the pull-out or the breakdown torque, which we talked about, which is almost 2.5 times of the normal torque. And this is the normal operating region. This is the accelerating torque here when the motor is operating at its normal speed. So the same things, there are usually two type of designations for this induction motor. Usually you may have this NEMA designations or IEC designations. So if we talk about IC designation, so in IC designation, the starting torque, which is also known as locked rotor torque, this is the same thing. So this is my locked rotor torque at the start of the when I am trying to start my generator. So this is slip. Here it is given in the form of slip. So slip means that from difference from the speed. So when the slip is 0, it means that motor is operating at its maximum speed, and when the slip is 100%, it means that the motor is at its stationary position. So this is the lock rotor torque, or the stalling torque, and there is the minimum torque, which is also known as pull-up torque, and this is my nominal torque, where this is my normal operating condition, and at the full load this is my operating point, and this is my breakdown torque, which is also known as maximum torque. So these are the designations which can be used, and from these designations you will come to know that what type of motor I am talking about. So a little bit more about the acceleration torque. The greater the acceleration torque means higher inertia that can be handled by the motor without approaching the thermal limits. So this is here, this is what is this? This is the load torque requirement. So the torque required by the load, and this is the accelerating torque available. So from this region we come to know that we have enough margin. So the more the margin we have, and it will be easier for motor to handle the load. Like we define equivalent of a transmission line or a transformer, similarly we can define an equivalent model of a transmission of a induction motor. So a typical model of an induction motor is shown here. So there are two parts of induction motor. We have a stator part and we have a rotor part. So what is the stator part? Stator part is the point where you provide the terminal voltage to the motor. So in case of a three-phase motor, what happens? We have three set of windings in the stator for phase A, phase B, and phase C, and we provide three-phase voltage to it. And what will happen? So three-phase voltage will initiate or generate a rotating magnetic field, and this rotating magnetic field, when it is induced into the rotor or the rotating part of the motor, so after the induction of this induction, we are going to have this motor rotating. So, and these are the losses within the motor, and this is the impedance of the rotor side, and here the input is the P electrical, and from here we are going to get P mechanical. In ETAP we have the capability, or we have the possibility of modeling this characteristic model. So if you have this model available from the manufacturer, then very good. If you do not have, what you can do is you can either select some characteristic model from the library. So when you select any characteristic model from the library, what are you going to get? You are going to get two things. Number one, the torque speed curve, and then the current speed curve, and the power factor and speed curve. So if you see here, when initially the motor is operating at this starting a locked rotor, you see the locked rotor current, when the torque is this, the rotor current will be 0. So at 0 speed the current will be much higher, but as the motor starts to go towards this maximum speed or its rated speed, the torque increases but then goes to its nominal value and the current reduces. So if the characteristic model or the equivalence model is not provided by the vendor, then MPET module in ETAP can estimate these models from below nameplate. So we will provide some kind of a nameplate data, and then based on this nameplate data we can ask the ETAP to perform this estimation for us. And some of the data which we will have is, or we have to provide, is the power factor at 100% loading, efficiency at 100% loading, slip by speed ratio, the locked rotor current, the locked rotor power factor, the locked rotor torque, and the maximum breakdown torque. Once we provide these values, so what we can estimate is we can estimate the equivalent model of the induction motor. Welcome to power system analysis using ETAP. In this lecture, we are going to discuss motor starting analysis input data for ETAP. So regarding the ETAP data, for motor starting analysis, we require similar data as we require for load flow analysis. For the bus data, required data would be the nominal kV and the load diversity factor. That's it. For the branch data, this branch data includes, as we discussed before, also the 3-winding transformer, 2-winding transformer, transmission line, cable, reactor, impedance. So all kind of branches come into this. For this we require R, X and B data for the branch, and X by R values and Z values if we are talking about 2-winding or 3-winding transformers, the tolerances values and the temperatures if applicable, the length and the unit of the cable and the transmission line, for the transformer kVA and kV data, and the load tap changer data, because this load tap changer data is going to play a very important role when we are discussing motor starting analysis, because we have to work with voltage dips. So voltage dip can be reduced with the help of load tap changers. The power grid, we need the rated kV, the short circuit levels, and if we can get the minimum short circuit level, this will be the best option, because the minimum short circuit level means that we are talking about conservative system where the impedance of the system is high. So the higher system means more voltage drop into the system, and the voltage at the point of interconnection. For the static load, we only require the rated kV, the load in kVA and its power factor. Similarly, the operating load at which the load is operating. For the lump load data, we require the percentage between the motor load and the static load, the rated kVA of the load, the rated voltage of the load, the power factor of the load, and how much the operating load is. Now for the induction motor data plays a very vital role in the motor starting analysis, because this is the equipment on which this analysis has to be performed. For this, the data which we required for the load flow analysis, so similar data, first of all, the similar data is required, like the rated kilowatt or HP and the rated the kV of the motor, the power factors and the efficiencies at different load levels, and similarly the operating load. In addition to the above parameters, required parameters for the full dynamic motor acceleration studies include the motor load and coupling inertias, mechanical load characteristic as a function of speed. So now we need to provide the inertia of the system, the characteristic of the motor characteristic of the load also, if we want to perform detailed dynamic motor starting analysis. But if we talk about static motor starting analysis, then the already data we provided in the case of load flow and short circuit, the locked rotor currents and the rated megawatt and megavar values, that would be enough. So summing them up, this is the type of data we require, the different equipment or the elements we have in our system, and what type of data. For the static motor starting analysis, for the generators, we need to model them simply as a constant voltage behind its transient source. The exciter and the governors, no need to model them. This won't have any impact on the static motor starting analysis. The utility ties, or also known as the power grid or the grid connection. So this will also be the constant voltage behind its short circuit source. For the large motor and the small motors, we will require the constant kVA. The starting motors, the locked rotor impedance at the time of starting. Similarly, starting motor post starting, again it will be considered as constant power. Starters, if they are available, then they should be modeled. If they are not available, then no need to model them. Similarly, the load tap changers needs to be modeled in this case. Same goes for the dynamic motor analysis. For the dynamic motor analysis, the different thing you will see here is that the starting motor, we need to model the dynamic model. And the second thing we need to do is we need the circuit model, the equivalent circuit model of the induction motor as well, so that we can capture the dynamics of the motor. Welcome to power system analysis using ETAP. In this lecture, we are going to discuss types of motor starting simulation. So the first type of motor starting simulation is static simulation. During the acceleration period, the motor is represented by its locked rotor impedance, which draws the maximum possible current from the system and has the most severe effect on the other loads in the system. So what are the applications of this? Used for the system with strong and weak power grid support, with or without generators. When dynamic motor information is missing. Typically used to analyze impact of critical LV or large medium motor loads. Can assess sequential or concurrent start of multiple motors. Existing system where motor is known to start without a problem and starting time determination is not a requirement. Determining adequate tap position. Some of the advantages of static motor starting a generator dynamic can be ignored due to presence of strong power source such as power grid with high MVA short circuit. This study can be conducted even when dynamic model information such as motor torque, slip characteristic, inertia and load torque characteristic are not available. Disadvantages: since dynamic model is not utilized, it is not possible to determine the starting time of motors. Generator dynamics are not considered, it is a conservative approach. In this way, this is a very good approach if you want to do the initial assessment, and usually in industrial applications people tend to do this type of static simulation more commonly, whereas when the motors are of big size, say more than 10,000 horsepower, then dynamic motor simulation is done. What are the applications? Some of the applications of dynamic motor simulation are used for system with weak power grid support when compared with the required starting kVA of the motor and or island system configuration. Dynamic motor information is available or can be estimated. Typically used to analyze impact as well as determine acceleration time of critical, low voltage or large motors. Sequential or concurrent start of multiple motors. Used in existing systems where motor is known to have problem starting or the starting device is being added modified. Also used for new systems in order to determine motor protection settings. Used to determine appropriate tap position. One of the most important application for dynamic motor starting is if you want to check your starting device. If you want to add some kind of a starting device to your motor or you need to modify your starting device, then dynamic motor analysis is the best way to move forward. Advantages are including system dynamics will provide a more accurate assessment of the perspective parameters during the motor starting, because now you are considering the equivalent model of the motor itself with its inertia and torque speed curve and everything, so the results will be more realistic. Disadvantages require motor and driven load dynamic model information which may not always be available. Therefore, the analysis is limited to typically critical LV motors and large MV motors only. Generator dynamics are required. Hence, it is a realistic approach but requires generator controls such as exciter and governor controls to be specified as well. This information may not be readily available, especially for older facilities. This type of analysis also requires the generator motor to be tuned against field measurement for optimum accuracy, which contributes to a higher cost. So you need to have a good working model. Without a good working model, you may not be able to perform dynamics. Although you will be able to perform dynamic analysis or the dynamic motor starting, but you won't have any benchmark to compare against it. So therefore, it is said that you need your models, whether they are your generator models, exciter model, governor models, they need to be validated against some field measurement in order to make sure that the models we are using in our simulation are exactly as they are available in the real world. Some type of starting devices most commonly used are auto transformers, stator resistor, stator reactors, capacitor at buses, capacitor at motor terminal, rotor external resistance, rotor external reactor, Y delta windings, soft starter, stator current limiters, and these can be in the form of stator current control, voltage control or torque control. So the idea for the starting device is to reduce this initial locked rotor current. So this can be done with the help of these type of devices. Welcome to the demonstration video of motor starting analysis in ETAP. So this is the same network which we have used for load flow analysis and short circuit analysis. Although I have made just one change in this configuration. If you go to the configuration, for the minimum configuration, now instead of opening the power grid 2, I have kept the power grid 2 connected and just opened the tiebreaker between each of the different voltage level bus. For instance, 13.8 kV bus. Now if you see, the both are open, so both will be fed from their individual transformer. Same goes for 4.16 and same goes for 0.48. So this is the only change I have made. Apart from that, the remaining configurations are same. First thing about motor starting analysis, you need to make sure that the motor on which you are trying to perform motor starting analysis is connected to the system. For instance, in this case, my motor crusher 1 3500 HP motor and compressor B 4500 HP motor are in open position. Similarly, pump C 500 HP is in open position. If I will try to perform the motor starting analysis for these three motors, I won't be able to do it. I will get an error in ETAP saying that I have not selected any motor for switching purpose, or I haven't considered any switching event. This can be avoided by considering a configuration in which the motor is open. Or for instance, if you still want to perform the motor starting analysis for such a configuration, then use other motor which is already available in the system, because this is considered in the normal configuration as standby, so this will not be considered by ETAP. So this was one of the important point which you need to take care of. Now to perform motor starting analysis, we need to add some additional data. So what is this additional data? The additional data is, in the previous lecture what we studied, that for performing static motor starting analysis, the most important thing is locked rotor current. Fine, we have already provided the locked rotor current. If I go into any one of my motor, for instance, if I double click on my 4500 HP motor, here you see we have already provided the nameplate data, we adjusted everything here. Similarly, we provided this impedance data or considered as it was. So you can consider anything. If you have the actual data, go for the actual data. If you do not have actual data, then you can use the ETAP calculated data. This model, this is not required. Inertia is not required, because these are the things required in the dynamic analysis, but we need the acceleration time and the static starting. So we need to provide this acceleration time for the static starting. From where we can find this time? This time is already available in the manufacturer nameplate data or the data sheet of the motor itself. So by looking at the motor data sheet or the manufacturer data sheet or the motor nameplate, you can get this data. For this case, we are going to assume that for this 4500 HP motor, my no load is 2 seconds and my full load is 5 seconds. So once I have added this data, I am all set to perform my motor starting analysis. We'll press OK. And for this 3500 HP crusher 2, we'll go to load. In this case, we are going to use no load 2 and full load 4. I'm assuming these values, but based on the actual values, when you will be performing, when you will have actual system data, you can use, but for the practicing, you may use these values. Once we are done with these values, we are all set to perform the motor starting analysis. So how do we perform motor starting analysis? For motor starting analysis, we have to go to this motor starting tab, which is fourth from the left. So we have first this edit mode, then power flow, then short circuit, then arc flash, and then the fourth one is motor acceleration. So this is motor acceleration analysis or motor starting analysis. So we click on this option and there we are. This is my window. But before going to this, let us select the configuration. So this is the easiest configuration I want to perform. The worst case when all the motors are running and my motor starts. So for this purpose, what I'll do, I'll just go to my dynamics and let me select my maximum operating condition in which everything is connected to the system. So now I go to my motor starting analysis, fourth option from the left, and there we are. Next thing we have to do is, if I'll try to perform the motor starting analysis now, nothing should happen because I haven't created any event. So just let us try, just to tell you. If I click, and it is going to ask for the, so let us say we have this time maximum configuration and we are performing a motor starting analysis for 4500 HP compressor. Yeah. So when I press OK, see, I get an error. No switching action is specified for up to the total simulation time. Error 250. So this is telling me that you want to perform the analysis, but you need to perform the switching action. So we'll go and perform the switching action now. So I'll close this one. Let us prepare a switching action. What would be my switching action? So this briefcase, the edit case study, I will go to this edit case study. So then this information, what I want my bus voltages in percentage. This is true. And what kind of solution engine I want to use. So I will go for the adaptive Newton-Raphson method, and the different values are there, the tap, and I'm going to keep them as it is. Low diversity factor I'm not considering. Initial voltage condition is bus initial voltages which have been calculated by the load flow analysis, and the pre-start loading or the pre-start generation I am considering whatever the actual were. So event mode, so this is the event mode where we have to create an event. So what kind of event I am talking about? Number one, action by load transitioning. So just let us deactivate this. Now first we create an event. So what is my event? I am going to add an event. So my event is, you can give it any name. So my event is event 1 compressor B. So I am trying to start compressor B at time 1 second. Okay, so I have added an event, but for this event, what will be my action? So action by element, I will go to add. See what kind of action I have. Do I want to switch on static load? Do I want to switch on MOV? Or do I want to perform any event on the generator or the power grid? Is it start stop event? For me, it's a motor event and it's a start event. And what I'm trying to start? My compressor B. So all the motor names are coming here, and the starting category should be normal. You can select, there are different categories available. When you will model all these categories, you can select whatever you want. So for me, this is a normal category, and I select OK. So I have my event and I have my action for this event. And when I press OK, my event is ready. To perform the analysis, what we will do? So I have already selected this report instead of prompt. Now my report will be saved in maximum 4500 HP. So this is exactly what I want. And for this static analysis, I'm going to select this second option which says run static motor starting. And when I run, ETAP is doing its work, performing the simulation, and there you go. The simulation has been done. And we have this report open, the alert report also open. Let us check if there is something in the alert report. So nothing. So everything seems good. So if I am going to start this motor with my maximum configuration, I may not have any problem. I'm just going to close this one. And you see this timer slider. With this timer slider, what you can do is you can change. So now, for now, what are you seeing? That my grid voltages are 100%, My voltages at buses are here 99.9%, here 98.2%. So these are my voltages at different buses. And what was my event? My event started at 2 seconds. So let me see. 1 second. So let me go to 1 second. So see, at 1 second, when this motor started, my voltages dropped from almost 99% to 93%. If you go back, 98%, and when the motor started, my voltages dropped to 93%. So I have a huge inrush and the voltages are dropping. So this way, you can see that how my motor has impacted my voltages. So I am getting the drop in the voltages. Welcome back to demonstration video of motor static analysis using ETAP. Okay, now before moving forward, I wanted to tell you one thing, that once you create an event, for a quick recap, when you go to event, here I just selected 3 seconds, so make it around 10 second or 12 second. Why we want to make it 10 or 12 second? So I make it 10 second here, total simulation time, and press OK, because if I go to my motor and I might go to my load, I have selected full load to be 5 seconds. So it is going to take almost 3 seconds from going from no load to full load. So that is why I need to see what will be the impact on the system. So if we do this and perform this analysis again, so I'm performing for maximum 4500 HP. Here, once the simulation is performed, there is no alert in the system, so everything seems to be okay for this maximum operating condition. So if I go here, 98.29, at 1 second my motor is going to be switched on. So as soon as my motor is switched on, the voltages are depressed to 93.31, and then it is going to, after, let's see what happens after 5 seconds. So as soon as my motor has started towards full load, the voltages increase again, and now the voltages have increased to 97.93%. What else you can do with this is, you can go to this display window and you can select what type of voltages do you want to see and what kind of power flow you want to see. Do you want to see in the form of amperes or kVA or kilowatt or plus megawatt? Similarly, do you want to see the load rated kV or the bus nominal kV? Similarly, what about the voltages? Do you want to see in the form of kV or in the form of percentage? So I want to see in the form of percentage. I have selected this. You can select whatever you want. When I press OK on this, and now you can also create the plots. So let us create some plot. I'm going to just close this one, and for creating the plots, the starting plots, you go to this window is going to open. So here is my plot window. Restore, because I was creating some plots before, no plots are restored. So I'm going to select no, because I do not want my old plots to be restored. Now here are my different device types. I want to check for my motor. I have only one motor because I created the event for only one motor. So I'm going to select this. And what do I want to see? Number one, I want to see the motor bus base voltage and VT motor base voltage. So let us see the motor base voltage and let us plot, and here it is. Before, the motor was not operating, so the terminal voltage at motor was 0. At 1 second the motor started to operate, and there you see you have this, and for the 5 second it reached its maximum value. As soon as the motor reached its maximum value, the voltages has increased again. Same goes for the, let's see, for the bus voltages. And when I can now task me, windows already displayed, close plotting, yes, I'm going to see yes. And now I have two plots here. One is for, and see what is happening here. So when my terminal voltage is 0, my bus voltages are at its 97-98%. So everything seems to be okay here. But as soon as the motor has started, my voltages had dropped to 93% and remains for 5 seconds, and then it recovers back to as soon as the motor hits its peak value or the full load. If we want to see the line current of the motor, we can simply select this, and when I go plot, yes, so now I have 3 plots here. So this is for the line current, and what is happening here, this is similar to 0 line current is there, but as soon as the motor starts, a huge inrush of current is there, and it remains until the motor is starting, and as soon as the motor reaches its full load, it reduces and goes to its full load current. So this is how you can review the results as well. Welcome to demonstration video of motor starting analysis using ETAP. In this video, we are going to perform dynamic motor starting analysis. So for the dynamic motor starting analysis, we need to provide some additional data for the motors. Before we perform the static motor starting analysis for compressor B, 4500 horsepower, and what did we enter? This is the nameplate data which was entered during load flow and short circuit analysis. Same, this impedance data was kept as it is, and the load data, we introduced acceleration time for the static starting for no load to be 2 seconds and full load to be 5 seconds, and that was it. But now, since we are performing dynamic analysis, we need to provide the model, the equivalent impedance model of the induction motor, as well as the torque speed capability curve and the inertia and the load torque curve. So we have to provide these kind of things. So in order to provide these kind of things, let us start with the data input. So first of all, we will go to model. From here, I'm going to go to library. From the library, I am selecting single 2. So this is that kind of model, and the design class is HV, HS, HT. And what I'm looking for here, I am looking for a 4700. Because the motor I have is 4500 horsepower, so this is the most closely related model, so I am using this. And when I press OK, so now ETAP is asking me that this is the kind of data I will be using for this. Okay, so it is going to be updated accordingly. So I'll ask it to update my data accordingly. And when I press update, there you go. Now we have this torque speed curve, we have this tuning, and everything is ready. So this is the lock rotate current, this with respect to percentage slip. This is the torque speed curve. So I have this data ready now. So my nameplate has also been updated, my impedance has been updated, and my everything related to this has been updated. I will go to inertia, and in the inertia, we have to provide the inertia. So what is the inertia in this case? So WR square here, this value. Let us assume this value to be 6901, but you can get this value from the motor nameplate rating. So here I am assuming the value. Similarly, I am assuming the inertia to be 1.4, H value to be 1.4. So I am done with these two values. So see, and the WR square and H are interrelated to each other with respect to the coupling. So I have given the motor RPM, its inertia, and its H value. So once I am done with this, so now let us go to the load. Now we have to provide the load. For the load, I'll be using polynomial, and for the polynomial, we will be using this raised to power 3, and let us press OK for this. So now this will be my polynomial load curve. So once I have provided these values, so let me check the model for this. So this is my model, so everything seems okay here. So I have this value, this is the typical value I have, and now so I do not need to provide anything else. And when I press OK, so I have everything ready for my dynamic analysis. So for this purpose, let us You can save the case at this moment. So I'll be just performing the analysis, so I'm not saving the case. Then now what we have to do, we will go to motor starting or motor acceleration, and then we will go to event. Let us check what is the event we have. So I'll keep these things as it is, and the event is the same, the starting of this motor, and simulation runtime is 10. I press OK. So now this time let me go to prompt. So from here I'm going to select prompt now, so that I can get the new prompt when this result is calculated. So run motor dynamic analysis. It is going to ask me for the output file. So the name of my output file will be, since I am working with the maximum configuration, so maximum, again it's, so let me say compressor B, and this time it's dynamic, and I press OK, and ETAP is calculating, and there you go. So again, what do we have here? Let's see if we have some kind of, no kind of violation is there, so it's good. So just let us close this one and see what is happening here. So again, the voltages are 98.29%, and when the motor starts at, the event starts at 1, so there is a voltage drop, and then we move on. See, now with the dynamics, the voltages are changing continuously. If you see this, see, the voltages are changing continuously. So this is the difference between your static motor starting analysis and dynamic motor starting analysis. So let us create the graph for this. For making the graph, what I will do, I'm going to select motor starting plot. Let the plot start. So here we have the plot. So we have maximum compressor B dynamic file. I'll go here. I will select my motor, and see, now we have additional data. So what should we plot? Let us see. First of all, let's see the terminal current. What happens to the terminal current when I plot this? So now here's the time. So initially the current is 0. As soon as the motor is started, it goes to its maximum current, and then it reduces, it's reducing, and until it reaches its value, it goes here. And with respect to this, let us plot the motor terminal voltages also at bus base. So there you go. So here you see, so here is the voltage. Let us see the acceleration torque. Let us plot this. So here is the acceleration torque. So isn't it the same torque? This is my, it reaches its breakdown value, and then it reaches its, so this way. And we can also see, so let us just close these plots. You can close these plots, whatever you want. So now let us see how the motor electrical power behaved, and we can combine the plots also. So let us see the electrical and the mechanical power and combine them, and let us plot them. So there you go. So there is this blue curve is the electrical and curve. So here the motor has started and the load is picking up, and here they have reached, and here there is the difference. So this difference is between, this is basically the slip between the motor and the difference between the two torques, and that is how your power is changing in your motor, because motor was started. So electrical power initially jumped, but mechanical power, because now electrical power will continue to increase and ultimately it will go to its value. So this is how you get the different kind of data you can get from here. If you want to see the speed of the motor, now let us see the speed of the motor, and let us plot the speed, or we'll plot on the same. So this is electrical, P mechanical, and this is the speed. So starting from 1 second to 5 seconds, the motor started gaining speed, and ultimately after 5 seconds it has reached its value. So this is how you perform dynamic motor starting analysis, and you try to interpret the results. Welcome to demonstration video of motor starting analysis using ETAP. Now that we have discussed the static and dynamic motor starting, now the one thing is that in the previous videos what we were doing, we were performing the motor starting analysis for just one motor. However, this is not necessary. You can create multiple events also. You can check starting of multiple motors also. So in this video, we are going to test starting of two motors. Number one, my compressor B 4500 HP along with my pump C 500 HP. And I'm going to perform static analysis, but you can go ahead and then perform dynamic analysis for this as well. So we already have the data here. If I double click on this motor and go to load for static, we already provided this dynamic data. This will not be used when I'll be performing static analysis. So acceleration time 2 seconds and 5. So this is already there. For my pump C, let us assume these times as well. I will go to load, and here let us assume the following times: 2 and full load 6, and I'll press OK. And to make the situation more worse, let us select this minimum operating condition in which we have each transformer feeding its respective load. So now what is going to happen? In this case, the impedance of the system has reduced. You see, from here, here, only one transformer is connecting each of the bus of this system. So logically what should happen, we should not see more voltage drop here, but voltage drop will be high on this side. And to make the matters worse, we are trying to switch on two motors. So to create the event, how we will do this? We will go to motor starting analysis. From this event, I'm going to select and create my event. If you see, I already have event 1 where I am starting compressor B. So let us add another event. Let's go to add. Let us make an event. Let's call this event 2, and it's pump C. And this is going to be started 1 second after the start of the first event. So let us give this time 2 seconds and press OK. Now for this event, we need to provide some actions. So what is the action? I'm going to add an action. I have a motor which is going to be started, and the motor is pump C. It will be started at normal category. I press OK and press OK. So I have my event created. Next thing is, from here I'm going to select prompt, because this is a new event I am trying to simulate. And for this event, I will go to static motor starting analysis. So this time it is minimum simultaneous, and I press OK. You can give whatever name you want. I'm going to press OK, and motor starting analysis is being performed. And this time, because the condition was worse, I'm seeing some under voltages. So I'm having at bus bar 1B and bus bar 2B, I'm seeing low voltages, and the voltages are reaching almost 2 seconds, and they are there for the duration of almost 6 seconds. The voltage drop remains for 6 seconds. And similarly, the different nodes and all these different nodes, they have the voltage drop, but still it is not that bad. So it is there, but depending upon your requirement, you have to see that is it okay or not. So I'll just close this and let us see here. So now for this minimum condition, my voltages are 99.27. Starting voltages here 99.22, here 99.96. So voltages are pretty good on each bus. So let's see what happens on these two buses, because these are my concern buses, my bus B and bus 1B. So let us see what happens. And another thing, you will see that here 99.27, but here voltage 97.36, here 99.22, 96. Why the difference is there? The difference is there because These two transformers are operating separately, so the load for each is being separate. That is why you have different voltages here, because the impedance, although the impedance is same, but the load connected on each side is different. So first event is going to happen at 1 second. So if I go to 1 second, my voltage is dropped to 91.65, here 91.23. And if I go to 2 seconds, so now voltages are going to remain this, because this is static analysis, this is going to remain the same. But as soon as I go to 2 seconds, the voltages are dropped further to 90.76, and here 82, and here 85. Why? Because now my second motor is starting when my first motor was, and if you see here, the voltages drop here is not that much, because due to this opening. And this way you can try different simulation. What you could have done is, you can take one event from here, one event from here, or one event from here, or make whatever you want. But this is how this is done. Welcome to Power System Analysis using ETAP. In this lecture, we are going to discuss optimal capacitor placement. Capacitor plays a very vital role in the industrial network. So let us see why it is necessary and why do we need this feature in ETAP for this capacitor placement. So most of the load in modern electrical distribution system are inductive. So the example of such a load is motor load, transformer, tube lighting, induction furnaces. So and what is the most important thing about this motor load? You know that in this motor load or inductive load, why this load is called inductive? Because anything which has magnetic field associated with it is known as an inductive load. So inductive load needs a magnetic field to operate. Now for inductive load to operate, we will have two kind of things. You have seen that when we were running this load flow analysis also, we had two values available, the active power and the reactive power. So what is this active power? The working power to perform the actual work of creating heat, light, motion, machine output and so on is known as active power. So which is calculated in megawatt or kilowatt. Whereas the reactive power, kilowatt or the megawatt, is to sustain this magnetic field. So the working power consumes watts and can be read on wattmeter. It is measured in kilowatts, megawatts, and reactive power doesn't do useful work, but circulates between the generator and the load. So basically it's a magnetic field which is continuously circulating between the generation and the load. It places a heavier drain on the power source as well as on the power sources distribution system. So reactive power is measured in kilowatts or kVAR or MVAR. So this is what we mean by. So how do we demonstrate or say this power in? So we use this term apparent power or the kVA power. That's why you have seen that these motor or these generators or these transformers, all these have this power in MVA or kVA, or basically apparent power. It's not in megawatt. The reason is this, because each of this equipment have some inductive load associated with it. So when the power will flow through them, it will be a combination of your active power and the reactive power. A simple example of the resistive load or the active power load is this lighting load or this resistance element or the heating plate. What will happen in this case? Only active power will flow through the system. Whereas in the case of reactive, you have this in case of a motor. When you energize the motor, you have this magnetic field associated with it. So inductive motor, what it does, it creates a magnetic field, which this magnetic field interacts with your stator and with your rotor, and you have this rotation in this. So as a result of this, this magnetic field will move back and forth between the generator and the motor, between the inductive load and the motor. So as a result of this, some kVAR power or reactive power will flow into the system. And what will be the, when you combine these two, we are going to get kVA or MVA or apparent power, in which we will have this resistive element as well as we will have inductive element. So the heat, the component which is basically doing the work, will be associated with the active power, and only the rotating, the workless thing or the workless quantity, which will just move back and forth between the load and the generation, will be known as the circulating component or the no work component. And how we can represent, if we say that this is the kVA power, then the cos of this will be known as the active power, and the perpendicular part or the sine part will be known as the reactive power. And whereas cos theta is also known as the power factor, which is basically equal to your active power divided by your VA. So basically this is the factor which is telling you how much actual work is being done from the apparent power available in the system or in any equipment. So power factor and its impact on the industrial system. So power factor is the ratio of the working to apparent power. It measures how effectively the electrical power is being used. A high power factor signals efficient utilization of electrical power, while a low power factor indicates poor utilization of electrical power, and which can be seen with the help of here as well. Because kVA is the combination of your active power and the reactive power, if you reduce this reactive power in the system, it means you can increase your active power for the same kVA or the MVA capacity. So here in this case, if we have a 142 kVA system having a 100 kilowatt of active power, so in this case power factor will be 100 divided by 142 is equal to 70% or 0.7. Whereas if we have the same active power, if we maintain the same active power, what we can do, we can increase the power. So in this case, for the same active power, if we reduce this reactive power, what will our number one, the apparent power will reduce, and the second, my efficiency will improve. And this same idea is used in the industrial installations. So what we do in order, because in industrial installations, basically we are charged with this value of reactive power also. Apart from active power, like in this residential systems or the commercial system, we usually are charged with active power only. Our energy meters only charge us with active power. Whereas in industrial load, they are charged from active as well as reactive power. So power factor can be improved by adding power factor correction capacitors to the industrial and the distribution system. So in order to reduce this reactive power, what we do, we install capacitors in our system. Theoretically, capacitor could provide 100% of the needed reactive power. In practical usage, however, power factor correction to approximately 95% provides maximum benefit. So in order to get the maximum benefit out of the system, what we will do, we will compensate our system with at least 95% of this reactive power. And how do we do it? Here's a simple example. So let's say we have a 18 ampere load flowing from the system towards the motor. So we have a 100 HP, 10 HP motor with a 480 volt, at a 480 volt, having a power factor of 84%. Now, this current is basically the combination of your active power as well as reactive power, because we know that motor is an inductive load. It is going to consume some reactive power as well. So what we can do, if we try to provide this additional reactive power from the capacitor bank. So here in this case, we can connect a 3 kVAr capacitor bank. So what will happen in this case? In this case, the power or the current coming from the system will reduce. So instead of now 18 ampere, we are only using 16 ampere, because the additional 3.6 ampere of the reactive power is coming from the capacitor bank. So power factor improved to 95% and the line current reduced to 11%. So this 11% reduction in current is basically your reduction in your utility bill. So this is how this is done. Or in other words, here we see that we have a system with a 100 kilowatt active power and 33 kilowatt reactive power. So this was the system. Now, if I want to improve the power for the same, what I can do, if I wanted to consume 100 kVA additional power in the system, what I had to do was I had to reduce my active power or the efficiency of the system, or my power factor was reduced. So what could I have done? If I include capacitor bank in my system, so by adding the capacitor banks in the system, I can maintain the same power factor which I was maintaining before, without any reducing the efficiency of my system or power factor of my system. So What are the benefits of these capacitor banks? In general, capacitor banks are installed in power system for voltage support. We have seen that they can provide voltage support for the power correction, reactive power control, loss reduction. We have also seen that how they control the loss, system capacity increment, and the billing charge reduction. This process involves determining the capacitor size, location, control method, and the connection type. The main effort usually is to determine the capacitor size and location for the voltage support and power factor correction. Secondary considerations are the harmonics and the switching transient. So where do we need to install this capacitor bank? This is the most important question. Now, how we can answer this question? There are several ways to answer this question. The most common method to answer this question is to go with this thumb rule of performing this hit and trial method. So what are you going to do? Your requirement is to improve the voltages. Your requirement is to reduce the reactive losses, and your requirement is to improve the power factor correction. So you can calculate the power factor correction from the theoretical method we have seen before, but where to place this capacitor bank? So what you are going to do, you are going to perform several load flow analysis in which you will use this different sizes. You will try different sizes at different locations and perform load flow calculation again, and you are going to do this again and again and again until you find the value which is optimum, until you go with the optimum solution. If you have a small system of 2 buses or 3 buses, for this system, maybe this method will be okay. But if we assume that we have a huge system, large system of 20 buses or 100 buses or 200 buses, in this case, this will not work. Now, what we can do, another proper method of this is to use optimum power flow. So optimum power flow basically uses an optimization engine. We tell them that, okay, I want to minimize this, I want to maximize this. So we provide different kind of objectives to the optimization engine. And then we provide the constraints. And with the help of these constraints and this objective function, optimum power flow tries to find the optimum point where the system can be operated. Now this can be used to optimize the capacitor size based on the candidate location selected by the engineer. This method requires pre-selected locations, since OPF can optimize the capacitor size but not the location. So for this purpose, yeah, you will get the advantage. So you get at least one advantage out of it, that you do not have to worry about the size, because the size will be told by optimum power flow. Optimum power flow, after performing this optimum load flow analysis, will try to tell you, okay, fine, this value of capacitor will be enough in order to minimize the system losses or increase the system voltage profile. But at the same time, it won't tell you about the location. Location would have to be told by the engineer. So again, you reduce some work, but still you have to do some work. So now what is the solution? What is the optimum solution or the final solution to this? So, or the most effective solution. So the most effective solution is to use the optimal capacitor placement method. So optimal capacitor placement, or OCP, will optimize the capacitor size and the location with respect to the cost consideration. OCP employs a genetic algorithm, which is an optimization technique based on the theory of nature selection. So this is the type of optimization technique which is used. And what does OCP do? OCP uses this present worth method to do alternative comparisons. It considers initial installation and operating cost, which includes the maintenance, depreciation, and interest cost. So in other words, you can include additional data into this as well. That, okay, what will be my operational cost? What is my initial cost I need to take care of? How much reduction in cost I am looking for? So it will take care of all these. And this is one of the technique. That method and the technique which we have mentioned here is basically used by the ETAP. In reality, or from the research point of view, there are several other techniques available as well. But since we are discussing ETAP, so we will discuss. So no need to go into the details of this. We will just see, okay, fine, we have this technique available. Now we have to see how to implement this technique. So for this purpose, we need to know about the optimization problem. Now the optimization problem we have is, so what is the problem here? The problem here is that the load in the system, or if we talk about this distribution system or industrial system, the load may vary with respect to time. In the morning, maybe the lightning load will not be there. or some of the motors or some of the pumps will not be operating, but in the night time your AC or some other type of load, so you have a changing load. So first of all you need to take care that my capacitor should be enough for all these combinations. So with this changing load, my capacitor should cover all this variation of changing load. So number one, so we have to give the objective function, that my objective function is, so to formulate this problem, we are going to tell, okay, what is my problem? So number one, my problem here is that I have a changing load. Then I have a problem that I need to reduce the cost in the system, because I should not have, maybe if I use a 10 kVAr capacitor, it may be okay for the peak load, but during the off-peak load, it may be more than enough. So what I have to do, I have to switch off this capacitor. So I am not basically utilizing the capacitor that much. So I have to use the capacitor in a way that I can optimally use it. I can minimize the overall system cost. I can maximize the system voltage profile. I can reduce the reactive power losses in the system. So this is my objective function. So the first thing when defining the problem, the optimization problem, is to define the objective function. What is the objective I want from this optimization method? And the second thing is, what is my system constraints, or what are my constraints? So in this particular case, what will be my constraint? My constraint is the changing load. I have a changing load. Other is the capacitor bank size. The third one is the location of the capacitor. The fourth one is what should be the voltage profile, in how much range my voltage profile should be, how much losses I need to maintain, what can be the maximum or the minimum losses. So these can be different kind of constraints which I have to provide to this optimization or the OCP in the system. So once I have provided it with the objective function and I have provided it with the possible constraints, then I can perform this optimization on the ETAP. So for this purpose, we are going to consider a one distribution system. We are going to see this in our demonstration video, what kind of system we have. For this system, we are assuming different these kind of constraints, that the design loading is 55%. So from this load curve, I can from the load curve, I've determined that most of the time my load will remain within the 55% design loading range, whereas for the 25% of the time my load may increase my maximum loading. And similarly, for the 20% of the time, my load may be less than my design load, 90% of the design load. So I have this maximum load, minimum load, and the normal operating load. So I have this changing load. I need a capacitor in such a way that it should take care of all the load. Similarly, my average energy cost is around $0.07 per kilowatt hour. So I want to either reduce it or maintain this. I do not want my reactive this cost to increase. Similarly, I want a capacitor which should work for at least 10 years. And for this, some constraints for the capacitors are that maximum size of the capacitor can be for the 4.16 kV, 200 kVAr bank. The purchasing cost is $20 per kilowatt hour. Installation cost is around $1,200 and the operating cost is $200 per year. So if I increase the size of the capacitor, it means that my operating cost will increase. My purchase cost will increase. So I need to take care of this. Similarly, for the 13.8 kV, I'm assuming that 300 kVAr bank can be the size and the purchase cost is $25 per kilowatt. Installation cost is around $1,600 and operating cost is $300 per year. Welcome to optimal capacitor placement demonstration video. So now we are using the same case which we have been using for our previous analysis. This is a sample industrial system. For this, we want to know that how much capacitors will be enough in order to maintain the system voltages. So for this purpose, first of all, let us perform the load flow analysis. Let's perform first load flow analysis. For load flow analysis, let us select the most conservative operating condition, which in our case, which was this maximum system. And this maximum system, we are assuming that everything is connected to the system. So this way, we are going to have the worst possible voltages. So for this purpose, when I perform the load flow analysis, there it is. Our voltages are 97% on the 4.16 and 0.48 kV bus, whereas on 13.8 kV bus we have 98% of voltages. But one important thing to note here is the tap position. If we see the tap position, in this case we had to adjust the tap in order to maintain the voltages. So what if I make the tap principal again? So I'm making it for all the 4 transformers which we adjusted the tap, and let us solve again. Let me select maximum system from here. So this is my maximum load. Let us solve. So here now my voltages are as low as 92.85%, and here 94.78, here 98%. So without tap adjustment the voltages are pretty low. So how about use the method of capacitor placement, optimal capacitor placement, in order to know if I want to improve my voltages to a higher value? How can I do that? For this purpose, let us go to optimal capacitor placement. So when I select this is the window for, let us first go to the case study and see what is in there. For the case study, what are the different objectives? For me, my objective is just to maintain the voltage. So I want voltage support from the capacitor banks. The average energy cost, I am assuming it to be 0.07. Usually the default value given here is 0.06. So you can select whatever value you want. Similarly, the planning period is by default 5. I have selected to 10. So this is my adjustments here in the info page. For the loading page, I am assuming the design load. Similarly, the load diversity factor is to be the global one, and for the load time distribution of the load, 20% for the minimum, average 55%, and maximum load 25%. This is exactly the same which we assumed in the lecture for the example case. So for the voltage constraint, by default the voltage constraint comes with 110% and 90%. So let us first go more conservative and see what happens. How about if I select a very tight schedule from 102 to 98? So I want to improve my voltages up on a very tight schedule. Power factor I'm not considering, so even if I have whatever value I have, it won't matter. Similarly, for the capacitors, here are the different capacitor info available for the 0.48, 0.6, 2.4. So if we see here, we have 2 buses, 3 type of buses. One is 13.8, then we have 4.16, and then we have 0.48. So we have for 0.48 and 13.8, but in this you will not see that we have 4.16. So let us take the assumption which we studied in our lecture. To add anything in here, you have to simply go to add. A new line will be added. So here in this case I am entering for 4.16 kV. My bank size is 200 megawatt, and maximum number of banks, let us assume to be 10. The purchase cost for each bank is $20 per kilowatt. The install cost is $1,200, and operational cost is $200 per year. So once I select these values, there you go, they are added. For the adjustment, I do not want any tolerance to be considered, so I have unchecked every one of these conditions. So once I have done this, I press OK. Now to solve the case, we can use this run optimal capacitor placement. And since here prompt is selected for the output, so it is going to ask me to save the case. So I am selecting my maximum system configuration, and which is conservative. So it's a pretty conservative one. So let us select OK. ETAP is going to solve. So we forgot to select the buses. So first of all, let us select the bus. For selecting the bus, we go to edit case study. We go to capacitors. From here we have to select. So we have 4.16, 0.48 and 13.8. So these are my candidate locations. You can select whatever you want. So let us press OK and solve. So now we are going to run, and there you go. So in order to maintain the voltages between the tight range, we have said we will be requiring 9 capacitor banks of 300 kVR rating at 13.8 kV location here, and 9 here. So 9 here, 4 here, and 10 here, because we had more machines and more motors on this side of the load. Similarly, here 4 and 3. So you see how high the requirement, or this is the requirement, because this high requirement is most probably due to my constraints. So let us reduce the constraint. How about I go here, and instead of this voltage constraint, I select a large constraint of 105 to 95%. And when I press OK, let us just select maximum system here and run the simulation again. And now in this case, see, my requirement has reduced a lot. Now I only require 8 here and 7 banks here. So this way you can perform this analysis. And to review the results can be reviewed from here, the report manager. You will go to report manager, you are going to see various kind of result, and from there you can check that what is the requirement, what will be the total cost and everything. So let us go here. Now what I want to select is, here I have different kind of summaries. So let us see in summary, what is my summary saying. Let us press on OK. So here my file has been created. So now it is telling me the bus loading report for the maximum loading. So the summary for the load report is here. So what are my base kV, what are my load, what are the different kind of power factors I have on each bus, the amplitude and everything. So if I want to know about my capacitors, I can go to the results and I can select. There are different reports, because you see, let us go to OCP results, because it has to perform load flow for 3 conditions: the maximum, the minimum and the average. So here it is. So we require one at 4.16. The rated value is 200 kVR per bank at rated kV of 4.8. So I require 8 banks here. So total requirement is 1.6 megawatt. And the installation, this is the installation cost, this is the total cost. So the total costs are being shown here. So for this purpose, I'll be requiring 15 banks. So if I have this 15 bank or 2.3 megawatt of reactive power compensation, my voltages shall remain between 105 and 95%. But if I want to increase it, then this value will increase as well. So this way you can perform optimal capacitor placement. Welcome to optimal capacitor placement second demonstration video. In this demonstration, we are assuming that we have a certain distribution system which is connected. This is the 132 kV source which is connected to the main system, and the main system is connected to 2 distribution feeder with the help of 240 MVA transformers. And this is the first feeder which has distributed load at different locations. Similarly, this is the second feeder which has and for the second feeder we have detailed some load at the 4.6 kV level as well. So there are some industries which are connected with the help of these transformers, and they have some industrial load going to different locations. So this is a case. Now in this case we want to see that if we want to maintain the power factor, because in distribution system one of the important point is to maintain the power factor. The power factor should be maintained on the distribution side to be around 0.95. Usually it is said in the distribution codes that the power factor should not fall below 95%. So for this, in the previous example we saw that how we can maintain voltages. In this example we are going to see how much capacitor requirement will be there if we only want to maintain the power factor. For For this purpose, again, let us first perform the power flow and see what is the requirement here or what is happening in this case. So I select load flow. I run load flow. And if you see, this case has a pretty much voltage problem here. Even at the tail end of the system, the voltages are well below 90% as well. So this means that this system does require reactive power compensation. So how much compensation is required? We will see. Okay, for this purpose, now again, let us go to optimal capacitor placement. So I select this. Let us go to edit case study. In this case, let us assume power factor correction only. So because we want to see what is going to happen if I want to improve the power factor on the board distribution feeder, how much capacitor banks I require. So the cost I'm assuming the same, $0.07 per kilowatt hour. By default, this value is 0.06 and planning period I am assuming to be 10 years. By default, this value is 5. For the loading, again, default loading, I am using design loading with the global load diversity factor, and the time distribution of load is 20%, 55% and 25%. This will be as per your requirement. So you can change it depending upon the requirement what you are studying. Voltage constraints, I am not worried about voltage constraint because I haven't considered this in my study. For the power constraints, I want my power factor to be 95%. So let us see whether I am able to solve this optimizer is able to resolve or calculate the capacitor values with this power factor of 95% or not. Similarly, for the capacitors, we have added the value of 4.16 here. The same value, you can add it if you want to add any value, you can use this add new capacitor. If you want to delete any entry, you can simply use delete. For me, I am using all the locations to be candid locations because this is a distribution feeders. So each point of the distribution feeder from where the load is going can be a candid location. So I want to see which are my best locations for installing these capacitors. For the adjustment, I am not using any tolerance. So let us press OK. Now perform the optimal capacitor placement. Let us run and see if ETAP is able to solve or not. So once the case has solved, let us see that just in order to improve the capacitor, we require a huge amount of capacitor in this case. So you see that at tail end here at 13.8 kV location, I require 15. Here 8. So at each point I require some capacitor banks in order to improve. But if I provide these amount of capacitors in my system, then I can improve the power factor, and my power factor will not be dropped below 95% for the transmission system. So this way you can improve the capacitor. So you can calculate the requirement of capacitors. So if you want to see the results, seeing the result is simple. You will simply go to report manager. In this case, let us select result and OCP result. When I press OK, there my results are displayed. So in this case, my requirement is 75. So it's a huge requirement, but this was just the case to show you how you will require, and this will require a huge investment in the capacitor for just the two. But this was just a sample case to make use or make you sure that how this capacitor placement optimization can be used. In the real world, this will be far less than this. Welcome to Power System Analysis using ETAP. In this lecture, we are going to discuss the modeling of solar PV system in ETAP. But before going to the modeling process or jumping on to ETAP, we are going to get know-how or some basics related to solar PV system. As you know that solar PV system is the upcoming technology or the latest technology which is in phase, which is working nowadays, and it is very important to able to model these kind of systems in your simulation software. So what is a solar PV system? Before starting solar PV system, we need to understand what is PV. PV stands for photovoltaic, and a photovoltaic system is a kind of a system that converts the sun's radiation in the form of light into usable electricity. So what happens in this case is that you have some kind of a solar panel, which is a basically power electronics device. So this solar panel is basically a power electronics device, which is a combination of many solar cells. When sunlight falls onto this solar cells, this solar light or this solar irradiation or the photons from the solar energy converts this photons or the solar energy into DC electrical energy. So once we have this DC electrical energy, we can convert this energy either into AC or we can use it directly as a DC energy. As far as the components are concerned, a solar PV system consists of PV arrays, the charge controller, the battery system, which can be used to store this energy for the off sun period, for instance, because the solar energy will usually be available during the daytime. If you want to use the solar energy during the night time also, what you can do is you can store some of the energy into your battery system and then you can use it later. And then we have this inverter, which will convert this DC power into AC power. From the application point of view, we can distribute or we can divide solar PV system applications into two types of systems. One is this on-grid solar system and the other one is the off-grid solar system. When we talk about on-grid solar system, what we are basically talking about is a net metering system, net billing or self-consumption system. So this is a kind of a system in which your solar panels provide energy direct to the grid, to the electrical system, to your distribution system or your transmission system. So for instance, if you have rooftop solar PV installed in your system and it is connected with the help of a net meter, so what is this net meter going to do, or what this net billing is going to do, is it is going to calculate how much energy was taken from the grid and how much energy was sent to the grid. So the difference between the two will be your net bill or your net energy consumption. Whereas off-grid systems are kind of system which are completely isolated from the system grid or the electrical grid. So it will not be connected to your grid system or the big electricity system which is running in the entire country. So it will be a standalone working, feeding the load of some house or maybe feeding some particular equipment, or it can be anything. So these are basically standalone. They can be hybrid system as well. So how you can make them hybrid? Hybrid can be made with the help of, you have this solar PV, then some batteries, and as a backup, your battery is going to be one kind of backup. If you want to provide additional backup, what you can have is a DG set. So this DG set or the diesel generator set will be will provide similar capability which is provided by the grid, that whenever you do not have electricity available from the off-grid solar system, the energy is then going to come from an outside source. So this outside source can either be a power grid or it can be a diesel generator set. And another example of off-grid solar system is solar pumping, which is becoming very famous nowadays. So when we talk about this net metering systems, what is a net metering system? A net metering system is a kind of a system which connects your renewable generation or your solar PV generation to the electrical grid itself. So how it works? It's pretty simple. You have certain kind of renewable generation. For instance, in this case, we are talking about solar PV system. So you will have a number of solar PV panels in your system. These solar PV panels are going to provide you with DC electricity or DC current. So this DC current is going to be converted into AC current with the help of inverter. And this inverter will be connected to your meter. And these type of meter are bidirectional meter, meaning that it can calculate the power going out of the system or going out of the house and power coming into the system. And when we say net meter means that at the end of the month or at the end of the week, depending upon what is your billing cycle, based on the billing cycle, it is going to differentiate between the two, that these were the amount of units which were provided to the grid through this home solar system, and this is the number of units which was taken from the system, and the difference of the two will be your net meter. So this will be the net consumption of your household system. So net billing, what do we mean by net billing? Net billing differentiate from this your net metering through a little bit difference. So what is the difference here? In this particular case, what we have is we have different kind of tariffs. So we define the regulator or your power system utility, which is providing you this capability of net billing or net metering or the feed-in tariff. What it is going to do is it is going to provide you with two kind of tariffs. One will be your import tariff or your feed out tariff. So what do we mean by feed out tariff? Feed out tariff is your general tariff which you usually use. So you have your house, in your house you have different kind of appliances, and these appliances run on electricity, right? So you need electricity from the grid. So when you take electricity from the grid, it is read by the meter, or it is stored, the consumption of electricity is stored in the meter, and you pay your utility at the end of each month the amount of electricity you used. Whereas now in case of net billing, what this electricity utility is going to do, or electric utility is going to do, is it is going to provide you with another set of tariff. This tariff will be specifically for power out or feed in. So what do we mean by feed in here? If there is some source of electricity generation within the house, so this amount of electricity will be provided to the grid at a different rate. So your input power is going to have a different rate. Your power which is being generated by you for the system is going to have a different rate. And at the end of the month, what electric utility is going to do is it is going to calculate the difference between the two and provide you with a net bill. Now the third type of system is a self-consumption system. So what is a self-consumption system? In case of a self-consumption system, if you design your system in a way that it is a self-consumption system, in this particular case, this is something similar to net metering or net billing consumption. But now the objective has changed here. In this particular case, our objective will be that no additional power is supplied to the grid. So what we want to do is we want to maintain a standalone system which has a backup power from the electrical utility, but we do not provide any power to the grid itself. And how we can manage that? That can be managed with the help of a central controller. Or you must have heard about this hybrid PV controller nowadays. Hybrid PV inverters are very becoming very trendy and very famous nowadays. So these kind of hybrid PV controllers, hybrid PV inverters have this capability available in them. So they have this controller, and the objective or the task of this controller is to make sure that you consume the electrical load within the house or industry or whatever kind of load there is. The electricity consumed by this electrical load is provided by the PV system. It just keeps you connected with the electrical grid, so that if something happens to this PV system, then only you can get some power from here, or you can define some amount of objective that I only want this much amount of power, or I want power from the electrical grid for this particular condition. So this controller will make sure that you get the electricity from the grid for this particular condition. So these kind of systems are self-consumption system, where they, with the help of this controller, you try to feed the entire load of your system or your facility with the help of solar PV, thereby reducing the import or export from the electrical grid. So what will be the combination of your self-consumption system, zero export system? So here is another way of showing an self-consumption system. Here in this kind of a system, you do not have any connection to your grid, outside grid. So like for instance, in this case, here we had a connection to the grid. So here in this case, what we have done is we have removed any kind of combination to the external grid. This means this is going to be a kind of a standalone system. So whatever energy or whatever the load you have in your system needs to be fed by the solar system itself. So now in this case, the solar system has to be designed in such a way that your electrical appliances load for the 24 hours should be able to feed from the solar PV system. So how we can store the energy? The energy can be stored only in one way, with the help of this battery system. So for a standalone system or a self-consumption zero export system or a complete standalone or a system, what we want is, in this case, two additional equipments will come. If you see for your net metering or your for zero export connected to grid, you did not require this, your charge controller and battery bank, because whatever energy was generated by the solar system will be directly provided to the grid, or the load, or whatever deficiency is there in the solar system will be taken care of by the external grid. But since when you do not have an external grid, what do you want? You have to take care of your load during evening time or night time, and also during the cloudy period or the rainy days. So in order to cover those periods as well, now you require an additional setup which consists of your charge controller and battery bank. So what will happen in this case is, the energy generated by your solar PV system will be modulated by the charge controller. It is going to make sure that the voltages remain at a particular level. The voltages do not vary a lot because we want to charge our batteries. So charge controller makes sure that we are tracking the maximum point on the solar PV system. And then what we are going to do is, this charge controller is going to provide whatever DC power is being generated to the battery. And once we have this battery, these batteries will further be connected to your inverter. And what this inverter is going to do is, inverter is going to convert the DC power available in the system into AC power, and with the help of this distribution board, the power is then going to be distributed throughout the house or throughout the facility to different kind of electrical load. Now, diesel generation PV hybrid system. So when we talk about this hybrid system, what is going to happen in this hybrid system? So hybrid system can be of two types. The first type we saw before was where we had this hybrid, we have this net zero combination, where you have this connection to the electrical grid, but you are making sure that no power is exported to the grid. So what if you are located in a location where you do not have any kind of external grid? So how you can connect your PV system to feed the electrical utility? Because the problem with this PV system is that it can provide you with energy only during sun hours or during the daytime when sun is there. But during evening time or night time when sun is not there, we are not going to have any kind of energy available from PV system. So in this case, if we are at a location where no electrical connection is available, what we can do is we can optimize this system by connecting it to the diesel generator set. So here what is happening, here is a standalone facility, you can call it an industrial facility or an electrical facility, whatever kind of facility you have. So it is connected to the, so this has two kind of inputs, electrical inputs. One is this diesel generator set and the other one is this solar PV setup. So what will happen in this case is, and you have this central controller here. So what is going to happen is, during daytime, your solar PV is going to provide electrical energy to your facility through this, passing through this controller or this inverter. But during evening time or during cloud time or during rainy days or during night time, when this solar or sunlight is not available, this power, the power which was generated by the solar PV will be replaced by the diesel generation set. So now with the help of this, what basically we are trying to do is we are trying to reduce the cost of this generation, diesel generation, by displacing some of its power by solar PV system. So this is how we displace the power. So for instance, let us assume that this green part is basically your electrical load. Now your PV system, as I said, can provide you power only during daytime. So starting from 6 in the morning to maybe 6 or 7 in the evening, you are going to have some sunlight available. And this sunlight also is going to vary throughout the day, because you know that during sunrise and sunset, the intensity of light is going to be less. But during noon or afternoon, this amount of sunlight available will be high. So based on this, we have this electrical power which is being generated from the solar PV system. So now during this time, during the night time here and during the evening time here, what we are doing is we are generating the electrical power for this load with the help of diesel generator set. But during the daytime, when sunlight is available, this diesel generation energy is displaced to a certain extent by the solar PV system. So this way, what we have done is we have reduced the diesel generation operating cost for a certain duration of time. Before, this whole area, so if we put it like this, before, this whole area had to be provided with the help of diesel generation set. So your operational cost will be, say, C1. But now a part of this cost is being taken up by this solar PV system. So let's say the generation of the number of units or the cost is this C2. So now we have reduced the cost of C2. So now my net cost, reduction in net cost will become C1 minus C2, because this part, during this time we do not require any kind of diesel generation, or we have reduced the diesel generation required during this time when we have solar generation available. Welcome to Power System Analysis using ETAP course. In this lecture, we are going to continue with some basics of PV system. So before we discussed about the different kind of applications we can have in our PV systems. So now we are going to get a little bit of more detail about the PV system components. But before going into PV system components, why it was necessary to tell you about different applications? It was important because as a power system studies engineer or as a power system analyst, it will be your job to study the impact of this solar system onto the existing facility, or say you are designing a new industrial facility in which some part of this load would be fed by this PV system. So first of all, you need to know, okay, what kind of PV systems are available or working throughout the industry and which will be the best for this particular kind of industry. And once you know that, okay, fine, this kind of equipment or this kind of system is going to be best for this kind of industrial facility, then you have to study it. So for the sake of study, we have already seen, for the good example is that throughout this course we considered an example of an industrial system. So let's say we have the same particular industrial system and now we want to add solar PV into this particular system. So now what we need to do is we already performed load flow analysis, short circuit analysis, transient stability analysis, motor starting analysis for that kind of a particular system. Now once we add this new type of generation into the system, what is going to happen? Now the impact of the system is going to change. Your power flows are going to change. So now as a system analyst, it is going to be your job in order to understand how the system is going to respond with this new addition into the system. Having said that, now let us move back to the solar PV system. Now the solar PV system consists of various components. And what are the main components within this system? These are the PV modules. The basic job of this PV modules or this photovoltaic module is to convert your sunlight into DC current. Then we have this solar inverters. What are these solar inverters going to do? These solar inverters are going to convert your DC electrical power into AC electrical power, which can be used by the system, because most of our system are in AC form, or appliances or systems, they are designed for AC type of power. So we need a certain kind of an inverter which can convert this DC power generated by the solar PV modules into AC power. Then we need some kind of a mounting structure. So what will be this mounting structure? This mounting structure will be the structure which is going to tell us how we are going to place our solar panels or the solar modules. So solar modules cannot be just laid flat onto the earth surface, right? So for instance, we have this rooftop or we have this ground level. This cannot happen that we just simply place like this and wait for the solar light to flow like this. So we need to place our solar panels at a certain angle, at a certain design. So we need a kind of a mounting system which is going to make sure upon which, so this is a mounting system upon which we are going to place our solar panels. So we need a certain kind of a mounting structure. So we will discuss about a little bit about mounting structure as well, and these mounting structures have an impact on the solar generation. Then balance of the system. What do we mean by balance of the system? So we have this solar panel. So this solar panel is going to take the sunlight and convert this power into DC power. This DC power is fed into inverter, and then this inverter, from the inverter side we get this AC power. So this is our natural flow, right? Now at this location, because there is going to be some cable which is going to connect my solar PV panel to my inverter. So this cable is an example of balance of system. Similarly, in order to protect this cable or protect this solar PV module from any kind of fault occurring within this solar PV system, we will be needing some kind of circuit breaker or fuses. So these fuses or circuit breakers is another kind of balance of system. So all the cables, all the fuses, all the circuit breakers which we require in order to protect this system or in order to connect this system will be considered as balance of system. Then we may require some kind of monitoring system, and when we talk about monitoring system, this monitoring system will not, you can say that this is not going to affect how our system is going to react or how my system is going to operate. This only tells us about how the system is operating. So we can monitor with the help of some mobile app or some computer app or computer software which is going to tell, okay, at this particular time I am generating this much amount of electrical power. Similarly, at the same time, this is my electrical load. So if I'm able to consume the whole power or something like this, or what is the total amount of power kilowatt hour which is generated during the day or during the week, or what was my load consumption during the entire month or during entire day. So it's some kind of statistical analysis, or if you have some batteries in the system, what is the effective charging of these batteries and things like this. These can be covered with the help of monitoring system. Once we move to this off-grid system, then we need two additional equipment. These additional equipment are the charge controller. Here we require charge controller, which is going to make sure that input provided to the battery is at a particular level of current and voltage, so that we can avoid fluctuation in current and voltages for the battery. So this can be done with the help of a charge controller, and then so this charge controller is going to take care of this part, and then we need a storage system in itself, which is a combination of batteries in order to store the amount of energy which is being generated by this solar PV system or this solar module. And then this battery is going to be connected to the inverter, and then we are going to have the output. So these are the different kind of components we require when we need to design a solar PV system. Now let us go into the detail of each and every kind of equipment we already discussed. So the first part is this photovoltaic module. So what is a photovoltaic module? It is responsible for connecting the sunlight. It is the most expensive part in the PV system, and it is the most largest part of the PV system as well. So what do I mean by the largest part? You are going to require a number of solar PV panels. So for instance, if you are designing a system for 100 watts, just as an example, so if you have a 100 watt system or 1 kilowatt system, you want to design a 1 kilowatt system. For this particular 1 kilowatt system, if we do not consider any kind of losses in the system, but we require, if we have a solar panel of 250 watts, then this means in order to make 1000 watt or 1 kilowatt, we will require at least 4 solar panels. So like this, we are going to require number of solar panels. So this is the largest number of quantity within the system. So it will take the largest area. It is going to take the largest expense, or the your capital cost is going to come from this PV modules. So the efficiency of these modules range from 3% to 24%, and it depends upon the type of technology which is being used or the type of solar panel you are using. The photovoltaic panels, the main types of these photovoltaic panels can be either they can be silicon photovoltaic, which can be further divided into monocrystalline or polycrystalline, or thin film photovoltaic, which has further divided into cadmium telluride, copper indium gallium, diselenide, or amorphous thin film silicon. To tell you a little bit about more, we are going to discuss a little bit more about this, but as far as this efficiency is concerned, these thin film have the lowest efficiency, and these silicon type photovoltaic system have a higher efficiency. So if we compare between the three modules, the monocrystalline, the polycrystalline, and the thin film, so as far as this pricing range is considered, monocrystalline have these it has a medium cost, whereas polycrystalline has the lowest cost and thin film has the highest cost. And the commercial efficiency range varies. For this monocrystalline, it ranges from 19 to 23%, polycrystalline 17 to 20%, and thin film ranges from 2 to 21%. So if you are looking for a good efficiency, you should always go for either monocrystalline or polycrystalline. And the temperature effect is worst on the monocrystalline, it is medium on the polycrystalline, and best on the thin film. So now what do you see here? So we have to come up with a trade-off between all these kind of properties. So if I am looking for the temperature, if I have a place or a location where temperature usually remains high, so although the temperature remains high, the efficiency is higher for monocrystalline, but the temperature effect is worst in this case. So what is the combination we can go for? We can either go for this polycrystalline, or we can go for thin film. But now the question will arise that, okay, we have this, so what kind of efficiency we are looking for? If we have large amount of area available, we can go for thin film, yeah, because we do not care about efficiency, but at the same time the price is high. So if we want to take care of the price as well, maybe this polycrystalline will become the most effective for that particular kind of situation. So depending upon these different kind of properties, what you have to do is you have to design, or you have to take this decision that what kind of solar PV module will be good for a particular kind of an application. Now the next important part of the solar PV system is the solar inverter. Solar inverter converts your current from DC power to AC power. So here we will have a certain modules available which will be connected together. Yeah. So we have multiple modules here. So sunlight, when it falls onto this solar panels, the electricity is generated. This electricity is collected by a certain kind of a collector system. So let's say these are connected together, and then these two are connected together, and they come to this collector system. So here what we have DC current. So sunlight falls, we have DC current generated onto this collector system. Then what we are going to do is we are going to connect this DC part to the inverter, and on the output, so this DC is going to be input to the inverter, and on the output we are going to get a sine wave or AC system. So other part, since now the question is whether if we are using a certain kind of a hybrid system. In case of hybrid system, we will have certain batteries within our system. Yeah. So these batteries are going to be charged with the help of DC. So now we will be needing a certain kind of a controller which is going to control this charging part and the input coming from here and the output to be provided to the load. So we will need a certain kind of a controller. So one job of this inverter in case of a hybrid inverter will be to have a controller which controls all this equipment within the solar PV system. What if we do not have this battery storage system? So we have a net metering system. Whatever is coming from this solar panel side is going to be converted into AC and then go to the grid side. So utility system or the utility grid, it is going to go out to the utility grid with the help of a net meter which is here. So now in this case, since what we have to do is we have to connect our system, our solar PV system with the grid. So in AC, this kind of connection is known as synchronization. So we have to make sure that the frequency which is being generated by my internal system is equal to the frequency which is available at the grid side. So in our case, this is going to be 50 Hertz. So nominal frequency in our country is 50 Hertz. So we have to make sure that this AC inverter, this inverter, when it generates AC power, this should be generated at 60 Hertz and it should be in phase with the utility system. So solar, the second important point which has to be provided by this inverter, it synchronizes the frequency with the grid. It connects your internal PV system to your external grid. Then the third important job which is done by this inverter is the tracking of the maximum power using MPPT. MPPT stands for maximum power point tracking. And what do we mean by maximum power point tracking? By maximum power point tracking, we mean that, let's say, if we take this curve like this. So on one side we have voltage and on one side we have current. So we have this IV curve. So now this MPPT is going to make sure that when this P, which is basically the combination of V and I. So within the curve of this solar PV panel, it is going to make sure that it is selecting the point where you get the maximum amount of power. So if you take this point here, the voltages become more but the current has reduced, right? But at this point your current is more but the voltage is less. So you need a type of a point where P becomes maximum. So the objective of this MPPT or maximum power point tracking controller is to make sure that the point within this solar PV system is selected which will give you maximum electrical power. As far as these types of inverters are concerned, we can have several types of inverters. One type of inverter is central inverter, one is micro inverter, and one is string inverter. And we are going to discuss this in detail here. So the first type of inverter is central inverter. So when we talk about a central inverter, what is a central inverter? For your whole PV system, when you have one controller for your or one inverter for your whole PV system, these kind of inverter are known as central inverter. So the capacity of this inverter is going to be huge because it has to take care of the whole power which is generated within this solar PV system. So this is an example of a central inverter where you have a huge solar PV farm. This whole solar PV farm is going to provide you power at a certain point, and for this whole PV plant you are going to have only one inverter. So such kind of an inverter is going to be known as central inverter. So but what is the disadvantage of this central inverter? The only disadvantage of the central inverter is what if something happens to your inverter. So if you have some problem in your inverter, or some fault comes into your inverter, then the whole power generated by this system is going to be lost. So this is one of the major disadvantage when it comes to central inverter. Then we have micro inverter. What do we mean by a micro inverter? A micro inverter is a kind of an inverter which has a very small value. As the name implies, it is micro, right? So micro means very small. So in this particular kind of inverter, what we are going to have is, we are going to have a small output power available for each particular inverter, but the advantage is that each solar panel or a certain group of one or two solar panels are going to have their own inverter. And what is the advantage of this kind of inverter? Number one, your system, your collector system, now you do not need an additional DC system in your design. So everything from each inverter is going to provide you power in the form of an AC power, and you can connect it to a certain bus and provide your home load in the form of AC. And another big advantage of this is that what if you have a shade on some inverter. So you have a design like this. So let's say if we have a tree here. So if we have a tree here or something like this. So we have a tree or something, a building or something here. So when the sunlight was here, so passing through this, due to this shading effect, maybe the sunlight cannot fall onto this inverter or say these two inverters, but the sunlight is falling properly on the other inverter. So this way your output is not going to be affected more, because these inverters are going to provide you with the maximum power. Only the affected panel is going to provide you with less power. After micro inverters, we have the string inverters. In case of string inverters, what we have is that we create string of solar PV panel. So for each string, what we are going to have is, we are going to have one inverter for each particular string. So if we assume that now in this case station generates more than central inverter and less than micro inverter. So in this case what is happening is, so this is one string, this is connected to one inverter. So then there can be another string exactly like this one. Again, this is going to be connected to this. So we'll have a bus, certain kind of a bus here, and which is been. But these type of string inverter, they are mostly used when it comes to like industrial applications or grid connected solar PV systems, but not for the home system. For the home system, we usually have an inverter known as this central inverter. Now same way we can have two combinations of MPPT. So MPPT can either be a single MPPT or a multiple MPPT. So when we say single MPPT, it means that like central grid inverter, we are going to have only one MPPT controller. This MPPT controller is going to track the maximum power point for the entire PV system. It is going to find the optimum point for the entire PV system. On the other hand, we can have multiple MPPT. In case of multiple MPPT, what is going to happen is that each MPPT is going to optimize the power of its own string and then provide to the inverter. So this way we can increase the efficiency of our solar PV system to a little bit. Then the mounting structures. So as I said, we can connect our PV system in different ways. So these are the different kind of mounting system. These mounting systems can either be fixed type. In fixed type, we connect our PV modules at a particular angle, a particular fixed angle which cannot be moved. So these are known as fixed type structures. Then we can also have tracker type. In case of tracker type, we can have two type of structures: the single axis tracker or a dual axis tracker. So in the tracker kind of a system, what we are trying to achieve is that we are trying to maximize the power for the sunlight falling onto the solar PV panel. You must have observed that when you see your sun path, sun starts from the east and sets towards the west. So throughout the day, your sun is changing the position. So in fixed type, when the sun is changing the position, the angle of this solar PV panel is not going to change. So the angle at which the sun rays are falling is going to change throughout the day. Whereas in the access controller, in this kind of a system, the access controller is going to make sure that each time the sun rays are falling at a particular maximum optimum level when the sun changes its path from one side to the other side. So the fixed mounting structure, they can either be connected to the ground or they can be connected onto the rooftop. So here we have two different kind of, and by the way, these both are fixed type. Then we have this axis tracker or the tracking system. In the single axis tracking system, as I said, as the sun positions moves from sunrise to sunset, the axis tracker is going to move its location in order to make sure that maximum power continues to fall, maximum sunlight continues to fall onto the system. Whereas in case of dual axis tracker, it is not only going to adjust its angle, or it is not only going to track the system from sunrise to sunset, but also changes its location with respect to the changing seasons. So with the changing season, the angle of this the angle is going to change. Similarly, throughout the day, the angle is going to change. So this type of systems are known as dual axis tracking system. And the balance of the system consists of your racks in which you are going to put your cables. Similarly, the distribution boxes or the distribution panels, the cable. Similarly, these blocks on which you are going to place your solar PV panels, then the connectors through which your solar PV panels are going to get connected, the circuit breakers, the fuses, these are going to create the balance of the system. Basic power system analysis using ETAP course. In this lecture, we are going to get an overview of some basic solar design calculations, because these design calculations are very important while evaluating solar PV system or creating a solar PV system design. So even if you are not designing the solar PV system, you are just studying the solar PV system, it is important that you get an idea about these kind of terminologies. So we are going to go through them one by one. So the first thing is this angle of declination. So when we talk about the earth rotation around the sun, we know that earth rotates around the sun throughout 365 days. So for 1 year, the Earth completes its rotation around the Sun. So when the Earth is going around the Sun, what we see is that it is going to change an angle with respect to this Sun or with respect to this universal axis. So if we assume that this universal axis, the perpendicular line passing through the Earth is a little bit tilted at a certain angle. So this tilt between the two is known as angle of declination or delta. So when we talk about this delta varies from plus 23.5 degrees to minus 23.5 degrees. So as the Earth rotates around the Sun, this angle of declination changes throughout the year. So as a result of this change in angle of declination or rotation of Earth around the Sun, we have different kind of, number one, we have different kind of seasons. So at during the June, we have this summer solstice in which the daytime is greater than your night time. Similarly, during September and March, where we have equinox, we have daytime almost equal to night time. Similarly, during the winter solstice, we have night time or the daytime less than the night time. So as a result of this rotation around the Sun, the rotation of the Earth around the Sun, we have number one, different seasons, and with the variation of these seasons, the daytime for which the sunlight is available for a particular area or a particular location varies. So this way, our solar PV design is going to be affected by this rotation, because as the Earth rotates around the Sun, the number of hours during which the sunlight is going to be available is also going to vary. So we need to calculate this, and this is calculating with the help of angle of declination. Then the next thing is solar orientation. Now there are two things related to solar orientation. The first thing we have seen that as the Sun, number one, as the Earth rotates around the Sun, my angle of declination is going to change. Number one. So with the change of this angle of declination, the sun light which is going to fall onto the solar panel is going to change. So this change is due to the rotation of the Earth around the Sun, and then we have another kind of rotation which is a 24-hour rotation from east to west when the Sun is the Earth is rotating around its own axis. So this revolutions take 24. This is completed within 24 hours, and during these 24 hours, the Sun comes out of the east and then continues to go to its maximum value during noon and then sets in the evening time. So as a result of these two rotation or these two orientations, the sunlight falling onto the solar panel is going to be affected, and this can be controlled by two angles. The number one is this azimuth angle. This azimuth angle is at which location the solar panel should be facing. So if you want to know the facing of the solar panel, this can be calculated or evaluated with the help of azimuth angle. Similarly, at which angle from the Sun my solar panel with respect to the ground should be placed, this is known as my tilt angle, and tilt angle is also given by beta. So depending upon the location on the Earth, which is given by, when we talk about Earth has a certain longitude and certain latitude. So based on this longitude and latitude, wherever the location we are on the Earth, this orientation is going to vary. So the first step in order to calculate the solar calculation is to know about the location, the latitude and longitude. Once you know the latitude of your the latitude of the location where this PV system is going to be designed, based on this we can calculate our azimuth angle and the tilt angle. Now, without going into the detailed calculation, let us talk about some optimum angles or the quick calculations. So hand calculations or quick calculations. So if you are interested in calculating the tilt angle, the ideal tilt angle during the winter can be given by the latitude into 0.89 into 24 degrees, where latitude is the point or the location within the earth where this has to be placed. Similarly, during summer season, it can be given by latitude in 2.92 minus 24.3 degrees. See, this change in degrees is due to this changing in the rotation. Similarly, if we want to calculate the tilt angle for all around the year, it can be simply calculated with the help of the equation latitude in 2.98 minus 2.3 degrees. So whatever angle we are going to get from this is going to be basically the tilt angle with respect to ground. So this, if this is my solar panel, this is my ground. So at this location, so I have to place my I have to mount my panel in such a way that with respect to ground it makes this angle. So this angle is known as tilt angle or beta. Similarly, azimuth angle. Evaluating azimuth angle is pretty straightforward. If the location, when we talk about Earth, so for the Earth we have two locations, right? So if this is the equator, anything above this equator comes into the northern hemisphere and anything below this equator comes into the southern hemisphere. So depending upon if the location where you are trying to calculate, where you are trying to put this solar PV is either above equator or below equator, or in other words in the northern hemisphere or the southern hemisphere, so depending upon the location you can select the facing of the solar panel. So if the location is available in the northern hemisphere, then the solar panel facing side should be north facing. Similarly, in the southern hemisphere, the facing side will be north side. So if we consider location of this South Asia, where India is located here, in this particular case our azimuth angle will be south facing, because we are in the northern hemisphere, so our location of the solar panel should be south facing. So here is a simple example. Here we are taking one location in Jordan, Amman. So if we assume the location in Jordan, Amman, and if we want to calculate the different angles related to this solar PV design, what we can do is, the first thing we need to do is we need to identify the latitude. For instance, for Amman, the latitude of this area is 31.95 degrees. We can simply calculate it from the Google Earth or some other site. So whenever you add a location of any, if you add any location in Google Earth, it provides you with certain kind of longitude and latitude. So from there you can get this latitude. Now if we want to calculate the tilt angles, we simply have to use the formulas we mentioned here based on this. So if I want to optimize my system for the summer condition, I will have to maintain my tilt angle of 5 degrees. Similarly, if I want to optimize my solar panel for winter season, then I have to adjust my solar panel at 52 degree. But if I want to get a location which can operate throughout the year, then I should place my tilt angle at 29 degrees. Similarly, because Amman is present in the northern hemisphere, so my azimuth will be south facing, or my solar panel should be south facing. Now to give you an idea about the sun hours or the sun hour concept, the sun hour concept is like this. You know that throughout the day, the solar energy being provided by the system is going to vary. Why it is going to vary? During the sunrise and the sunset, the solar irradiance or the solar radiation falling onto the solar panel is going to be very less. whereas during the peak it is going to be maximum. So what we can do is for solar angle, instead of now here during this part and similarly during this part and during this part, we are not having this energy at its highest value, but during this part we are having maximum energy. So maximum. So what we can do is we can take a location of this part and theoretically displace it here. Similarly, take this part and theoretically displace it here. So now instead of this bell curve, what we can get is we can get this rectangular type of shape. So this particular rectangular type of shape in which the energy you can get throughout the day through the solar panel is known as this peak sun hours. So this way you can calculate peak sun hours. Now some other concepts regarding this is power to energy. Now we know that the power is basically the instantaneous power which is available at us at that particular location. But when we talk about when we want to talk about throughout the day or for a particular duration, this power, instant power multiplied by the number of hours or by the time, so work done with time is known as energy. So whatever is the energy consumed by the load, for instance, if you have a 10 watt bulb in your house and it operates for 6 hours. So this means that the power of this bulb at any particular time can be 10 watt. But the energy consumed by this bulb for 6 hours is going to be 10 multiplied by 6 is equal to 60 watt hours. So this way we can calculate the energy from the actual power. So for instance, if we know that we have a 1000 watt solar PV system and it can give power for 6 sun hours, so that we can say that the energy which we can get from a solar PV system is going to be 6000 watt hours, because the sunlight is only available 6 hours for 6 sun hours rather than whole 24 hours. Now the actual power in itself, this will be equal to the peak power multiplied by the performance ratio, because we know that any equipment, any system which occurs in this world, once you provide this energy to the system, we are going to get some output. Now the energy provided into the system can never be equal to the energy out of the system. There are always going to be some losses within the system, and this is true for any kind of system which is occurring in our world. So same is true for this solar PV system. For instance, whatever the power or the solar radiation which is falling onto the solar power will not be completely converted into DC current. Some of it is going to be lost within the solar panel. So we need to calculate the efficiencies, and based on this efficiency multiplied by this peak or the maximum power will give us actual power. So for instance, again taking the example, if we had 100, again if we take the example, let's say we had this 1000 watt PV panel with the efficiency of only 25%. So what does this mean? Out of this 1000 watt, this is the peak power possible, but the actual power possible will be 1000 multiplied by 0.25. So this is going to be only 250 watts. So actual power which will be available at any instant will be 250. And how much energy we can gain from this? So we will simply multiply this actual power with the sun hours or the duration during which this power is available. So therefore we can say that my actual energy or the total energy which is generated by the system will be equal to my peak power multiplied by my performance ratio or my efficiency of the system multiplied by the time. So now to understand with a simple example, for instance, if we want to calculate the energy produced from 1 kilowatt hour, same 1 kilowatt power system in KSA, where the average peak hours is 5.6 to 6.5 hours and a performance ratio of say 75% to 85%, what is going to be the energy? So the energy throughout the day or throughout the year can be calculated as the peak power multiplied by my efficiency multiplied by my peaks and hours multiplied by 365 days, because we are calculating for the entire year, so that is why we are multiplying it by 365 days. So the total energy generated by the 1 kilowatt power system throughout the year is 156 kilowatt hour, or in other words 1560 units, because this kilowatt hour is also known as unit which is billed by your utility. So I have generated 1560 units. So for instance, if I was able to consume, or my annual consumption is 2000 units throughout the year, so what will be my net bill in this case? My net bill for annual net bill will become 2000 minus 1560. So this means that instead of paying for whole 2000 units, I have to only pay the difference, which is around equal to 440 or 450 kilowatt hour, or 440 or 450 units. So here, to further explain this net metering example, for instance, the electrical consumption within the load is 21,900 kilowatt hours per year. The solar insolation or the sun hours is equal to 6 hours per day. My panel output is 500 watt power or 0.5 kilowatt per hour. This is my peak power, and the performance ratio is 80%. So this means that kilowatt hour by kilowatt hour peak will be equal to, or my annual power throughout the year is going to be my sun hours multiplied by my 365 days for throughout the year multiplied by my performance ratio will give me around 17.5 kilowatt per peak. So the capacity needed can be calculated. So now here what we are trying to do is we are trying to calculate the capacity. So here we are getting the ratio, that how much energy we can get per kilowatt power for the entire year. So this equals 1752. So now in order to get the capacity of 21,900 with this type of system, we are going to need a solar power system of at least 12.5 kilowatt power. So if we design a system of 12.5 kilowatt power, we can get the annual energy of around 21,900 kilowatt hour. So for this particular case, for this 12.5 kilowatt system, the number of solar panels we are going to require is that, since the one individual solar panel is equal to 500 watt or 0.5 kilowatt, and the total power required is 12.5, so simply divide 12.5 by 0.5, which requires 25 solar panels. So in order to design a system which can give you 21,900 kilowatt hours per hour for a solar insolation level of 6 kilowatt per meter square for a day, we need 12.5 kilowatt hour system consisting of 25 solar panels. Similarly, the next selection will be the inverter selection. So what kind of solar inverter we have to select? Now for this particular, the thumb rule is that if you want to select a solar panel, make sure that the DC to AC ratio is preferable to be 1.25. So this is particular for Middle East, but it is going to work for this India also, or the South Asia also. So what we have to do is, for instance, if we have 1000 watt or 1 kilowatt system, then my inverter power should be 1 kilowatt multiplied by 1.25. So for a solar PV system of 1 kilowatt, I should have a DC inverter of at least 1.25 kilowatt. So what is the reason? The reason is that DC peak power is barely achievable Number one, that although we have this sun curve, but it is not necessary that each day you are going to receive this peak power. Always the power will be something less than this, because this is for this we will achieve maybe for 1 day or 2 days throughout the system when the sun is for the maximum amount of time, whereas in the during the winter or autumn or spring we may not have this value. So this is the number one. The inverter efficiency is at its rated power. Too many extra losses. Now the problem is that inverter itself is converting energy. So you have dual conversion here. Number one, the conversion is coming from the PV system, which is converting sunlight into DC power. Then you have inverter, which is converting this DC power into AC power. Similarly, you have cables within the system. You have charge controller. You have different kind of equipment within the system. Each equipment within the system is going to have a certain amount of losses. So in order to cover up these losses, we need to take care of this. So what we can say is that if we have a DC power of 22 kilowatt, then the best inverter size is to use 20 kilowatt, but we must check the inverter data sheet to assure not exceeding the maximum DC input power. So the first thing we need to make sure is that my DC power should not exceed. Yeah. So if my inverter is providing maximum of 22 kilowatt and we are sure that we cannot achieve 22 kilowatt hour, but if we know that we can achieve this 22 kilowatt hour, so we need to take care of this. So we need to design, or we need to consider the solar inverter according to my DC input power. Now the last important thing to discuss is this combination. Now how we can connect this solar panels together in order to create a string. So in order to create the string, you know that now in any kind of a solar PV system, you are not going to have one solar PV panel. You are going to have multiple solar PV panels. So now the question is how to connect this solar PV panels in order to get the particular amount of energy out of it. So for this purpose, we may have to connect our solar panels in the form of series and parallel combination. So when we talk about a series combination, what we are basically doing is we are connecting the positive terminal of one panel to the negative terminal of the other panel. This way we can get series combination. So if we assume that we have one panel which has a capacity of 12 volt and 5 ampere. So if we connect these two in series, what is going to happen? The voltages are going to add up. So if one panel has 12 watt and two panels are connected in series, so my new voltage for this series combination will be 12 multiplied by 2, or 12 plus 2 is 12 plus 12 is going to be 24. But the current passing through this solar panel is going to remain same, and this is going to be only 5 ampere. Whereas the other combination is this parallel combination. And when we talk about parallel combination, what we basically do is that the positive side of the panel is going to be connected to the positive side of the next panel. Similarly, the negative side of one panel is going to be connected to the negative side of the other panel. In this way, the combination achieved will be known as parallel combination, and in case of parallel, the reverse happens. In case of parallel, the voltage throughout the panel system is going to remain same, whereas the current is going to add up. So we are going to have some current coming from here. This current is going to add it up with this current, and then this current, this. So the total current will be the combination of these three currents. So I out of this will be equal to I1 plus I2 plus I3. And when we make the combination of these two, the series plus parallel, so we'll see, okay, if how many solar panels are in series, so all series the current will be added. Similarly, for the parallel for the series combination, voltages is going to be added, and for the parallel combination, current is going to be added. And in this way we are going to get our particular combination of voltage and current we want to get out of this solar PV system. So here is a simple example. So panel distribution within a string. Let us assume that we have a one solar panel which can provide a maximum voltage of 200 volt and a current of 10 ampere. So if when we create a string out of this, so for this particular string, what is going to happen? The current from here is 10 ampere. So since these are all connected in series, the current is going to remain same. So the current input to the inverter is going to be 10 ampere, whereas the voltage are going to add up. We have 4 panels. So 200 plus 200 plus 200 plus 200 is going to give me 800. So now we need to make sure that what is the voltage range of my inverter. So that I can, when I create this series combination or the string of solar panel, I should not exceed the rating of this inverter. If I exceed the rating of this inverter, what I can do is I can damage my inverter. So here is a particular example of a solar PV panel and a solar PV inverter. So what kind of data you may expect from this kind of is this. So for here, for instance, in this case, when you see solar panel, what you are going to see is you are number one going to see what is the peak power out of this. So the peak power in this particular case is this solar panel can give you a maximum power of 215 watts. So the different currents, the rated voltage for this particular is 39.8 volt and the current is 5.4 ampere. So these are the open current and the short circuit current. This is the maximum available which can go, but here, and the maximum system voltage can be 600 volt. So here we are interested in these 2 points. So my solar panel can give me for a particular maximum power point tracking 39.8. So now the next thing I will have to do is I have to check it against here that what is the maximum startup voltage, what is the maximum power. So here my voltages can be from 100 volt to 500 volt. So if the input power to my inverter is between 100 to 500 volt, my system is not going to get damaged. But the maximum in any case should not exceed 600. Welcome to Basic Power System Analysis using ETAP. In this demonstration video, we are going to learn how to model a solar PV system in ETAP. So now we have the same example which we have used for our different analysis throughout the course. So this is the case where we have this system and industrial facility with various kind of voltages level. At each voltage level, some motor load and some static load is available. See, some static load, some lump load, and everything is available. We have performed load flow analysis on this. We have performed short circuit analysis on this. We have performed motor starting analysis on this model. So considering the same model, and we prepare different configurations which we can see from here. So now what we want to do is we want to create, now let us assume that for this particular industrial facility, the owner of the facility or whatever is the administration of this or the management of this facility wants to connect this solar PV into this system. So now if we want to connect the solar PV into this system, we can see, we will learn how to model this PV system and how to adjust its parameter so that we can get our particular results. So before going on to this, let us just perform the load flow analysis, a simple load flow analysis to see what is the power flows and the voltage profile within this so that we can compare it at a later stage with the results of our solar PV system. So now let us go to power flow. I have my configuration as normal selected here, and the load flow results will be stored in LF_normal. So this is normal load flow. Going to the top, if I perform solve here, so the power which is input to this industrial facility is equal to 16.18 plus 8.12. So almost 15 megawatt or 14.3 or 14.4 megawatt of power is being injected into this industrial facility through this two power grid or two transmission line which connects the grid, outside grid, to this. Now what do we want to do is, on this 0.48 kV level, we want to model a solar PV system. And what kind of solar PV system we want to model? The details we see from here. So here is our example solar PV for ETAP. The peak power produced from this solar PV system is going to be equal to 7.8 kilowatt. And the panels we are trying to use or we will be using have a maximum power of 230 watts, having a Vmax or VMPP of 29.32 volt and IMPP or current DC of 7.82. So for the standard temperature conditions at 1000 watt per meter square of solar irradiance, this solar panel can give me a maximum power of 230 watts. So in order to create 7.8 kilowatt power out of these 230 watts, we consider the number of series panels to be 17, number of parallel panels to be 2. So the total number of panels equal to 34. So for the series panel, what is going to happen? For the series panel, the voltages throughout the panel is going to increase. Similarly, for the parallel panels, the current within the panel is going to increase. So this is the design of the system which we want to model in our ETAP. So now once we go to ETAP, now we have all these values available. Now the interesting thing to note here will be, or the important thing to note here will be, the power that is input to this. So the incomer power through this transformer here is 0.348 megawatt here and 0.348 megawatt here. So if we add up the two power, so we have a total load of around 0.7 megawatt or 7 kilowatt, almost 7 to 8 kilowatt of load is available here. So if we want to check this load in kilowatt, what we can simply do is we can change the unit from here. So let me go here. So we have this, these are in megawatt and megawatt. So if I go to here, unit to kVA, press OK. So here 348 and 348. So almost 350 here, 350 here. So almost 70. So if we model a solar panel of 7.8 kilowatt for this particular location, what we are going to end up with? We are going to end up with zero power. We should theoretically end up with 0 megawatt of 0 kilowatt of power here, or some power being exported to my HV system. And another important thing would be to note how my voltage profile changes in this particular case. So for this purpose, what we can do is we will simply go to my edit mode, just go into the edit mode. So we are assuming that this solar panel is going to be available on bus 2B. So let us just extend our bus. Now for modeling this solar PV panel, you have two possibilities available. Either you can model your solar PV panel from this AC toolbar with this here solar PV array. So this is option number one. What you can do is, if you select this and click here, so you have this solar PV panel here. So if I double click on this panel, you will see that you have a tab for solar PV panel, the PV arrays, the combination of series and parallel we are going to give here, the inverter design, the physical characteristic, the time domains, and the things like this are available in this. So everything can be modeled here. Now there is another way of modeling this solar PV panel. The other way of modeling this solar PV panel is using this DC toolbar. So if you want to model the solar PV panel as a DC, so what you have to do in this particular case is that you have to use this solar panel. So if I click here, so now in this particular case, this is just the solar PV panel, nothing else, only solar. If I double click on this, you are going to see the solar PV and PV array. So all the data related to only solar PV panel is there. So if you want to model, now we will require some kind of a bus for this purpose. So we have this DC bus to which my solar PV is going to be connected, and the DC voltage of this is going to be depend upon the series and parallel combination which we are going to achieve from here. Once this is done, then we can select the inverter from here. So inverter on this DC tab, we click here. So connect this here, and similarly connect this here. Once this is done, so here we are going to have, but in this case, so if I double click on the inverter, so you have this rating, loading, and everything related to the solar PV inverter available here. But in this case, how I can find the inverter ratings? So if I double click, if I go to inverter, within inverter you are going to see this inverter editor. So if I click on this inverter editor, but you see the same tab which is available for solar inverter here is available here. So in simple words, what we can say is that if we assume, or if we want to use this DC type, in DC type we will have to individually model my solar arrays and my inverter. Whereas if I want to use a composite model which has the solar panel as well as the inverter, we can use this model from here. The both are going to give the same results. But for our purpose, or for this demonstration purpose, we are going to use this composite model. So just let me select this model and delete. So now let us connect this model to here. So once we are done with this, now what we can do is we can model the different characteristics. So first of all, let us start from the solar PV. So the name, let us remain it PVA1. You can give whatever name you want. It is in service. Let us go to PV panel. Now, there are two ways to model the values here. The first way to model the values is either if you have all these data available from the solar panel data sheet. So you will go to the solar panel data sheet. You will see each and every kind of data from here. Come to your solar panel and put everything here. But if you do not know these values, or due to some reason you do not have these values available, there is another possible way. What we can do is we can use different panels available within the ETAP library. So let us click on this library. For this particular example, let us assume that we have a solar panel from Q cell. The solar panel from Q cell having IMP of 7.82, size of 230, short circuit current of this, maximum VDC of 100 volts. So this is something similar to the one which we plan to model here in our particular example, that the panel should have 230 watts and a current of 7.82. So when I pressed on OK, see all the data related to the solar panel will come here. So for this particular panel, the number of cells within this panel is 60. This is a polycrystalline 230. If we say here, the total power is 6.9. The VMP or the V maximum power point is 29.32. IMP is 7.82. Short circuit is 8.27. V open circuit voltage is 36.08. Efficiency is 13.8. Percentage fill factor is 76.4. So in short, all data related to this is. Then you can see two kind of curves here. The first curve is this PV curve and the second curve is this IV curve. So what does these two curves tell? These two curves tell us that with varying solar irradiation level, what is going to be my maximum power point tracking, what is going to be my maximum current, and what is going to be my maximum voltage. So these curves help us understand these different values within the solar panel. So if I first go to my PV curve, I can even print this value. So irrespective of printing, here you see the maximum voltage which you can achieve, the open circuit voltage is 36.08. See, so this is available here, 36.08, and the value is a little bit changing with respect to the different solar irradiance level. Similarly, the second thing which is given is the power, the maximum power which you can get for the particular voltage level and at the maximum power point. And these different curve gives you the different solar irradiation levels. Similarly, this IV curve or current voltage curve is going to give me the values of current and voltage for different solar irradiation level and the maximum power point tracking value. So if I am operating at 1000 watt per meter square or the maximum possible solar irradiance level, the current I am going to get from this system is 7.82, and for this particular my voltage is going to be 29.32. So 29.32 is my maximum power point voltage, and if the solar radiation is going to reduce, you see my current is going to reduce. Similarly, for this reduction in solar irradiation level, I am going to have different values of power output available from here. So if I am operating at noon, maybe I'll be getting the maximum 100 watt per meter, 1000 watt per meter square or maximum irradiance level. So for this maximum irradiance level, I'll be getting 230 watt out of this solar panel. But if I am operating during evening time or during the morning time when there is sunrise or there is sunset, my value will be a little bit lower, maybe operating at any of this curve. So this was a little bit about the solar panel. And the next thing is solar PV array. So if I go to array, so this is telling me my solar PV array has this watt per panel value is around 230 watts. But I still have to provide the number of solar panels. So how I can provide the number of solar panels? The number of solar panels for this particular design, which is going to be provided you by the designer for this particular design, the value is series 17 and parallel 2. So if I come here, series 17 and parallel are 2. So by changing this value, did you note that my kilowatt DC value has changed? My DC current has changed. So now DC current, depending upon the number of series, my maximum DC will be 498.44. My number of panels will be 34. My DC current out of this system will be 7.8 amperes, and my DC ampere, the maximum kilowatt DC will be 7.8 kilowatt DC, and maximum amperes will be 15.6, because since two are in parallel, so it means 7.82 plus 7.82 is going to give me 15.64. Welcome back to solar PV system modeling using ETAP demonstration video. Let us continue with modeling our solar PV system for our sample network. So now once when we go here, we have already seen how to model or how to get from the library the type of solar module which we need. So we have selected the solar module here. So now once the solar module is selected, we adjusted the solar array. So the series and parallel combination of the solar array depends upon the maximum power output you require from the solar PV system. So in our case, our requirement was 7.8 kilowatt. This 7.8 kilowatt requirement could be met with the help of 34 solar PV panels of 230 watt each. Now, when we talk about solar panels, we need to know the two important factors that affect the output of solar panels. These two factors are the solar irradiance and the ambient temperature. If you see here in the design tab, four things are given: the irradiance level, the TA, which is the ambient temperature, TC, the temperature condition at the solar panel itself, and the maximum power in kilowatts of the solar panel. Now when we say that the power of the solar panel is 230 watt, this 230 watt is at a specific condition. What are these specific conditions? These specific conditions are temperature should be 25 degrees centigrade and the solar irradiation level should be 100 watt per meter square. So this means, and this is also known as STC, standard temperature conditions. So if we see this condition, it means that in order to get 7.8 kilowatt of the solar output from this particular PV system, we should have an ambient temperature of 25 degree and solar irradiance level of 100 watt per meter square. So in this case, we already have solar irradiance level of 100 watt meter per square, but let's see TA, the ambient temperature is 30 degrees. So for this 30 degree of ambient temperature, you will see that the maximum power output available is 7.68 rather than 7.8 kilowatt. So what if I adjust this value to 25? If I make this value 25, you will see my maximum power has increased to 7.8 kilowatt. Similarly, if I adjust my solar irradiance level, let us reduce this value to 500. See, the same solar panel or the same solar PV system which has the ability to give me 7.8 kilowatt as maximum will only be able to give me 3.82 kilowatt if my ambient temperature is 25 degree and solar irradiance level is 1000 watt per meter square. So now what should be the value? What value should I consider for my solar PV system while performing this analysis? So now this is a really important question, because this solar irradiance value will vary from day to night, number one, and from season to season. So if you are operating in summer season, your solar irradiance level will be something different, your temperature will be different. But if you are operating in winter condition, your values will be different. So this way, it is very important to know that for which particular time you are performing this analysis for. Now, in order to get this value, what we can do is we can calculate this with the help of solar irradiance calculation. So ETAP provides you with a method by which you can calculate the value for the particular day, particular time, for a particular location. So based on this, ETAP is going to calculate the ambient temperature of that location, the solar irradiance level of that temperature, and based on this, how much maximum output power in DC you will be getting from this system. So for this purpose, let us click on irradiance calculation. For this purpose, let us first calculate the longitude and latitude of the location where we want to put this solar PV system. So let us assume that we want to put this solar PV system in Delhi. So for this purpose, what we can do is we can simply go to a website known as latlong.net. Here, if I am going to enter any location around the world, say Delhi, and I press on find, longitude and latitude location. So now I have this location. I can simply use this location. My latitude is 28.7 and my longitude is 77.1. So if I come back here, so the values are 28.7 latitude and 77.1 is the longitude. So the time zone, now let us select the time zone for this purpose. So we have to select the time zone. So this is my time zone. I will select the time zone here. The time of the day for which I want to perform this analysis. As you know that the solar PV will be maximum around peak when the whole sun is available. So for this purpose, let us assume this value to be 12 noon. So let us make this 12 noon here, and you can select any day any day of the year. So for me, let us select the date of 6 June. And if I press calculate, so everything has been calculated by so 12 noon instead of 12 night, because if here you will see that solar irradiance level at this available will be around 903 watt per meter square. So I can update all the values, or I can update one value. So let me update selected value. So when I press on update selected, you see the automatically my value has been updated with the solar irradiance level. So once this value is updated, now instead of 7.8 kV, I am going to get 7.2. So this way you can adjust any value you want regarding your solar PV system. Now let us press OK. Once we press OK, and the value is updated. Welcome back to solar PV system modeling using ETAP demonstration video. Now that we have modeled our solar PV system, now it's time to model our inverter as well. So for the purpose of modeling the inverter, we will again double click on my solar panel or the solar PV system. Here we have already adjusted the solar PV panel. We already selected the type of panel we require. The number of arrays we have within the panel, we have already selected this part. Then the next part is inverter. So now for the inverter, the basic data for the PV array is that volt DC can be as high as 498.44 and my maximum kilowatt is 7.8. So I need an inverter which is similar to this or a little bit higher than this. So for this purpose, usually the factor of 1.25 is used, but for this purpose what I'm going to do is going to inverter. Let us select the inverter, go to rating. So now here 7.8. So how about we select a DC rating of 8 kilowatt. It is always good to select a higher rating inverter, so that in future if you decide to increase the number of solar panels, so you won't have to change the inverter itself, because inverter will have the capability to cover this. So now we have selected this. It is 498. So how about we select 400 volts for this purpose. So this is my current here. Here you can change the efficiency. Let us assume that at 100% efficiency is 97%. Here 95%. Here 93%. So I change my efficiency here. So let me select it to. So this is my kVA. And my power factor is 1 per unit. I can go as low as 80. My AC side voltage is 0.48 kV. So everything is good here. If I go to generation, you will see here that for my design category, my voltage is my DC power is 7.02. This is exactly the DC power which I am getting for the particular solar irradiance level and the particular temperature. So for this temperature, for this particular solar irradiance level and temperature, my DC output is 7.02 kilowatt. And then I have a losses of 0.284, which is around 3% of this losses are within the solar inverter, because this AC to DC conversion losses, these efficiency losses, and after these losses, the AC power I am getting at my solar output is 6.73. So this will be exactly the power which I will be achieving from my solar PV system. And when I press OK, so here my data has been updated. And when I press, you can also select the cable from the library. So this will be the cable which will be connecting your solar PV system, the inverter, the output of the solar PV system to your main bus bar, system bus bar. But here, just for the sake of demonstration, I am not doing this. So once I press OK, my data is added. So the next thing we have to do is we need to perform the analysis, the load flow analysis, in order to see how this has impacted my output. So for this purpose, we are going to do two things. The first thing I will be doing is I will be performing my analysis without any solar PV system, and then with the solar PV system, so that I can get the difference between the two. Since the value of this system is very small, so you will see a little bit of change, but if you will increase the solar PV output, or you will design a larger solar PV system, then surely you are going to see the difference. So now first let us calculate this. Let us go to load flow analysis. For the load flow analysis, let me just switch it off. So now, for now, I have no solar PV system connected to my solar PV connected to my industrial system. So this is my original system which we have already studied. So once I perform load flow analysis, you will see that my voltages are at this 0.48 kV bus or 480 volt bus is 93.89 without anything, and then the input to this bus is 350 kilowatt each end, and 348 here and 348 here. So now what I have to, and the kilowatt is 255.2 and 255.2. So what if we install this solar PV system in our industrial facility? So what I'm going to do is switch this in. When I press OK, let us solve again. So now this time you can see that my solar PV system is providing me with a power of 6.73 kilowatt, which is as per after the losses and everything. And for this particular, my power here, the input power has reduced from 348 to 344. So this reduction in power is due to this additional generation available from solar PV system. But if you see the megawatts, the megawatt value is still the same. It's 255.2. Why is that? Because my solar PV system is not providing me with any reactive power. But in reality, this solar PV system or the inverters have the capability to provide you with reactive power. And how do they do it? Basically what is happening is by controlling the firing angle. Basically what you have to do is you have IDC as input. Now by controlling the firing angle of the electronic circuitry, what you can do is you can convert this into ID and IQ, your D and Q axis. By converting your current DC current into ID and IQ, you can get the active power as well as the reactive power. So how I can get some reactive power out of this system? For this purpose, what I have to do is I have to go to my solar panel. I will go to my inverter editor. I go to my rating. Here I am saying that my solar PV system is operating at unity power factor. So instead of unity power factor, how about if my solar PV system operates at 95% or 0.95 power factor? This is most commonly used power factor which is given for this inverters as per standards. Even in the IEEE standards or IC standards or any local or the national standard, the requirement from this renewable type of system is that they should be able to provide me with reactive power with a power factor control of plus minus 0.95. So this is exactly what I am doing, 95%. Let us see if I press OK. So I have changed my power factor. Let me press OK. Let us calculate it again. Okay, so because I haven't mentioned it there, if I go here, inverter, module, so here I have given the value, but my design value is still 100%. So instead of 100, let us say I want this time 95% rather than 100%. So now, did you see? My power has increased from reactive power. Before the value was 0. As soon as I change my power factor, by changing the power factor, I'm starting to get some reactive power out of this system also. If I make this 100 again, so 0. If I make this 95, so it becomes 2. So I press OK here. Let us press OK. OK again. Let us try to solve this case again. So this time you are getting exactly 2.2 kilowatt out of this system, and for this reason my reactive power from here has reduced or dropped from 255 kilowatt to 254 kilowatt.